Hey everyone, and welcome to our exciting course on database design and modeling with PostgreSQL and MySQL. In this journey, you're going to gain some hands-on experience, like seriously hands-on, in building robust databases, understanding normalization, and mastering SQL like a pro. Together, we're going to tackle coding exercises that are not just practical, but also engaging. So be sure to stick around because we've got a final project waiting for you at the end to really test those skills you'll be developing. The code is going to be available in our GitHub repository linked below, so you can follow along easily. So let's dive in and start building some awesome databases. A database is a structured collection of data that's organized and accessed electronically, providing efficient mechanisms for data storage, retrieval, update, and management. Imagine trying to find a particular book in a massive library without any catalog. It would be a nightmare. Databases help us avoid that chaos by implementing systematic methods to organize data, making it easy to search and manipulate. Today, we're diving into understanding databases and data models, and we're making it as engaging as possible. So, let's get started with the basics. Databases, at their core, function like an organized filing system. Just like you wouldn't want your library to be a jumbled mess, a database ensures that everything is neatly arranged and readily accessible. Now, when we talk about data models, think of them as blueprints that define how data is stored and interacted with. This guides us on how to manage the data efficiently. All right, now let's consider some common types of databases. We've got relational databases, which store data in tables. Think of them like spreadsheets, where each row represents a record and each column represents an attribute of the record. Thoughtful pause. Then we have NoSQL databases, which are great for unstructured data, allowing for a bit more flexibility. For instance, if you picture a social media platform, its data might include user posts, comments, and likes, lots of varied information that doesn't fit neatly into a table. And to make things clearer, let's touch on a few important concepts. One key term is schema, which is essentially the structure that defines how data is organized within the database. It's like a map that guides you to find your way through your data landscape. Next, we have queries, which are requests made to the database to retrieve or manipulate data. Picture yourself asking a librarian for a specific book. You're querying the system. Finally, understanding normalization is crucial. It's like meticulously organizing your books to prevent overlapping categories and ensure that everything is stored properly. As we dive deeper, you'll see how these principles come to life in real applications, creating systems that are not just functional, but also elegant in their design. So, hang tight. There's so much to explore in the world of databases, and trust me, it's going to be fascinating. To grasp the concept of databases, let's start with the data model itself. Now, a data model, it's really a framework for defining how data is connected, stored, and accessed. Think of it like the blueprint for a building. Just as an architect creates plans to ensure a structure is sound and functional, a data model organizes how information interacts and fits together. So let's focus on three main types of data models: hierarchical, relational, and object-oriented. Now, as we flip over to relational databases, which is our primary focus, let's dive into SQL, the structured query language. This is the language that lets us interact with data in relational databases like Postgres. It's really exciting once you get the hang of it. Now check this out. SQL, or relational databases, take up 40.0, and that's visually emphasized on the chart. Meanwhile, the NoSQL family as a whole takes the cake with 60.0. Within the NoSQL segment, document databases form the largest slice, representing 25.0, followed by key value stores at 15.0. Then we see both column family and graph databases each making up 10.0. So what does this all tell us? Well, there are some clear patterns emerging. First off, relational databases still hold the title for the single largest individual category. But when we combine the NoSQL approaches, they collectively constitute a majority, right? This indicates a broad adoption of those schema-flexible and specialized stores. From this distribution, we can draw some practical conclusions for system design. If you need that strong structure, transactional integrity, and mature tooling, relational models are your go-to. But if flexible schemas and rapid iteration are key for your project, you might want to lean towards document stores. For ultra-fast lookups and caching, key-value stores are a solid choice, while column family and graph databases are perfect for those niche workloads that benefit from wide column storage or traversing complex relationships. Overall, the chart highlights that modern architectures often balance the robustness of relational systems with the scalability and specialization offered by NoSQL, depending on the specific application requirements. Now, let's implement the following code that sets up our library database. First up, we're going to create a new database named library using the create database command. This action establishes a dedicated space to manage our book collection, which is super important, right? After that, we're going to utilize the \c library command to switch to the library database. This way, we ensure that any subsequent operations are performed within this context without any hiccups. Next, let's create a table named Books. This is where we'll store essential details about each book. The table is defined with 4 columns: ID, title, author, and published year. Now, the ID column uses the serial data type, which automatically generates a unique identifier for each book, making it super easy to track records. The title and author columns are defined as varchar 100, allowing for text entries with a maximum length of 100 characters. Finally, the published year column is designated as an int, enabling us to store the publication year in integer format. And there you have it. This foundational setup provides the structure necessary for our relational database, ensuring efficient data management and retrieval. Pretty neat, huh? Sure. Let's dive right in and see how we can implement a categories table to enhance our book database. We start by creating the categories table using the create table command. This command defines a new table with 2 columns: an ID column, which we designate as the primary key, and it auto-generates unique identifiers for each entry, and a category name column, where we'll store the names of each category. This setup ensures that each category is distinct and easily referenced. Next, we need to establish a connection between our books table and our new categories table. We can do this using the alter table command, which allows us to modify the existing structure of the books table. Here, we'll add a new column called Category ID, which will serve as a foreign key linking back to the ID column in the Categories table. By doing so, we define a many-to-one relationship, meaning that each book can belong to one category, while a single category can encompass multiple books. This arrangement is essential for organizing our data while maintaining relational integrity within our database. Now that we've established our foundational tables, it's time to dive into data manipulation and add some essential information to our library database. First up, we're going to insert 3 book categories: fiction, science fiction, and nonfiction, into the categories table. This step is crucial because it helps us effectively categorize our books, providing a structured approach to managing different genres. Next, we will populate the books table with 3 engaging titles: Dune by Frank Herbert, 1984 by George Orwell, and Sapiens by Yuval Noah Harari. Each book entry will include important details such as the title, author, published year, and, of course, a reference to the category it belongs to by way of category ID. This relationship ensures each book is neatly categorized, enhancing our database's organization. By executing these insert commands, we showcase the power and efficiency of SQL in managing and populating relational data, really enriching our library database with curated content. With these steps, we're not just adding data, we're laying down the foundation for meaningful queries and insights that can emerge from our library's inventory. It's all about creating that framework for deeper understanding. Now, let's see how we can retrieve data from our books table using SQL queries. So, the first command we're going to use selects all records from the table. This is indicated by the asterisk, which just means we're fetching every field from every row. It's the simplest way to get a broad overview of all the books stored in your library database. Now, if you're curious about specific information, like say we want to see only the titles and authors of books published after the year 2000, we can refine our query. By using the select statement, we can specify which fields we're interested in. So here, that would be title and author. Then, the where clause comes into play, allowing us to set a condition for our results. This way, only the books that meet our criteria will be displayed. It's really cool how SQL empowers us to filter and retrieve targeted information efficiently, tailoring our data retrieval to suit our needs. So, whether you're browsing through a few titles or looking for specific authors, SQL makes it all possible. Now, let's see how we can join our books and categories tables to retrieve some meaningful information. So the first part of our SQL statement is going to specify the fields we want to display. We're looking for the title of the books from the books table, and then we want the category name from the categories table. Next, we define which tables we're querying from, starting with, the books table. Now, to connect the two tables, we implement the join clause. This is where the magic happens. We use the on keyword to say that the category ID from the books table should match the ID in the categories table. This relationship allows us to seamlessly combine the data, creating a comprehensive view of book titles alongside their category names. So, when we run our query, we get a well-organized list that not only tells us what each book is, but also categorizes them. Isn't that neat? This way, we really emphasize the interconnected nature of the data we're working with. Joining these tables enhances our ability to query data meaningfully, reflecting real-world relationships within our database. It's pretty powerful, right? Now, let's see how we can enforce data integrity in our books table. To ensure that every book has a title, we begin by applying a not null constraint to the title column. This means that no record in the books table can have a null value for the title. Each book must have a designated name, which is crucial for identifying it in the library. Next, we want to validate the published year entries to confirm that they are all positive integers. We accomplish this by adding a check constraint named valid year that specifies the condition must be greater than 0. This guards against erroneous data entry, such as including books without valid published years or, heaven forbid, negative values. By implementing these constraints, we enhance the reliability and accuracy of our database. This not only helps maintain a well-structured and trustworthy dataset, but also facilitates smoother querying and reporting in the future, ensuring users can rely on the data's integrity in all operations. Now, let's dive into how we can analyze the distribution of books across different categories within our library database. We're going to implement an SQL query that fetches the names of categories along with the count of books in each. By using the count function, we can effectively aggregate the number of books that belong to each category. Now, to make sure we have a comprehensive view, we'll employ a left join between the categories and books tables. This approach guarantees that we retrieve all categories, even those without any associated books, ensuring we don't miss out on any valuable information. After that, the Group By clause will come into play, which groups our results by category names, enabling the count function to accurately tally the number of books in each category. This powerful combination of aggregate functions and joins is really fundamental for pulling insights from our data. It clearly demonstrates how we can uncover meaningful relationships from pieces of information that might seem isolated at first. So, by executing this query, we're not just deepening our understanding of category distributions, we're also showcasing the robustness of PostgreSQL's analytical capabilities in generating insights from data stored in relational databases. We've traversed various aspects of databases and data models, establishing a solid foundation of understanding. Whether it's creating tables, inserting data, querying, applying constraints, or analyzing data, each component plays a vital role in the dynamic world of databases. Remember, the efficiency of data management translates into improvements in accessing information, enhancing decision-making, and leveraging analytics for data-driven strategies. As you progress on your journey of mastering SQL and PostgreSQL, practice remains key. So, experiment with what you've learned here. Play around with queries and tables, and most importantly, always keep in mind the potential your newfound skills can unlock. Thank you for joining me on this adventure into the world of databases. Keep coding, keep querying, and, don't forget to look for those valuable insights in your data. Happy learning! Let's dive into an in-depth exploration of the relational data model, a cornerstone of SQL databases that has been a staple in the industry for decades. This model not only defines how data is structured, it's really crucial, but also plays a vital role in how we interact with that data using SQL. Just think of it as the blueprint for how everything fits together, allowing us to efficiently store and retrieve information. It's like having a well-organized library where every book has its place, making it easy for us to find what we're looking for. So, in this tutorial, let's break this down further and see just how powerful the relational model is in managing our data interactions. So far, we learned that a database is a structured collection of data that facilitates storage, retrieval, and management, making data organization easier. We explored the concept of data models and focused on relational databases, particularly using SQL to create and manipulate tables like books and categories. We discussed the importance of querying data, using join statements to enhance our results, and maintaining data integrity with various constraints. Finally, we highlighted the power of data analysis in PostgreSQL, emphasizing how these skills can aid in deriving meaningful insights from data. Now, we will delve deeper into the relational data model, understanding how it operates and why it's crucial for effective data management. We'll uncover its components and see how they interconnect, allowing us to manage our data intelligently. Ready? Let's get started. Now let's implement a command to create our employees table, shall we? The SQL statement we're using will establish an employees table with several crucial attributes. First, we're going to define the employee ID column, which is of type serial and designated as the primary key. This step is really important because it ensures that each employee record gets a unique identifier automatically generated by the database. That's essential for maintaining our data integrity. Next up, we'll focus on the name column, where we specify varchar 100 as the data type. This allows us to store variable-length character strings, so we can keep employee names up to 100 characters long. Following that, we define the department column using varchar 50, giving us ample space for department names. Now, as for the salary column, we'll define it as decimal 10-2 to accurately represent monetary values, including 2 decimal places for cents. By structuring our table this way, we create a clear and concise schema that makes data management and retrieval easy. Now, with this foundation in place, we can smoothly move on to inserting, querying, and manipulating employee data effectively. Now, let's dive into implementing the code to create the departments table and establish a relationship with the employees table using a foreign key. First up, we're creating the departments table, and within it, we defined a department ID as a serial primary key. This is super handy because it allows the database to automatically generate a unique identifier for each department, ensuring that each record is accessible individually and, crucially, without duplication. Next, we're going to modify the employees table by adding a new column called Department ID. This column will serve as the foreign key reference that corresponds directly to the department ID in our departments table. By doing this, we're linking employees to their respective departments. It's like connecting the dots. Now, here's the important part. The foreign key constraint ensures that any entry in the department ID column of the employees table must match an existing department ID in the departments table. This is crucial because it enforces relational integrity. With this solid structure in place, we can perform more complex queries. Imagine the insights we can gain by merging data from both tables, such as discovering which employees belong to which departments. Isn't that fascinating? Now that we have our foundational tables established, let's see how we can insert data into these tables. We begin with the Insert Into statement for the Departments table, which allows us to add multiple department names in one go. By specifying the column Department Name, we ensure that each department we list, Human Resources, Engineering, and Marketing, is accurately captured in our database. This structured approach not only populates our departments table, but also sets the stage for linking employees to these departments. Next, we move on to inserting records into the Employees table. Here, we specify the columns for Name, Department ID, and Salary. Each employee is associated with a particular department through the Department ID field, which links back to the corresponding department in the Departments table. This relational aspect is crucial as it allows us to maintain organization and keep track of which employees belong to which departments. With this insertion, we effectively create a foundation for the ongoing data management tasks that will follow. Next, we will write the following SQL statement to retrieve valuable information from our relational database. This code utilizes the join operation, which is essential for combining data from different tables based on shared attributes, specifically the department ID. By selecting employees.name, departments.departmentName, and employee salary, we are creating a comprehensive view of our workforce, linking each employee to their respective department. The From clause specifies that we are pulling data from the Employees table, while the Join clause seamlessly merges the Departments table. The On condition establishes the relationship between the two tables, ensuring that we only return rows where the Department ID matches between the linked tables. This method allows us to generate insightful results, facilitating data analysis and reporting. Now the output of this query will yield a list that not only names the employees, but also presents their corresponding departments and salaries, giving us a clearer understanding of the organizational structure. The displayed figure is a bar chart titled Employee Distribution Across Departments, and it shows the number of employees across 5 key departments. Human Resources has 15 employees, Engineering leads with 30, Marketing hosts 20, Sales contributes 25, and IT rounds out the group with 10. Each bar is clearly labeled with its exact value, and when you add them all up, you find a total of 100 employees. Now, interpreting this chart, it becomes clear that engineering is the largest department, representing 30% of the workforce. Meanwhile, if we look at sales and marketing together, they account for a significant 45%, with sales at 25% and marketing at 20%. Human resources takes up 15% and, unfortunately, is the smallest department at just 10%. So, what do these numbers tell us? Well, we can see a strong concentration of staff in engineering and a notable combined presence in the customer and product-facing functions like sales and marketing. Conversely, the IT and HR departments show relatively low staffing levels. From these counts, one can conclude that this organization's workforce is skewed toward engineering roles and those that drive revenue generation, while support functions have a smaller footprint. These proportions are not just interesting to note, they're directly visible and can actually guide resource allocation decisions, help with capacity planning, and even inform targeted queries or aggregations when analyzing headcount across departments. Now, let's see how we can enforce essential data integrity rules in our employees table using constraints. The first part of the statement alters the structure of the table, specifically adjusting the name and salary columns to ensure that neither can hold a null value. By applying the not null constraint, we make sure that every employee record requires a valid name and salary, which are critical attributes for maintaining accurate employee information. Additionally, we introduce a unique constraint on the name column. This prevents duplicate entries of employee names within our table, ensuring that each employee can be uniquely identified by their name. Which really enhances the reliability of our dataset. Together, these constraints help uphold the quality of data, preventing inconsistencies and errors that could arise from null values or duplicate names. By implementing these changes, we're creating a more robust framework for our employee data, thereby supporting better query results and overall data integrity across the board. Now, let's dive into how we can implement an index to optimize data retrieval in our employees table. We're going to use a command that creates an index named IDX salary on the salary column of the employees table. Now, why are indexes so important? Well, they play a crucial role in enhancing the performance of frequently executed queries, especially when we're dealing with large data sets. By placing an index on the salary column, we enable the database to locate employees based on their salary much more quickly than if it had to scan the entire table for each query. However, it's also important to consider that while indexes significantly speed up read operations and improve query response times, they do come with additional storage requirements and maintenance overhead. So we really want to be strategic about which columns we choose to index based on usage patterns. In this case, indexing the salary column makes a lot of sense, particularly if salary-based queries are common. This way, we can ensure maximum efficiency in how our database responds to such requests. Now, let's dive into computing some really important analytical metrics using SQL aggregate functions. So, in the query we're looking at today, our goal is to find out the average salary of employees for each department. And why is this important? Well, it helps us understand how salaries are distributed across the entire organization. We're going to start by selecting the department name from the Departments table. Then we'll apply the AVG function to the salary column from the Employees table. The AVG function calculates the mean salary for our dataset, giving us a clearer picture of compensation within the different departments. To make this analysis even more insightful, we'll join the Employees table with the Departments table on the Department ID. This is where we establish a connection based on the foreign key, ensuring we accurately pair employees with their respective departments. Finally, we'll group the results using the Group By clause applied to the department name. This means that the average salary will be calculated for each unique department, resulting in a comprehensive summary of how each department compensates its employees. This aggregation technique can really uncover valuable insights for HR and management, enabling them to make well-informed decisions regarding salaries and budgeting. Now, let's see how we can update an employee's salary using SQL. The update statement is a powerful command that allows us to modify existing records in our database. In our example, we are updating the salary of an employee named John Doe to $70,000. This operation is essential in maintaining accurate and relevant data, especially when circumstances such as pay raises occur. The set clause specifies the new value for the salary attribute, while the where clause ensures that only the record corresponding to John Doe is affected. This precision is crucial in a database as it prevents unintended changes to other records. Next, we'll write a command to remove an employee's record from the database. Using the delete statement, we can proactively manage our dataset by eliminating records that are no longer necessary, such as when an employee leaves the organization. In this case, we are removing the record for Emily Davis from the employees table. The simplicity of this command highlights SQL's effectiveness in data management, allowing for straightforward updates and deletions to keep our dataset aligned with real-world conditions. Now, let's see how we can enhance our existing employees table by adding some essential contact information. To achieve this, we'll be using the alter table statement, which allows us to modify the structure of an existing table without losing any of the data already stored in it. In this instance, we'll add two new columns, email and phone. The email column will be of type varchar 100, meaning it can store strings of up to 100 characters. That's plenty of space for most email addresses. The phone column, on the other hand, is defined as varchar 15 to hold typical phone numbers, ensuring that we can capture various formats without running into limitations. This command perfectly exemplifies the flexibility of relational databases, allowing us to adapt our data structure as business requirements evolve. By integrating new attributes like contact information, we're enhancing our database's utility and providing a more comprehensive view of each employee. Through this approach, we're ensuring that our database remains a dynamic tool for managing valuable information efficiently and effectively. As we wrap up our exploration of the relational data model, it's become clear that this structure offers a highly efficient framework for organizing, manipulating, and analyzing data. With a solid grasp of how tables, keys, and constraints work together, and the powerful capabilities that come with SQL, you're truly equipped to tap into the potential of relational databases. Now, remember, mastering SQL isn't just about memorizing syntax. It's about learning to think in terms of data structures and relationships. As you keep practicing and applying these concepts, you'll find that the relational data model serves as an invaluable foundation for building data-driven applications and systems. So I encourage you to embrace this knowledge. Keep experimenting, and before long, you'll be navigating the complexities of databases like a seasoned pro. Happy querying! Nosql databases have emerged as a robust alternative to traditional SQL databases, catering to the evolving needs of modern applications that require scalable, flexible, and schemaless data storage solutions. Today, we're going to explore the document data model in Nosql databases, diving into its structure, benefits, and practical applications. So far, we've learned about the relational data model, focusing on the structured organization through tables, the importance of primary and foreign keys, and how constraints and indexing enhance data quality and performance. Now, we'll cover the document data model, its advantages over relational models, and how to interact with it using popular NoSQL databases like MongoDB. You see, the document data model allows us to store data in a more intuitive way, organizing information in documents that can contain complex structures, making it particularly effective for applications requiring unstructured or semi-structured data. These documents can hold nested data and arrays, which means you can manage sophisticated relationships without overwhelming complexity. And the best part? You don't have to define a rigid schema up front. Instead, you can adapt your data structure as your application evolves, providing significant flexibility. So, let's dig deeper into how we interact with this model in MongoDB. It's really intuitive, so let's get started. Now, let's take a look at how we can represent a user profile in a NoSQL database using the document data model. In this example, we have a user document that captures various attributes, which gives us a complete view of the user in a single entity. The document begins with a unique identifier, user ID. And, this is really essential for distinguishing this user from all the others. Next, we include key information like the user's name and email, which shows just how easily we can store different data types, such as strings. Now, also noteworthy is the Preferences section. This part includes Booleans that indicate the user's choices regarding newsletters and notifications. This allows for really quick access to a user's settings, you see. Unlike in relational databases, there's no need for complex joins here. The Addresses field is an array that showcases the document's ability to contain nested objects. In there, we define multiple address types along with their respective details. This structure really highlights the flexibility of the document data model. It enables developers to evolve and modify the document as application needs change, ultimately enhancing the user experience and simplifying data management. Isn't that neat? One of the most significant advantages of the document data model is its scalability. As applications grow, they often demand more data, and this is where NoSQL databases shine. They can handle high volumes of unstructured data without experiencing performance hiccups. This strength stems from their ability to distribute data across multiple servers seamlessly. So, when you need to scale your application, you can simply add more servers to your NoSQL cluster, which makes it really straightforward to accommodate increased workloads. Isn't that just fantastic? The displayed bar chart, titled Application Areas Leveraging the Document Data Model in NoSQL, presents 5 application areas with their respective data handling percentages. E-commerce at 30%, content management at 25%, social media at 20%, analytics at 15%, and gaming at 10%. Now, let's take a closer look at what this means. You can see, right from the left to the right, there's a very clear descending pattern, indicating that e-commerce is, by far, the largest single area leveraging the document model. It's closely followed by content management and social media. Together, these top 3 categories, make up a whopping 75% of the total distribution. This strong concentration highlights how these applications are really focusing on content and documents. Now, when we do see those lower percentages for analytics at 15% and gaming at 10%, it seems to suggest more specialized or smaller scale adoption in those sectors. So, what can we conclude from all this? Well, the document data model is primarily being utilized in applications that demand flexible, nested document structures and frequent updates, the majority of which are focused on customer-facing and content-oriented systems. It's really fascinating to notice how the landscape of data management is shifting towards these needs, reflecting broader trends in technology and user interaction. Now, let's see how we can insert multiple user profiles into our application using MongoDB's document data model. The code employs the InsertMany method to efficiently add multiple documents to the user's collection in a single operation. Each document represents a user's profile, containing fields like user ID, name, email, and, get this, nested objects for preferences and addresses. By structuring user data this way, we really leverage the flexibility of the document data model. It allows us to adjust profiles easily without being stuck with a rigid schema. For example, the Preferences object can include booleans that indicate whether a user is subscribed to newsletters and notifications, while the Addresses array can hold one or more addresses representing all the physical locations a user might have. This method not only simplifies data insertion, but also boosts performance when we're working with large data sets, which is a key advantage of NoSQL databases. With the ability to insert multiple user documents effortlessly, developers can manage vast amounts of user data with quick commands. That really caters perfectly to modern application needs where scalability and rapid access are absolutely critical. Now, let's see how we can represent different products using the document data model. In our first example, we're going to define a document for a pair of wireless headphones. This document has fields such as product ID, name, and brand, which tell us the product's unique identifier, its name, and its brand respectively. But wait, there's more. It also includes a nested object called specifications. This helps us organize specific details about the product, like battery life and warranty. You see, this structure really highlights the flexibility of the document data model. By using those nested objects, we can easily group related attributes together. All right, moving on, let's write the next document for a cotton t-shirt. Now here, the structure varies, and that illustrates the schema-less nature of the document data model quite nicely. This document features fields like size and color, showcasing how different products can have unique attributes relevant to their type. How cool is that? By using this approach, we can accommodate various product details without being constrained by a rigid schema. And that makes it so much easier to manage diverse data sets. This adaptability, folks, is a key strength of NoSQL databases, allowing developers to create dynamic and relevant representations of their data. Now, let's dive into filtering our users based on their preferences. Specifically, we're looking to find those who have opted in for a newsletter. We can achieve this using the find method available in MongoDB, which lets us directly query the user's collection. In our query, we're going to specify a condition to target the preferences field within each user document. By utilizing dot notation, we'll check the subfield newsletter and set its value to true. This way, we're able to retrieve only those user documents where the newsletter preference is indeed enabled. Now, here's where it gets really interesting. The beauty of this querying capability lies in its intuitive syntax, kind of like accessing properties of JavaScript objects. So, it makes it super easy for developers to search for specific data without all the complexity involved in joining tables, as you would with traditional SQL databases. Whoa! Plus, as users update their preferences, those changes are reflected immediately in the corresponding document. This not only simplifies data management, but also ensures that our application is always working with the most up-to-date information. Now, let's dive into optimizing our queries in MongoDB by creating an index. So, using the command db.users.createIndex, email1, we're essentially telling MongoDB, hey, create an index on the email field within the users collection. This nifty little index helps speed up search operations that filter by the email attribute. Now picture this. When you query the database for user information based on email, MongoDB can zoom in and quickly identify the relevant documents. This dramatically enhances performance, especially when you're working with collections that have a ton of entries. But it's essential to understand that while indexes are super powerful tools for improving query efficiency, they do come with some trade-offs. For instance, they introduce additional storage overhead and might impact write operations since the index needs updating whenever the data changes. So it's really crucial to implement indexes strategically. This helps balance those performance gains with resource usage and keeps your application responsive. Regular monitoring and careful planning of your indexes can really help ensure your application remains efficient and scalable, especially as your data grows. Now, let's take a look at how we can represent a blog post with its associated comments using the document data model. In our example, we define a JSON document for a blog post, which includes a unique identifier, a title, and an array of comments. Each comment itself is structured as a separate object, containing the user who commented, the content of the comment, and the date it was made. By embedding the comments directly within the post document, we create a one-to-few relationship that is efficient and easy to manage. This approach allows us to retrieve a post along with its comments in a single query, enhancing performance and reducing the complexity of our data retrieval operations. As the number of comments is likely to be limited for a single post, you'll find that embedding is the optimal strategy here. This encapsulated structure not only keeps related data together, but also aligns well with the flexibility offered by NoSQL databases. Now, in scenarios where we anticipate a large number of comments or a more complex relationship, we could alternatively consider using references for a cleaner, more scalable solution. This allows for greater adaptability as our application grows.
As we reflect on the document data model, it's really important to acknowledge the balance between flexibility and complexity. You see, the freedom to structure documents in ways that best fit application needs can lead to powerful designs, but it also requires careful consideration. For instance, you definitely want to avoid deeply nested structures unless it's absolutely necessary, as this can really complicate your queries and updates. To help visualize this, let's think of it like building with Lego blocks. Each block can be created in different shapes and sizes, just like our documents. However, if you stack them too high without a solid base, meaning too many nested fields, your entire structure might just tumble down when you try to change one piece. Now, let's not forget about performance testing and monitoring. These should be integral parts of using NoSQL databases. Since they scale horizontally, the dynamics of application performance can change, especially as more nodes are added to the cluster and the amount of data grows. So keeping an eye on these factors is crucial for maintaining efficiency and stability in your applications.
To sum up, the document data model in NoSQL databases really represents a significant shift in how we manage and interact with data. Its flexibility, scalability, and robust querying capabilities make it an excellent choice for various applications, especially those that deal with evolving data structures. Now, throughout our journey in the world of NoSQL, we've explored how to create and manipulate documents, understand relationships, and enhance performance while keeping a keen eye on data integrity. And with this knowledge, you now have a solid foundation to harness the power of document data models in your applications effectively. So, embrace this shift, experiment with case studies, and leverage the flexibility of NoSQL databases to propel your development capabilities into the future. NoSQL databases have revolutionized the way we manage data in contemporary applications, offering flexible alternatives to traditional SQL databases. Each of these options brings its own unique advantages and disadvantages. So today, we'll explore these aspects to better understand where NoSQL really shines and, well, where it might fall short. So far, we've learned about NoSQL databases as this flexible alternative to the more traditional SQL setup, specifically focusing on the document data model, which uses JSON-like documents for dynamic data representation. We've also covered its scalability, its ability to handle diverse data structures, and some practical examples, like managing user profiles and product details. This document data model allows for complex data interactions without the usual constraints of fixed schemas, and indexing, well, that really optimizes performance. Ultimately, NoSQL offers a powerful approach to data management, enhancing innovation and adaptability for modern applications. Now, let's dive into the advantages and disadvantages of NoSQL databases. Now, let's see how we can efficiently insert multiple user profiles into a MongoDB database. The provided code demonstrates the use of the insert many function, which allows us to insert multiple documents into the user's collection in a single operation. In this example, we start by specifying an array of user objects, each with a unique user ID and name. This approach really highlights the flexibility of NoSQL databases because, unlike traditional databases, we don't need a predefined schema to dictate how our data should be structured. So, what does that mean for us? Well, it means we can easily add new users with varying attributes down the line, without having to deal with complex alterations to the database structure. Now, when we execute this command, MongoDB takes care of the insertion behind the scenes, ensuring that each user document is stored correctly. It's a method that's not only straightforward, but also super efficient, particularly when we're dealing with large volumes of data that need to be processed quickly, like when applications suddenly experience a spike in user activity. Overall, this code snippet really showcases the rapid and dynamic capabilities of NoSQL databases in managing user data seamlessly. Now, if we take a closer look, the top 4 bars, scalability at a whopping 90%, flexibility at 85%, high availability at 80%, and performance at 75%, are not just longer. They're also highlighted in one vibrant color. This clearly emphasizes that these attributes, well, they're scored really high and represent the core strengths of NoSQL systems. In contrast, the bottom 3 bars, showing lack of standardization at 40%, limited transaction support at 35%, and maturity and ecosystem at 30%, are noticeably shorter and displayed in a different color. This choice makes it crystal clear that these are the primary weaknesses. You can see that the visual ordering really makes the trade-offs explicit. There's a steep drop from those impressive performance-related strengths, hovering between 75 and 90%, down to the ecosystem and transactional limitations, which sit around 30 to 40%. So, what does this tell us? Well, it indicates that while NoSQL shines at scaling, flexibility, availability, and raw performance, it definitely tends to lag behind in standardization, transactional guarantees, and mature tooling. Now, the percentage labels at the end of each bar quantify these gaps, and they support the conclusion that, for use cases prioritizing scalability and flexible schemas, the advantages numerically outweigh the disadvantages. However, if you're working on applications that require strong transactions or standardized tooling, you'll definitely want to weigh those lower-scored categories carefully before diving in. Now, let's explore how we can represent an article in a NoSQL database using a JSON-like format. In this example, we're going to define a document that encapsulates all the essential details about an article, including its unique identifier, title, author, content, and associated tags. Each element in this structure really highlights the flexibility of NoSQL databases. The article ID serves as a primary key that uniquely identifies the article, while the title and author fields provide this structured metadata that can be easily queried. Now, the content field is where the magic happens. It allows for unstructured text, showcasing the NoSQL model's strength in handling diverse data types. Additionally, the tags array demonstrates how we can use the document model to group related keywords, enhancing our search capabilities. This approach allows for seamless modifications. If we find ourselves needing new metadata or content types in the future, we can simply add them without getting bogged down in complex migrations. It makes this structure so highly adaptable. Overall, this representation illustrates the power and convenience of using NoSQL databases for dynamic content management systems, where data can evolve along with the application itself. Now, let's see how we can retrieve an article from a MongoDB database efficiently. The code executes a query using the find_one method on the articles collection, specifically searching for an article with a unique identifier, article_ID, set to A001. This simple query is significant because it highlights the intuitive nature of NoSQL databases, allowing us to access precisely what we need without the complexities often associated with SQL databases, like intricate joins. By leveraging this straightforward syntax, developers can quickly obtain the relevant document, which not only improves retrieval speed, but also boosts productivity, since there's no need to define relationships through tables or worry about those pesky schema constraints you find in traditional SQL environments. This feature becomes particularly advantageous when managing hierarchical or nested data structures. It really allows for fast and flexible access to varied data types stored together in a single document. In summary, the ease of querying in NoSQL, especially through this MongoDB example, exemplifies one of the platform's major advantages, simplifying data interactions significantly. Now, let's take a look at a scenario in which user actions might lead to data inconsistency in a NoSQL database due to the eventual consistency model. So, in this example, user Alice adds an item to her shopping cart, which shows us how data gets updated in a NoSQL environment. Now, while this operation is happening, the update command is executed to ensure that item 123 is added to Alice's cart. However, due to this eventual consistency thing, there might be a little delay before other users, like user Bob, see that change reflected in their views of the data. Next, let's consider how user Bob queries Alice's shopping cart right after she adds that item. He retrieves that cart using a find operation, but here's the catch. There might be a lapse where Bob sees a version that does not show Alice's recent addition. This inconsistency really highlights the challenges developers face in NoSQL systems, where immediate data visibility isn't guaranteed. It's super important then to understand the use case and what levels of consistency are acceptable for different applications. Now, let's dive into how to manually back up a MongoDB collection, which is a crucial step for any NoSQL database management strategy. We're going to use a command that leverages MongoDump, a handy utility designed explicitly for creating backups of Mongo databases. So, to get started, we specify the database name with the -db option and input mydb, which, by the way, is the database we're aiming to back up. Now, the -out option is essential here. It directs the output to a specified folder on the server. In our case, it's set to -backup/mdb backup. Just imagine that folder as your safe deposit box, where all backup files will be stored, making it easy to access them when needed. By executing this command, you're essentially taking a snapshot of all the data in the specified database right at that moment. This manual backup method, while quite straightforward, underscores a vital aspect of NoSQL database management, the heavy reliance on command-line tools for these important administrative tasks. Unlike many traditional SQL systems, which often showcase user-friendly graphical interfaces for operations, get ready for a little more hands-on coding here. So it's super critical to incorporate these practices into your workflow to ensure the safety and integrity of your data in your applications. Now, let's take a look at how we can model user data in a social network application using NoSQL, specifically within a document-oriented database like MongoDB. In our example, we represent a user as a JSON-like document that captures essential information, such as the user's unique ID and their name. Additionally, we include an array of friends, where each friend is also represented by a document that holds their own user ID and name. This structure allows for efficient retrieval, since we can quickly access a user's information along with their network of friends in a single query. However, while this model certainly provides advantages in terms of speed and ease of access, it also necessitates careful consideration when it comes to data updates. For example, if a user changes their friends list, those changes need to be reflected across all relevant documents, which could lead to data duplication and more complex operations. This highlights the importance of understanding how to strike a balance between performance and data consistency in NoSQL data modeling. Next, we will write a SQL-style transaction to demonstrate how data handling differs between traditional SQL databases and NoSQL systems. In SQL, transactions are really important for ensuring data integrity and consistency. So let's jump right in with a begin statement, which signals the start of a series of operations that should be treated as one complete unit. Now, we'll execute an insert command to add a new user to the users table, where we will specify the user's ID and name. This straightforward approach allows developers to ensure that the user data is added consistently, as no other changes can occur until this transaction is either committed or rolled back. Following up with a commit statement finalizes the transaction and applies those changes to the database. This example illustrates the relational model's strength in managing transactional data, which stands in stark contrast to NoSQL's approach, where transaction guarantees may not always be as robust. Understanding this transactional flow is crucial for developers transitioning from SQL to NoSQL, because they'll need to adapt to different concurrency controls and data management strategies in a NoSQL environment. To summarize, NoSQL databases come with a bunch of exciting advantages, like horizontal scalability, flexible data handling, and user-friendly querying capabilities. This makes them super well-suited for a wide range of modern applications. But of course, it's important to balance these pros with some of the cons, such as eventual consistency issues, limited tooling options, and the complexities of data modeling and learning curves. So, getting a grip on both the upsides and the downsides is key. It helps you make informed decisions on whether to dive into NoSQL technologies for your projects. By familiarizing yourself with these trade-offs, you'll be better equipped to innovate in the fast-changing world of data management. With all this knowledge, you're now ready to explore practical applications of NoSQL databases as you embark on your development journeys.
The CAP theorem is a pivotal principle in the domain of distributed systems and NoSQL database design. It's crucial for understanding how these systems operate, particularly when it comes to making trade-offs between consistency, availability, and partition tolerance. So far, we have explored the fundamental aspects of NoSQL databases, focusing on their scalability and advantages over traditional SQL databases. NoSQL designs prioritize dynamic data management and the need for flexibility. Moving forward, we will dive into the CAP theorem, discussing how it influences NoSQL architecture and decision-making. The CAP theorem, articulated by Eric Brewer in the early 2000s, states that in the presence of network partitions, a distributed system can provide only two of the following three guarantees: consistency, availability, and partition tolerance. Each of these elements plays a crucial role in determining how a NoSQL database operates under various conditions. To break it down, consistency ensures that all nodes see the same data at the same time. For example, when a write operation occurs, that data should be immediately visible to all nodes in the system. Availability guarantees that every request results in a response, either with the requested data or an error message. Even during failures or network partitions, the system continues to operate and serve requests. Partition tolerance means that the system continues to function despite communication failures between the nodes. It can handle situations where some nodes cannot communicate with others without compromising overall system functionality. The displayed bar chart titled Key Concepts of the CAP Theorem in NoSQL Design quantifies the relative emphasis placed on each CAP dimension: consistency 70%, availability 80%, and partition tolerance 90%. On the x-axis, the three key concepts are labeled, while the y-axis shows an importance level percent with numeric tick marks and values. Each bar is color-coded: consistency in green, availability in blue, and partition tolerance in amber, and numeric labels appear above each bar indicating their exact percentage values. The pattern is clear. Partition tolerance is shown as the highest priority, 90%, availability follows closely, 80%, and consistency is somewhat lower, 70%. From these visual values, we can conclude that in typical NoSQL design considerations, systems tend to prioritize surviving network partitions first, then keeping services available, while accepting that strict immediate consistency may be relaxed. The relative gaps between the bars suggest that while consistency remains significant, architects often trade some immediacy of consistency to ensure the system remains partition tolerant and highly available in distributed environments. Now let's implement a simple session storage operation in Apache Cassandra that aligns with our discussion of the CAP theorem. In the provided Python code, we create a function called storeSession, which is designed to connect to a Cassandra cluster and store user session data in the specified key space. First, we initiate a connection to our Cassandra cluster by specifying the IP address of the node, which in this case is set to 127.0.0.1. Once connected, we access the session key space where our user session data will be stored. The heart of the operation is the insert statement that constructs a query to add new user session data into the user sessions table, using the provided userid and session data. After formulating the query, we execute it using the session connection, ensuring that the session data is stored in the database. A success message is printed to confirm the operation was completed successfully. It is essential to recognize that in a real-world scenario, especially during periods of high traffic or if some nodes are down, this system illustrates the trade-offs of availability where data consistency might not be immediate, leading to potential stale reads until all nodes are synchronized. Now let's see how we can implement a simple order placement system using MongoDB. This code connects to a MongoDB instance running locally and specifies the database and collection that will be used for storing order transactions. The placeOrder function takes two parameters, orderid and order_details, which represent the unique identifier for the order and the specific details about the order, respectively. Inside the function, we first establish a connection to the MongoDB server through the Mongo client. After connecting, we access the orders.db database and the orders collection where our orders will be stored. Next, we construct an order document in the form of a dictionary containing the order ID and details. To ensure consistency, the code inserts this order document into the collection using the insert_one method, which triggers an acknowledgement from the primary node before confirming the operation. If successful, a message is displayed to inform us that the order has been placed. This approach aligns with MongoDB's primary-secondary replication settings, emphasizing consistency, even at the cost of availability during primary node failures. Now let's implement a function to save user profile information in Amazon DynamoDB, showcasing its eventual consistency and high availability features. The first step in the code involves importing the Bodo3 library, which is the official Oz SDK for Python. This library allows us to interact with various AWS services, including DynamoDB. Next, we define a function named saveProfile that takes two parameters, username and profile data. Inside this function, we initiate a connection to DynamoDB by creating a resource for the service. We specify the DynamoDB table we will be using, which in this case is named userProfiles. The key operation here is the putItem method that we call on the table object. This method is responsible for saving the user's profile data specified in the parameters. The data is stored in a dictionary format where the keys are username and profile data. After executing this command, the function prints a success message, confirming that the profile has been saved. In this coding scenario, users understand that while their profile changes may not appear instantly across all nodes in the database, the system remains responsive and functional, illustrating DynamoDB's balance between availability and partition tolerance. Now let's shift our focus to the strategic decisions that developers and database architects must make when designing a NoSQL database system based on the CAP theorem. Choosing between consistency and availability involves understanding the application's specific use case and the user experience you are designing for. For instance, in a social media application, keeping the platform available and responsive is crucial. Users expect to post updates, comment, and like posts without delays. Therefore, it might be acceptable for users to see slightly outdated information if it means the application remains snappy and operational. In such a case, adopting a NoSQL solution that leans towards availability would be prudent. Conversely, in banking applications where consistency is paramount, it's critical to ensure that every transaction is accurate, leaving no room for stale data that could lead to incorrect balances or record discrepancies. Hence, a more consistency-focused database configuration would be necessary. Now let's implement the following function to handle payment submissions using Couchbase. This code connects to a Couchbase cluster instance located at localhost using the designated username and password for authentication. It specifically targets a bucket named Payments Bucket where payment transaction documents will be stored. In our defined function, submitPayment, we prepare a payment document that includes the user ID and the payment amount. This document serves as the backbone of our transaction data. To ensure the utmost reliability, we utilize the upsert method, which updates the document if it exists or creates a new one if it doesn't. In addition, we specify durability options to ensure that the payment document is saved across a majority of nodes in the cluster, thereby enhancing data safety, especially during network partitions. By employing this robust method, we can be confident that the payment processes adhere to strong consistency rules, essential for financial transactions. With this implementation, when the payment is submitted, users receive immediate confirmation, ensuring a seamless experience while maintaining data integrity across the distributed database system. This mixture of strategies enables developers to create resilient applications tailored to their requirements. By leveraging the CAP theorem, architects can decide which trade-offs best suit their application's functionality. Understanding these decisions ultimately leads to the successful implementation of the NoSQL databases that will power modern applications. In conclusion, the CAP theorem significantly influences the way we design and implement NoSQL databases. By weighing the importance of consistency, availability, and partition tolerance, developers can tailor NoSQL architectures to fit their application needs. We've seen practical examples across various databases, demonstrating how each employs different strategies to align with the principles of the CAP theorem. Now that you have a fundamental understanding of the CAP theorem and how to apply these concepts in NoSQL design, you can approach your distributed system projects with greater confidence, knowing how to navigate these crucial decisions. So far, we've covered the foundational aspects of NoSQL databases and the influential CAP theorem. Moving forward, we'll delve into specific NoSQL database implementations, examining their unique features and real-world applications while maintaining an emphasis on performance, scalability, and reliability. Prepare yourselves as we continue this exciting journey into the world of distributed databases. Transaction management and concurrency control are vital components of database systems that protect data integrity in multi-user environments. Today, we will delve into transaction management methods in NoSQL databases, exploring how they differ from traditional relational databases and examining their importance in maintaining data consistency. So far, we learned that the CAP theorem outlines crucial trade-offs among consistency, availability, and partition tolerance in distributed systems, particularly for NoSQL databases. We discussed how designs prioritize these elements differently based on application needs, illustrated through examples like Apache Cassandra, MongoDB, and DynamoDB. These considerations guide developers in selecting appropriate strategies for specific use cases, enhancing system resilience while accommodating necessary performance metrics. Next, we will explore unique implementations of various NoSQL databases and their real-world applications. The displayed bar chart titled Transaction Management Methods in NoSQL Databases shows 4 methods and their importance levels as percentages. Eventual consistency, 75%, acid compliance, 60%, optimistic concurrency, 70%, and lightweight transactions, 80%. Key patterns are immediately visible. Lightweight transactions have the highest importance, 80%, followed by eventual consistency, 75%, and optimistic concurrency, 70%, with ACID compliance rated lowest at 60%. The annotated values above each bar provide precise comparisons and reveal a 20-point spread between the least and most emphasized methods, 60% to 80%, indicating a moderate variance rather than extreme divergence. From these values, we can conclude that NoSQL practices tend to favor mechanisms that support scalable, low-latency operations, lightweight transactions, and eventual consistency, while still placing meaningful emphasis on optimistic concurrency for conflict handling. Strict ACID compliance is comparatively de-emphasized but not ignored. This distribution aligns with the earlier CAP-based discussion. Systems often choose higher availability and scalability while applying stronger transactional guarantees selectively when application requirements demand them. Now let's implement the following function for transferring funds between two users in a MongoDB database. We first establish a connection to the MongoDB server using the Mongo client and target the appropriate database labeled banking. By creating a session, we can manage a multi-document transaction, which is crucial for ensuring both balance updates occur together without partial application. Inside our transaction, we fetch the sender's and receiver's current balances. If the sender has sufficient funds, we proceed with two update operations to deduct the amount from the sender's account and credit it to the receiver's account within the same transaction session. A successful completion of these operations leads to committing the transaction, ensuring the changes are applied as intended. If the sender lacks the necessary funds, we abort the transaction to prevent any inconsistency. In case of errors, such as a connection failure, we catch exceptions and also abort the transaction, safeguarding the integrity of our data. Finally, we ensure our session is properly closed regardless of the outcome, maintaining good resource management. This transaction management in MongoDB showcases how modern NoSQL databases facilitate robust data integrity while providing performance benefits. Now let's see how we can implement a function to place an order in DynamoDB using the Bodo3 library. The function, placeOrder, takes three parameters, userid, orderid, and order data. First, we establish a connection to the DynamoDB service and specify the orders table where we will store our order data. Inside a try block, we call the putItem method on the orders table, where we define the item we want to store in the table. This item includes the order ID, user ID, and order data. A key feature of this implementation is the condition expression, which ensures that an order can only be inserted if it does not already exist in the database. If an order with the same ID already exists, the transaction will trigger an exception. In the event of a successful insertion, the function confirms the order placement with a printed message. However, if an exception occurs, such as an attempt to place a duplicate order, the function catches the error and displays a failure message. This demonstrates DynamoDB's eventual consistency model, allowing for quick acknowledgements while maintaining the integrity of the order data. Now let's see how we can implement a lightweight transaction to update user profiles in Cassandra. First, we establish a connection to the Cassandra database by creating a cluster instance that points to the server's IP address. With the session object, we connect to the specific key space, in this case, user profiles, where our user data is stored. Next, we formulate an update query using the simple statement class. This query modifies the user's profile data but includes an important condition, the if exists clause. This ensures that the update only happens if the specified user exists, thus preventing issues related to stale or non-existent data. After preparing the query, we execute it against the session. The result object returned from the execution tells us whether the operation was successful. We use the wasApplied attribute to check if the update was actually applied. If so, we notify the user of a successful update. Otherwise, we inform them that the update failed due to the user not existing in the database. This approach emphasizes maintaining data integrity and avoiding inconsistencies in a multi-user environment, showcasing the power of lightweight transactions in Cassandra. Now let's see how we can implement optimistic concurrency control in Couchbase to update a user profile. First, we establish a connection to the Couchbase cluster using the appropriate cluster options and credentials. This connection allows us to access the specific bucket called user profiles to interact with user documents. We begin by retrieving the existing user document with a unique identifier, userid, which provides us with the current user details. Once we have this document, we prepare the new profile data by merging it with any updates contained in the new data parameter, ensuring we retain existing information while incorporating new changes. Next, we attempt to upsert the new profile data back into the collection. This operation is crucial as it allows us to update existing records or insert new ones if they don't exist. If the operation completes successfully, we print a confirmation message. However, to handle potential conflicts, we wrap this call in a try-except block. If a document not found exception occurs indicating a conflict, we catch the error and inform the user. This code elegantly demonstrates the use of optimistic concurrency control by allowing concurrent reads while ensuring that updates are safely managed. It's essential to recognize that while NoSQL databases do provide flexible transaction management options, the responsibility often leans on developers to implement robust concurrency controls and mitigate potential issues. Transaction management in NoSQL requires thoughtful design decisions based on the specific needs and constraints of your application. The trade-offs become particularly evident in distributed database systems where data consistency and availability must be balanced. Developers often find themselves asking, is immediate consistency essential for my application, or can I afford eventual consistency? This will guide whether to leverage lighter transactional mechanisms or adopt stronger guarantees as needed. Thus, in the realm of NoSQL databases, transaction management varies significantly from traditional SQL paradigms, offering flexibility at the cost of strict compliance to ACID principles. By implementing optimistic concurrency controls and lightweight transactions, developers can ensure data integrity while maintaining the high performance and availability features that define NoSQL architectures. In closing, we have covered an array of transaction management methods in NoSQL, exploring how these methods differ significantly from traditional SQL databases. Understanding these differences allows developers to make informed choices and design resilient applications that appropriately balance data integrity and performance. We've looked at exciting examples, from MongoDB's multi-document transactions to DynamoDB's eventual consistency, and even Cassandra's lightweight transactions. As we move forward, keep these concepts in mind as we prepare to explore further real-world applications of NoSQL databases and their numerous capabilities. Whether it's building robust applications or system architectures, having a sound understanding of transaction management in NoSQL sets a strong foundation for success. Now let's see how we can implement a basic user profile creation function using MongoDB in Python. The script begins by importing the necessary Mongo client from the PyMongo module, which allows us to interact with the MongoDB server. We define a function named createUserProfile, which takes three parameters: userid, username, and email. Within the function, we create a client instance that connects to the MongoDB server running on our local machine. We specify the database we want to use, in this case, user profiles, and then we access the profiles collection where user data will be stored. Next, we use the insert1 method to add a new document to the collection, encapsulating the user's information in a dictionary format. This method easily allows us to insert the user's ID, name, and email into the database. Finally, we conclude by printing a confirmation message indicating that the user profile was successfully created. This simplicity in the code illustrates the ease of inserting data into a NoSQL database, aligning perfectly with the scalability advantages we discussed previously. Figure 1 displays a pie chart titled Advantages and Disadvantages of NoSQL Databases that breaks down 6 factors by their relative importance: scalability, flexibility, performance, complexity, consistency, and standardization. The chart assigns approximate shares to each factor: flexibility approximately 22.2%, scalability approximately 21%, performance approximately 19.8%, complexity approximately 14.8%, consistency approximately 12.3%, standardization approximately 9.9%, revealing clear patterns. First, the 3 top slices, flexibility, scalability, and performance, collectively form roughly 2/3 of the chart, indicating that perceived advantages dominate the assessment. Flexibility is the single largest slice, closely followed by scalability and performance, which suggests that adaptability of data models, the ability to scale horizontally, and raw operational speed are viewed as primary strengths. By contrast, complexity, consistency, and standardization occupy the smaller slices, with standardization being the smallest. This indicates these are the principal concerns or disadvantages. The chart also visually emphasizes scalability, the exploded slice, drawing attention to it as a focal advantage. From these patterns, we can conclude that while NoSQL systems are primarily valued for enabling flexible, scalable, and high-performance architectures, significant trade-offs remain in governance, uniform interfaces, and consistency guarantees, areas that teams should explicitly address when choosing or designing NoSQL-based solutions. Now let's see how we can implement a blog post creation feature using Couchbase, a document-based NoSQL database. First, we establish a connection to the Couchbase cluster by providing the server's address and authenticating with a username and password. This connection grants access to the specific bucket where our blog data will reside. Next, we define a function called createBlogPost, which accepts the title, content, and author of the blog post as parameters. Within this function, we create a dictionary to represent the blog post, encapsulating all the relevant information in a single entity. This highlights one of the main strengths of NoSQL databases. It's easy to modify the structure by simply adding or removing fields as needed. We then use the upsert method to insert the blog post into the collection, which allows us to either create a new entry or update an existing one without worrying about the constraints typically required by relational databases. Finally, upon successful execution, a confirmation message is printed, letting us know that our blog post has been created. This illustrates the efficiency and simplicity of working with document-based NoSQL systems like Couchbase. Now let's see how we can implement a basic query to retrieve a user's information in both SQL and a NoSQL environment like MongoDB. In the SQL example, we issue a simple select statement that fetches all fields from the user's table where the user ID matches a specific value. This concise syntax is a hallmark of SQL, providing developers with a standardized way to perform queries across different systems. Next, we will write the equivalent query in MongoDB, which uses a different syntax and method due to its document-oriented nature. Here, we utilize the find_one method to search for a document in the user's collection that contains the same user ID. While the MongoDB syntax is more verbose and specific, it illustrates the customized approach databases like MongoDB require. By examining both queries, it becomes evident that the lack of standardization among NoSQL databases like MongoDB creates a steeper learning curve for developers. Understanding these differences is crucial when transitioning between SQL and NoSQL systems, as this fragmentation can lead to increased complexity and additional training needs. Now let's see how we can implement a basic transactional control in a relational database used for managing an inventory system. The code begins with the begin statement, which initiates a new transaction, ensuring that all subsequent operations are treated as a single unit. This sets the stage for maintaining data integrity. The first operation is an update to the inventory, specifically reducing the quantity of a product with the ID A123 by 1. This is a crucial step in e-commerce applications to avoid overselling products. Following the inventory update, we insert a new order into the orders table, linking the user ID 456 to the product ID A123. The execution of this insertion is critical as it creates a record of the transaction in the orders database. Finally, the commit statement is used to finalize the transaction, ensuring that both the inventory update and the new order are saved permanently in the database. This approach adheres to ACID properties, ensuring reliable and atomic transactions, thus maintaining data consistency even in error scenarios. Now let's take a look at how we can implement a simple balance update operation in DynamoDB. This function, updateBalance, begins by establishing a connection to the DynamoDB service using the Bodo3 library, which is a popular SDK for OS services in Python. Once the connection is made, the function specifies which table to interact with, in this case, the accounts table where user balances are stored. The core of the operation is the putItem method, which allows us to insert or update an item in the table. Here, we create a dictionary with the user ID and the new balance that we want to set, and we pass this dictionary as the item to be inserted. Finally, after successfully executing the database update, a confirmation message is printed. It's important to remember that due to DynamoDB's eventual consistency model, this balance update may not be immediately visible across all nodes, which is something to keep in mind when developing applications that depend on real-time data accuracy, such as in financial scenarios. Now let's see how we can implement a user status update in Cassandra, showcasing the importance of data integrity during write operations. In this code, we begin by importing the cluster class from the Cassandra cluster module, which allows us to connect to our Cassandra cluster. Next, we define a function called updateUserStatus, which takes a user ID and a new status as parameters. Inside the function, we establish a connection to the Cassandra cluster by specifying the IP address of the node, here set to 127.0.0.1, and connect to the desired keyspace, user data. The pivotal part of this implementation is the query. It uses a conditional expression, if exists, to ensure that the update only occurs if the record associated with the provided user ID is present. This mechanism is crucial for maintaining data integrity, as it prevents overwriting data that shouldn't be modified. After executing the query, we check the result using the wasApplied attribute, which indicates whether the update was successful. Based on this, appropriate messages are printed, informing us whether the user's status was updated or if the user does not exist. This approach highlights the developer's responsibility in handling consistency checks within NoSQL databases, a complexity often less pronounced in traditional SQL systems. In summary, NoSQL databases deliver standout advantages like scalability, flexibility, and performance, making them ideal for modern applications that need to handle vast amounts of data and fluctuating user demands. However, they also introduce challenges such as non-standardization, potential for data inconsistency, and increased management complexity. This balance of pros and cons makes NoSQL a compelling but complex choice. As we wrap up today's lesson, remember that choosing between NoSQL and SQL should always be grounded in the specific requirements of your application. Reliably evaluating the advantages against the disadvantages will empower you to make informed decisions that align with your development goals while maintaining the integrity and performance of your applications. Next, we will explore real-world applications of these NoSQL advantages and how developers have implemented successful solutions using them. Stay tuned for that. As modern applications generate and process massive amounts of data, the need for a robust and scalable data management solution becomes paramount. Today, we dive deep into the scalability and flexibility of NoSQL solutions and what that means for your applications. So far, we learned that NoSQL databases provide significant advantages such as scalability, flexibility, and performance, making them suitable for handling large datasets and varying user demands. However, they also present challenges like non-standardization, eventual consistency issues, and increased management complexity. We explored various transaction management methods and specific implementations in databases like MongoDB and DynamoDB, emphasizing the importance of understanding these trade-offs. Moving forward, we'll examine real-world applications of NoSQL advantages and successful developer implementations. Now let's see how we can implement a straightforward method to add a new node to an existing Cassandra cluster, showcasing the seamless scalability of NoSQL databases. In this code snippet, we begin by importing the necessary cluster class from the Cassandra driver library, which provides the foundation for connecting to a Cassandra cluster. Next, we define a function called addNodeToCluster, where we initiate the cluster with a list containing the existing nodes as well as the new node that we want to add. By doing so, we align with Cassandra's capability for horizontal scaling, where additional nodes can be brought online to handle increased data loads effectively. The magic of Cassandra lies in its ability to redistribute data automatically across the cluster once a new node is added, thus ensuring an even load balance amongst all nodes. Finally, a confirmation message is printed to indicate the successful addition of the new node. This process is crucial for maintaining high availability and performance, especially in scenarios such as e-commerce applications where demand can fluctuate dramatically. Overall, this example illustrates how effortlessly you can scale your database infrastructure with a NoSQL solution like Cassandra. Next, we will implement a function to create user profiles in our MongoDB database, showcasing how easy it is to manage diverse user data. We begin by importing Mongo client from the PyMongo library, which allows us to interact with our MongoDB instance. The create user profile function takes three parameters: username, posts, and friends. This design reflects the flexibility of Nosql, allowing us to capture various data types under a single user profile. Inside the function, we establish a connection to the MongoDB server running locally and access the social media database. We then construct a user profile as a dictionary, which includes the username along with arrays for posts and friends. This approach illustrates how we can easily expand user profiles by adding new fields later on without any schema restrictions. After defining the user profile, we insert it into the user's collection using insert1, which stores the document in the database. Finally, we print a confirmation message indicating the successful creation of the user profile. This example exemplifies how NoSQL databases simplify data management, enabling quick adaptations to changing requirements. The figure presents a horizontal bar chart titled Evaluation of NoSQL Solutions, Scalability and Flexibility that quantifies perceived importance across 5 key features: scalability 90%, flexibility 85%, performance 80%, complexity 70%, and consistency 60%. The most prominent pattern is a clear descending ranking. Scalability is prioritized highest, closely followed by flexibility and then performance, indicating decision-makers value the ability to expand capacity and adapt schemas slightly more than raw throughput. Complexity sits in the middle range, 70%, signaling a notable concern about operational overhead and management effort when adopting NoSQL solutions, while consistency is lowest, 60%, reflecting a willingness to accept weaker or eventual consistency models in exchange for the other benefits. The percentage labels on each bar confirm the magnitude of these differences. The gap between scalability and consistency, 30 percentage points, emphasizes that trade-offs around consistency are an expected part of many NoSQL deployments. From these values, we can conclude that when selecting NoSQL technologies, teams typically prioritize scalable and flexible architectures first, optimize for performance next, and then invest in mitigating complexity and consistency risks through tooling, application-level checks, or hybrid approaches. Now let's examine how we can implement a function to log user interactions in a DynamoDB table. This function, logUserInteraction, takes 2 parameters, userid and videoid. First, we import the Bodo3 library, which is the Amazon Web Services OS SDK for Python, allowing us to interact with DynamoDB. Inside the function, we establish a connection to the DynamoDB service by creating a resource object with Bodo3 resource DynamoDB. Next, we specify the table named UserInteractions, where we will store our data. To log an interaction, we use the putItem method to insert a new entry into the table. This entry consists of the userid, videoid, and a timestamp that you would generally set dynamically to reflect the actual interaction time. Finally, the function includes a print statement that confirms the logging of the user interaction, providing immediate feedback that the operation was successful. This straightforward implementation highlights how efficiently DynamoDB can handle high-frequency data logging, crucial for real-time analytics in applications like streaming platforms. Now let's see how we can implement transactions in MongoDB to ensure data integrity during operations like transferring funds between accounts. First, we establish a connection to the MongoDB server using the Mongo client, pointing to the local instance. This step is crucial as it allows us to interact with the database. Next, we initiate a session, which is necessary for executing transactions in MongoDB. By wrapping our operations within a start transaction context, we ensure that both account updates, debiting one user and crediting another, occur within a single atomic transaction. This means that if any part of the transaction fails, all changes will revert, preserving the consistency of account balances. As we define our updates, we employ the update1 method to decrement the balance of the first user and increment the second user's balance, both linked to the active session. This structure not only maintains data integrity across both accounts during the money transfer, but also adds an extra layer of reliability, preventing any erroneous states if something goes awry. With this implementation, we demonstrate how MongoDB's transaction capabilities can be harnessed to address the challenges of consistency commonly faced with NoSQL databases. Now let's implement a basic validation function for user profile creation to ensure data integrity in a NoSQL environment. This function, validateUserProfile, checks that the username meets specific criteria. It must be a string with a minimum length of 3 characters. If the username fails this check, a value error is raised with an informative message, prompting the user to provide a valid username. Next, we ensure that both the posts and friends parameters are lists. This step is crucial because, in a schemaless database, maintaining uniformity in data types is essential to prevent inconsistencies. If either of these conditions is not met, a value error is again raised, indicating that the user must provide lists for these fields. At the end of the function, if all validations pass, a confirmation message is printed to indicate that the user profile is valid. To demonstrate the function in action, an example usage is provided within a try-except block, which gracefully handles any errors during the validation process. This not only emphasizes good programming practices, but also reinforces the importance of validation in managing NoSQL data effectively. In summary, the scalability and flexibility of NoSQL solutions present enormous opportunities for modern applications. They allow developers to build systems that seamlessly handle increased loads and diverse data while maintaining performance. However, it is crucial to navigate the accompanying challenges around consistency and management effectively. What we've covered today emphasizes that the future of data management lies in harnessing these strengths while keeping potential pitfalls in mind. As we conclude this segment, remember that the key to effectively using NoSQL lies in understanding when to lean into its strengths, scalability, and flexibility, while planning for the necessary governance and management strategies that will maintain data integrity as your applications evolve. Stay tuned for the next session, where we will explore real-world implementations that showcase NoSQL capabilities in action and how developers have successfully utilized these databases to solve complex problems. In this lesson, we're diving into the world of NoSQL design choices, particularly focusing on the importance of the CAP theorem in distributed systems. Let's start with a crucial concept that every budding database developer should understand: the CAP theorem that was introduced by Eric Brewer in the early 2000s. The CAP theorem states that in a distributed data store, there are three core properties to consider: consistency, availability, and partition tolerance. The theorem essentially posits that you can only achieve two of these three properties at any given time while sacrificing the third. This might sound disheartening, but understanding this trade-off is fundamental in making informed design choices for your NoSQL database. Let's break this down a bit further. Consistency means that every read receives the most recent write or an error. Availability ensures that every request receives a response about whether it was successful or failed. Partition tolerance guarantees that the system continues to operate despite network partitions that may occur during communication of failure. Imagine you're at a restaurant and the chef serves food immediately after it is cooked. If the chef only prioritizes serving a perfect meal, consistency, customers may wait too long, availability. Alternatively, if food is rushed out as fast as it's made, availability, it may not always be perfect, consistency. So, making design choices often means choosing which aspect to prioritize according to your application's specific needs. The displayed bar chart titled CAP Theorem Trade-offs in NoSQL Databases quantifies the relative emphasis placed on each CAP property: consistency 80, availability 70, and partition tolerance 90. Reading the chart, the clearest pattern is that partition tolerance has the highest value, 90, indicating it is the dominant priority in this hypothetical NoSQL design scenario. Consistency follows at 80, showing a strong but secondary emphasis, while availability is the lowest at 70. The numeric gaps 10 points between partition tolerance and consistency, and another 10 points down to availability, illustrate a deliberate rebalancing. Designers accept somewhat reduced availability to ensure the system tolerates partitions and still keeps a high level of consistency relative to availability. The value labels above each bar make these comparisons explicit, and the y-axis grid helps compare magnitudes precisely. From this visualization, we can conclude that the model design choice favors maintaining operation under network partitions first, preserving a high but not maximal consistency second, and accepting more limited availability than the other two properties. These relative priorities map directly to trade-offs discussed earlier. When partition tolerance must be guaranteed, for example in geo-distributed systems, architects may tune replication, quorum, and failover strategies to keep the system running, while using techniques like eventual consistency or controlled quorums to balance consistency and availability according to the application's tolerance for stale reads. Now let's see how we can implement a simple interaction with MongoDB using Python. We begin by establishing a connection to our MongoDB server with the MongoClient class, pointing it to our local database instance running on the default port. After connecting, we specify which database and collection we want to use by referencing myDatabase and myCollection, respectively. Next, we insert a document into our collection, which represents a user with a username and email address. This operation is done using the insert1 method, allowing us to store the user data effectively. After inserting the user, we proceed to retrieve the user's data with the find1 method, searching for the specific user by their username. Finally, we print the retrieved user information. It's important to note that due to the nature of distributed systems and potential network partitions, when querying data, the information we receive can be stale or outdated, especially if we access nodes that have not yet synchronized with the most recent updates. This example highlights how simplicity in code can face the complexities introduced by the CAP theorem in real-world applications. Now let's take a look at how we can implement a simplified model for a distributed database that emphasizes consistency through the use of locking mechanisms. In this code, we begin by defining a class called **distributed database**, which serves as the framework for our implementation. Within the constructor, we initialize an empty list to hold the nodes of our distributed database and a threading lock to manage access to these nodes during data operations. This locking mechanism is crucial for ensuring that concurrent access to shared resources doesn't lead to data conflicts, a common challenge in distributed systems. Next, we have a method called **addNode**, which allows us to add new nodes to our database. By wrapping the node addition in a lock, we assure that the integrity of our node list is maintained, preventing any race conditions that could arise if multiple threads attempt to add nodes simultaneously. The write data ** method reflects how we're enforcing consensus during write operations. Here, we iterate through our list of nodes and invoke a mock function, commit **, on each node to simulate writing the data. This mimics a scenario where all nodes must agree on the data being written, reinforcing the consistency model we aim to uphold. Thus, through strategic use of locks and a consensus approach, this code lays the groundwork for a more reliable and consistent distributed database. As you consider these design choices, evaluating real-world case studies can also offer insights into how various technologies apply the principles of the CAP theorem. Take Amazon's DynamoDB as a notable example. DynamoDB was specifically designed to provide high availability and partition tolerance while conceding some levels of consistency, embracing an AP approach. For businesses dealing with massive scale and varying loads, the implementation of this approach serves its purpose excellently. Applications like shopping carts can afford eventual consistency. For instance, if a customer adds an item and then checks out, the quantity may be updated across distributed instances, but not instantaneously. By accepting that it will achieve eventual consistency, DynamoDB can ensure availability and performance across a large dataset while still maintaining reasonable consistency levels. Now let's implement a keyspace and a table in Apache Cassandra designed for a retail application. The first command creates a keyspace named retail, specifying a replication strategy to enhance data availability and resilience. By setting a replication factor of 3, we ensure that even if some nodes in the cluster go down, our data remains accessible through other replicas. This is crucial for maintaining system availability, especially in scenarios where reliability is key. Next, we create a table called orders within the retail keyspace. This table is structured to store essential information about customer orders, featuring 4 fields: orderid, item name, quantity, and order date. The orderid is set as the primary key, ensuring each order can be uniquely identified and retrieved efficiently. Now let's see how we can insert data into our orders table. The insertion command adds a new order with a unique identifier generated using a UUID, specifying details of the order such as the item, quantity, and date. This approach highlights the flexibility of Cassandra's data model and its suitability for handling high-volume read and write operations seamlessly. In conclusion, as we think through design strategies informed by the CAP theorem, keep in mind that the right choice is driven by the application needs, the expected workload, and crucially, how data integrity is managed. NoSQL databases bring with them unparalleled flexibility and scalability. but as developers, we must navigate the delicate balance of consistency, availability, and partition tolerance. So far, we covered the fundamentals of the CAP theorem and its implications in NoSQL database design. We've explored various strategies and real-world applications. Now, as we wrap up this lesson, remember that the decisions you make in how you design your database schemas will significantly impact your application's functionality and user experience down the line. So keep experimenting, understand your application's requirements, and don't hesitate to mix and match strategies until you find the best fit. Thank you for joining this exploration of NoSQL design choices. In this session, we are diving into the essential topic of analyzing consistency models in NoSQL databases. These models are crucial for understanding how data is managed across distributed systems, especially given the trade-offs between availability and partition tolerance. So far, we learned about the CAP theorem, which highlights the trade-offs between consistency, availability, and partition tolerance in distributed systems. We discussed how different NoSQL databases, such as MongoDB and DynamoDB, prioritize these properties differently based on application needs. Strategies like eventual consistency and specific data modeling patterns were also explored to manage these trade-offs effectively. Lastly, we emphasized the importance of aligning database design choices with application requirements to optimize functionality and user experience. Now we will cover the various consistency models prevalent in NoSQL databases, exploring how they impact data access and system performance. Now let's see how we can model strong consistency using SQL and PostgreSQL to ensure that our updates maintain data integrity. We begin with a transaction using the begin statement, which marks the start of a series of operations that must either complete successfully or be rolled back if any issues arise. This is critical for maintaining consistency during operations. Next, we acquire an exclusive lock on the orders table to prevent any other transactions from accessing or modifying the data while we perform our update. By using lock table orders in exclusive mode, we ensure that no other transactions can interfere with our operation, which is crucial when we want to guarantee that all subsequent reads reflect our right operation. Then the actual update occurs. Here, we modify the shipping address for a specific order identified by orderid. The command update orders set shipping address equals 123 New Street, where orderid equals 1, updates the record with the new address. This operation will only succeed once the lock is acquired, reinforcing the notion of strong consistency. Finally, we complete the transaction with commit, which commits all changes made during the transaction to the database, ensuring that all nodes see the updated information immediately. By using these mechanisms, we maintain strong consistency, providing a reliable experience where the most current data is always accessible immediately after any write operation. Next, we will write the following code to simulate eventual consistency in our SQL database using asynchronous updates. The first part of the code inserts a new shipping address into the shipping updates table. This acts as a staging area where updates can be queued without immediately affecting the main data stored in the orders table. By doing this, we ensure that the system remains highly available, allowing read operations to proceed even if the updates haven't fully propagated yet. Now let's see how we can implement the second part of the code, which involves applying these updates asynchronously to the orders table. This is achieved by executing an update statement that retrieves the new address from the shipping updates table. By associating the new address with the relevant orderid, we execute the update only when it's convenient, reflecting the eventual consistency model. With this approach, users may read the old address immediately after the update is inserted, emphasizing that while the update process is ongoing, the system still prioritizes availability over immediate consistency. This technique provides flexibility in managing data, ensuring that users can interact with the system without waiting for all nodes to settle. The displayed bar chart, titled Analyzing Consistency Models in NoSQL Databases, shows 5 consistency models on the x-axis and their corresponding effectiveness levels on the y-axis. The exact values shown on the bars are strong consistency equals 70, eventual consistency equals 60, causal consistency equals 75, session consistency equals 50, and strongly consistent reads equals 65. From the bar heights and the numeric labels, the clear pattern is that causal consistency has the highest effectiveness, 75, followed closely by strong consistency, 70, and then strongly consistent reads, 65. Eventual consistency sits in the middle at 60, while session consistency is lowest at 50. The y-axis grid and the value labels make these differences easy to compare quantitatively. Causal and strong models dominate in this depiction, indicating that models preserving ordering or global agreement score higher for the scenarios represented, whereas session-level guarantees score lower in overall effectiveness. This visualization therefore reinforces the trade-offs discussed earlier. Approaches that aim for broader ordering or immediate global agreement rank higher on effectiveness here, while session-scoped or more relaxed models show reduced numerical effectiveness in the same context. Now let's take a look at how to implement causal consistency using versioning in a SQL-like context. In this code, we begin by creating a table called orders, which includes 3 columns: ordered, shipping address, and version. The ordered is defined as a primary key, with the serial data type that automatically increments, ensuring each order has a unique identifier. The shipping address column stores the address associated with the order, while the version column tracks the last modification made to the order data. Next, we see an operation to update the shipping address for a specific order identified by ordered. Here, the code updates the shipping address to 987 Another Street and increments the version by 1. This versioning approach helps nodes distinguish between different states of the data, for instance, indicating that an update has occurred. By employing version numbers in this manner, we ensure that causally related updates, such as changing an address that directly follows another update, are issued in a consistent order across all nodes. This design serves to uphold the guarantees of causal consistency, as it allows for efficient tracking and organization of updates in a distributed system. Now let's see how we can implement session consistency in our code. In this example, we begin a transaction by using the begin statement, which marks the start of our session. This is important because it sets the transactional scope within which all operations will occur. Next, we perform an update on the user's table, changing the email address for a specific user identified by their userid. This ensures that the user sees their latest changes immediately within the session. After executing the update, we follow it up with a select statement that retrieves the data for that same user. This allows the user to confirm that their email has been updated without awaiting any external confirmation or refresh. Finally, we conclude the transaction with the commit statement, which saves all the changes made during the session. The essential aspect of this flow is that while the user can view their own changes instantly, any updates made by other users will not be visible until they start a new session, aligning perfectly with the session consistency model. This design supports a smooth user experience by allowing immediate feedback on individual actions. Now let's take a look at how we can implement strongly consistent reads in SQL to ensure that our application always interacts with the most up-to-date information. In this example, we begin by initiating a transaction using the begin statement, which sets the stage for our operations to be executed safely and atomically. Next, we execute a read operation on the orders table, specifically fetching the record for a particular order ID. By utilizing the for-update clause in this query, we effectively lock the row we're reading, ensuring that no other transactions can modify or read this data until our transaction is fully completed. This locking mechanism is crucial, as it guarantees that the data retrieved reflects the most recent state, which is essential for operations where accuracy must be prioritized, such as in financial transactions. Following this read operation, we proceed to update the shipping address for the same order, demonstrating how we can manage data modifications while maintaining consistency. Finally, we conclude the transaction with the commit statement, which applies all the changes made during the transaction, thus ensuring that the updates are both atomic and consistent within the context of our application. This approach exemplifies how strongly consistent reads can be effectively implemented in SQL to cater to critical read operations. In conclusion, the consistency models in NoSQL databases present varied approaches to handling data across distributed systems. Understanding the trade-offs between strong consistency, eventual consistency, causal consistency, session consistency, and strongly consistent reads is essential for developers and architects in making informed decisions based on their application needs and traffic patterns. With these models, one must recognize that different applications will have distinct requirements. For instance, applications needing fast user interactions may lean on eventual or session consistency, while those handling critical financial transactions may require strong consistency guarantees. Ultimately, as you design your systems, always keep the specific operational requirements in mind and select the consistency model that aligns best with the user experience you wish to deliver. Thank you for joining this session on analyzing consistency models in NoSQL databases. Keep experimenting with these concepts in your next projects, and who knows what systems you might design. Now let's see how we can implement sharding in MongoDB to optimize our database for large volumes of data. The shard collection command is essential for distributing data across multiple servers, allowing for improved performance and scalability. In this command, we're specifying the database and collection we want to partition, which in this case is my database, my collection. Here, the myShard key is critical. It determines how the data is divided logically, allowing MongoDB to distribute data efficiently. By using a shard key, we ensure that related data is kept together and queried more effectively, which is crucial in environments with vast amounts of data. The operation enables MongoDB to enhance query performance by balancing the load across different nodes. This means that even as your data grows, the system remains responsive, minimizing the performance bottlenecks often seen in traditional relational databases. As we execute this command, we lay the groundwork for a more resilient architecture that can gracefully scale with our application's needs. Overall, this sharding strategy exemplifies how NoSQL databases like MongoDB are designed to handle modern data challenges. Now let's see how we can insert a user document into a MongoDB collection without adhering to a strict schema. In this example, we're creating a document for a user named Alice, which showcases the flexibility that NoSQL databases provide. Here we define the user's details, including the name, age, and email address. Notice the nested structure under Preferences, allowing for additional customization, such as the theme and notification settings. This highlights how different users can have various fields without any disruption to the database structure. Next, we utilize the InsertOne method, which is specifically designed for inserting a single document into the user's collection. This operation is quick and efficient, demonstrating how NoSQL databases remove the complexity of schema constraints found in traditional SQL databases. By not requiring a fixed schema, businesses can adapt their data models rapidly in response to evolving requirements, making development cycles swift and agile. As we see with Alice's document, the ability to add new fields seamlessly paves the way for innovation and responsiveness in application development. Now let's see how we can implement a simple example using the Redis client in Python. First, we initiate a connection to the Redis server running on our local machine. By specifying the host, port, and database index, we create a client instance that allows us to interact with the Redis database. Next, we demonstrate how to store data efficiently. In this case, we set a key-value pair where the key uniquely identifies the data for a user. The value is formatted as a JSON string containing the user's details, including their name and age. This method showcases how easy it is to insert structured data into a key-value store. After storing the user information, we proceed to retrieve it. By calling the get method with the same key, we can quickly access the stored data. The retrieval process in Redis is extremely fast, illustrating one of the primary benefits of using a key-value database: rapid access to data without the overhead of complex query operations typically found in relational databases. This example effectively highlights the performance advantages of NoSQL databases in real-world applications. The figure titled Advantages and Disadvantages of NoSQL Databases presents a grouped bar chart comparing assessment levels in % across 5 features: scalability, flexibility, performance, complexity, and consistency. For each feature, an advantages bar shows a positive assessment: 90% scalability, 85% flexibility, 80% performance, 60% complexity, 40% consistency, while a corresponding disadvantages bar shows the complementary value: 10%, 15%, 20%, 40%, 60% respectively. Key patterns are clear. Scalability, flexibility, and performance are evaluated very highly on the advantages side, indicating these are core strengths of NoSQL systems. Complexity is more balanced, advantages at 60% versus disadvantages at 40%, highlighting that while NoSQL can simplify certain modeling tasks, it can also introduce architectural or operational complexity. Consistency is the standout weakness. Advantages at only 40% with disadvantages at 60%, reinforcing the lesson that consistency guarantees are a relative shortcoming for many NoSQL solutions. From these values, we can conclude that NoSQL is generally well suited where horizontal scaling, schema flexibility, and high throughput are priorities, but teams must explicitly plan for consistency requirements and manage complexity when designing systems that rely on NoSQL technologies. Now let's implement a keyspace in Cassandra with a robust replication strategy. The create keyspace command is used to establish a new keyspace called myKeyspace, which serves as a container for your tables and data. In this command, we specify the replication strategy through the with replication clause. We are employing network topology strategy, which is designed to support multi-data center environments. Here we define two data centers, DC1 and DC2. For DC1, we set the replication factor to 3, meaning that 3 copies of the data will be stored in this data center, enhancing durability and uptime in the event of a failure. Simultaneously, in DC2, we specify a replication factor of 2, ensuring that 2 copies of the data exist there as well. This approach not only makes the system resilient to node failures, but also optimizes data access across geographic locations, leading to improved availability for applications. By defining these replication strategies, organizations can effectively safeguard their data while ensuring that applications remain operational and performant even during potential outages. Next, we will write a SQL transaction that demonstrates strong consistency to ensure accurate balance updates in a banking application. First, the transaction begins with the begin statement, which sets up a new transaction context. To ensure that no other operations can change the user's balance while this transaction is in progress, we select the balance using select balance from accounts where user id equals 14 update. The for update clause locks the row, preventing any concurrent updates from occurring until this transaction is completed. Once we have confirmed the balance, the next step is to update it with the withdrawal amount. We do this with the statement update account set balance equals balance 100 where user id equals 1. This operation deducts 100 from the user's balance. After making the update, we call commit to finalize the transaction, making all changes permanent. This structured approach highlights the need for strong consistency in sensitive applications, ensuring that users see the most current data and protecting against errors such as overdrafts or misunderstandings. By managing the locking and committing process effectively, we can maintain reliable user experience and data accuracy. Now let's see how we can utilize MongoDB to query data effectively using its aggregation framework. The code provided demonstrates a powerful query designed to extract specific information from the orders collection. Initially, it filters the data to retain only those records where the status is marked as shipped. This step is crucial, as it helps in narrowing down the dataset to those orders that have already been dispatched, allowing for efficient data processing. Following the matching operation, the code groups the filtered results based on the customer ID. This grouping is important as it allows us to aggregate the data by customer, providing insights into the total order amounts associated with each customer. The sum operator is then employed to calculate the cumulative total of the order amounts for each grouped customer. This capability showcases the flexibility of MongoDB's aggregation framework, enabling complex data manipulations without the need for traditional SQL join operations. It emphasizes a paradigm shift for developers accustomed to relational databases, highlighting the need to adjust to the NoSQL mindset for effective data analysis. Now let's implement a user role in MongoDB that facilitates access control within our database. This is crucial for maintaining security, especially as applications scale. In the following code, we create a role named readWrite, which allows users to perform specific actions on a designated collection in our database. The role is defined with associated privileges, specifically granting the ability to insert, update, and remove documents from my collection in my database. This granular control is vital for regulating what users can do, helping prevent unauthorized access and modifications to sensitive data. Additionally, we can see that the roles array is empty. This means that the newly created role does not inherit any permissions from other roles, providing a clean slate for access management. By implementing user roles in this manner, developers can ensure that their applications adhere to best practices for security and governance. Consistently auditing these roles and their usage is essential to confirm that they align with the overall security framework of the organization. In conclusion, NoSQL databases present a compelling approach for managing data in our ever-evolving digital landscape. Their advantages in scalability, flexibility, speed, and resilience make them an appealing choice for many modern applications. As we explored today, these systems shine in handling unstructured data and supporting rapid development environments. Yet they also come with their fair share of challenges, from potential consistency issues to proprietary querying languages, which developers must navigate wisely. Always remember that the choice between SQL and NoSQL is not an either-or situation, but rather a matter of contextual application requirements. Knowing when to leverage the strengths of NoSQL depends ultimately on the specific needs of your application. As we move forward, continue experimenting with these concepts in your projects. Understand your use cases thoroughly, and don't hesitate to open up to the diverse data architectures available in the vast world of data management. Thank you for joining today's exploration, and I hope you're feeling ready to tackle the NoSQL universe with confidence. The base model in NoSQL databases introduces fascinating implications for data integrity and concurrency control. Today, we'll dive deep into these concepts, exploring how they impact the design and functioning of NoSQL systems while leveraging some code examples to elucidate these ideas. So far, we learned that NoSQL databases are popular for their flexibility and performance, making them suitable for large volumes of data and various use cases. We covered different consistency models, sharding, and schema flexibility, which enhance scalability and adaptability in changing environments. Additionally, we discussed the advantages of superior read-write performance and the ability to support distributed architectures, while also addressing limitations such as potential consistency issues and proprietary querying languages. Understanding the trade-offs of NoSQL databases is key to effectively utilizing them in modern applications. Now we will talk about the implications of the base model on data integrity. The BASE acronym stands for basically available, soft state, and eventually consistent. This model is often seen as an alternative to the ACID properties traditionally associated with relational databases, which guarantee strong consistency. Instead, the base model embraces a more relaxed approach, allowing for greater flexibility and availability at the cost of immediate consistency. This brings us to our first point. What does it mean for data integrity when we adopt the base model? Now let's see how we can manage user sessions within a key-value store like Redis. The code provided registers a session for the user with ID 1001 by setting their session status to logged in. This operation is simple yet powerful, highlighting the flexibility of the base model, which allows us to store this information without a strict schema. Additionally, we set an expiration date for the session, indicated by a separate key that defines when the session should no longer be valid. This approach ensures that sessions are managed effectively, removing potential stale data and enhancing overall application performance. Using a key-value format in a NoSQL database like Redis allows for efficient reads and writes, especially during peak traffic, as it does not require immediate consistency across nodes. This means that different nodes can update session data independently, improving responsiveness for users interacting with applications during busy times. By leveraging these features, we can seamlessly handle user sessions while embracing the relaxed consistency inherent in the base model. Next, we will write the following code to implement versioning for user sessions, which is crucial in a base model environment where different nodes can hold distinct views of the data. By incorporating version numbers into our key naming convention, we establish a clear differentiation between successive updates to a user session. In this code, we set two different session states for user ID 1001, one indicating the user is logged in and the other noting the user has logged out. This versioning helps ensure that when multiple updates occur from different nodes, we can reference the appropriate session state. Next, we will see how timestamps can enhance data integrity when managing product inventory levels. In this snippet, we designate a timestamp for the inventory level of product 1001 and then set its current stock to 150. By tagging the inventory level with a timestamp, our application logic can verify the recency of updates before proceeding with any changes. If a new update comes in with an earlier timestamp, it is disregarded, effectively protecting data integrity in scenarios where concurrent updates might otherwise create inconsistencies. Through these techniques, we can maintain a robust yet flexible data management strategy in a distributed environment. Now let's implement a banking transaction example using optimistic concurrency control to ensure data integrity. We start the transaction by initiating a block, followed by selecting the current balance from the database for the specified account ID. This step is crucial as it establishes a snapshot of the account's state before any modifications are made. Next, we check if the current balance is sufficient to cover the transfer amount. This conditional check is vital as it prevents overdrawn transactions and ensures that the funds are available. If the condition holds true, the code updates the account balance by deducting the transfer amount. Upon successfully updating the balance, the changes are committed to the database, finalizing the transaction. However, if the initial balance check fails, indicating that another transaction altered the balance during processing, a rollback occurs. This rollback ensures that no inconsistent state is committed, thus maintaining the integrity of the banking system. Through this approach, we leverage the advantages of the base model by allowing concurrent operations while ensuring eventual consistency through conflict resolution mechanisms. Now let's see how we can implement a mechanism for refreshing comment visibility in a distributed database. The code operates within an infinite loop, continuously updating the visibility status of comments that have not been seen by users within the last 5 minutes. The statement updates the database to mark comments as updated, where their visibility status was previously old, and the timestamp of the last update exceeds the 5-minute threshold. This approach ensures that users are consistently presented with the most relevant and timely information. To avoid overwhelming the system and to manage server load, the loop includes a sleep command, effectively pausing the process for 60 seconds before repeating the update check. By allowing regular background updates, this mechanism embodies the soft state concept in the base model, which helps maintain performance and user experience without requiring strict immediate consistency. This strategy exemplifies how developers can efficiently manage the transient nature of data in an environment where changes may occur at varying rates across multiple nodes. We've covered a lot about managing data integrity under the base model, but how does it impact real-world applications? The implications of the base model can be observed significantly in applications that handle massive data volumes like streaming services, e-commerce platforms, and collaborative tools. Take, for instance, a real-time collaboration tool like Google Docs. When multiple users edit documents simultaneously, the underlying data must embrace eventual consistency. Changes may not be synchronized instantly across all users, yet the system remains functional and responsive. Each user operates on the most recent version that their node acknowledges, and an eventual reconciliation obscures immediate conflicts. Leveraging the base model allows such applications to scale effectively while still functioning in an agile environment. Adopting strategies like user prompts, notifications, or visual cues can mitigate user risks as they collaborate. For example, if a user tries to edit a section of a document that's currently being modified by another user, the application might provide a message indicating that changes are being made, ensuring the user understands the transient states of their system. Now let's implement a system for tracking operational metrics in our Nosql environment. The code creates a table named System Metrics, which will serve as a centralized repository for collecting and storing various performance metrics over time. Each record in the table will consist of an identifier, id, which is automatically generated as a primary key using the serial data type, ensuring uniqueness for each entry. In addition to the unique identifier, we have a metric name column where we can store the specific name of the metric being monitored, such as request latency or user interactions. This column is defined as a varchar data type, allowing for a variety of string lengths that will accommodate different metric names. Next, the metric value field captures the numerical value associated with the metric, using the numeric data type, which is crucial for high-precision values often found in performance measurements. Finally, the recorded@. column is automatically populated with the current timestamp whenever a new metric is inserted, thanks to the default current timestamp clause. This ensures that we always have context about when each metric was recorded, allowing for detailed time series analysis and performance tracking over time. In summary, we've journeyed through the implications of the base model on data integrity. From understanding the core principles that prioritize availability and soft state to recognizing the necessary trade-offs regarding concurrency control and eventual consistency, we've equipped ourselves to navigate this evolving landscape more effectively. Incorporating strategies like versioning, timestamps, and monitoring will empower developers to manage potential pitfalls and capitalize on the base model's advantages. As we continue exploring NoSQL databases, remember that data integrity must be approached with care, balancing performance, availability, and the nuanced needs of your application. By understanding these implications, we'll be better prepared to tackle the challenges of modern data management systems. Keep experimenting with these concepts in your projects and watch how these principles come to life in your next big application. Thank you for your time, and let's continue to dive deeper into the world of databases in our upcoming lessons. NoSQL databases are revolutionizing the way we manage data, especially in an era driven by big data and real-time analytics. Unlike traditional relational databases, they offer flexible schemas and can scale horizontally, making them perfect for handling massive volumes of data with speed and efficiency. So far, we learned that NoSQL databases prioritize flexibility and performance, which makes them suitable for handling large datasets across various applications. We explored the base model, emphasizing availability and soft state while accepting eventual consistency, contrasting with traditional ACID properties. The importance of data integrity management and concurrency control within the base framework was highlighted, alongside strategies for maintaining data integrity such as versioning and timestamps. Lastly, we discussed real-world applications of the base model, particularly in high-volume environments, and the need for robust monitoring systems to manage potential inconsistencies. Now we will delve deeper into the key concepts of NoSQL databases, exploring their various types, use cases, and advantages. Now let's take a look at how we can implement a simple in-memory key-value store to manage user profiles. We define a dictionary called user profiles, where each key is a unique user ID, such as user123, and the value is a nested dictionary containing user information like their name, age, and email address. This structure allows for easy and efficient data retrieval based on the user ID. Next, we will write a function named getUserProfile, which takes a user ID as an argument. This function utilizes the get method of the dictionary to return the corresponding user profile. If the provided user ID does not exist in the user profiles dictionary, it will return a friendly message indicating that the user was not found. This approach ensures that even if we query a non-existent ID, the program continues to run smoothly without throwing an error. To demonstrate this functionality, we will call our getUserProfile function with the user ID, user123, and print the result. This example highlights the simplicity and efficiency of key-value stores for quick lookups and easy access to user data, making them an appealing choice for many applications that require fast data retrieval. The bar chart titled Types of NoSQL Databases and Their Popularity displays 4 categories with labeled percentages: document stores at 35%, key-value stores at 25%, column family stores at 20%, and graph databases at 20%. The clear pattern is that document stores lead in popularity, representing the largest single share, followed by key-value stores as a strong second. Column family and graph databases share equal, smaller shares, indicating they are more specialized but still significant. From these values, we can conclude that flexible document-oriented models are currently the most widely adopted approach, likely because they balance schema flexibility with rich query possibilities, while key-value systems remain highly valued for simple, high-performance access patterns. The equal shares for column family and graph solutions suggest that analytic and relationship-centric workloads are important niches. Column family stores are favored where wide-scale analytics and grouped attribute access are required, and graph databases are selected when traversing complex relationships is the priority. Overall, the distribution shows a moderate skew toward document and key-value models, together accounting for 60% of the chart, reinforcing the lesson point that technology choice is often driven by the dominant application needs. flexibility, and speed, rather than by a one-size-fits-all solution. Now let's see how we can implement a simple representation of a blog post in Python using JSON. The given code begins by simulating a JSON object containing details about a blog post, such as the title, author, content, tags, and comments. This structure is a perfect illustration of how document stores like MongoDB work, as they allow documents to contain nested arrays and objects. To transform this JSON string into a usable Python dictionary, we use the JSON loads function. This method parses the JSON formatted string and loads it into a data structure we can work with in Python. Next, we define a function named getComments, which extracts the messages from the comments associated with our blog post. By utilizing a list comprehension, this function iterates over the comments and compiles a list of the messages. Finally, we invoke this function to retrieve the comments and print them out, demonstrating how easy it is to access nested data in a document store format. This practical example showcases the flexibility and power of using JSON data structures in applications that require complex data representation and retrieval. Now let's see how we can implement a simple representation of column family data using Python. We begin by utilizing the default dict from the collections module, which allows for easy creation of nested dictionaries without needing to check for the existence of each key. This is particularly useful in organizing our data into logical groupings, such as personal and contacts under a specific user ID. Next, we store various attributes about a user, specifically for user 123, under the relevant column families. Here we assign values to the user's name and age under personal, while their email falls under contacts. This structure effectively mimics the way column family stores organized data, enabling efficient data retrieval when we need to access specific attributes. To retrieve the user data, we define a function called getUserData that takes a user ID as an argument and returns the data stored within that user's column family as a dictionary. Finally, we call this function, providing the user ID, and print the result. This demonstration showcases how column family stores can efficiently manage and retrieve grouped data, thereby highlighting their utility in handling vast datasets effectively. Now let's take a look at how we can model a social network using a graph database approach. In this implementation, we define a user class that captures essential properties of a user, including their username and a set of friends. The addFriend method allows a user to establish a friendship with another user, effectively updating the friends set to reflect this relationship. To suggest new friends based on mutual connections, we implement the suggestFriends function. This function takes a user and constructs a set of suggested friends by iterating through the user's friends and collecting their corresponding friends as well. It's important to note that the function discards the current user from the suggestions to avoid self-recommendation. Finally, we create instances of the user class for Alice, Bob, and Charlie and establish their friendships. When we call the suggestFriends function for Alice, it suggests connections like Charlie, who is indirectly connected through Bob. This exemplifies how graph databases, by visualizing data as nodes and edges, enable intuitive exploration of relationships and facilitate complex queries in interconnected data scenarios. So far, we have covered various types of NoSQL databases and their unique features. Each type serves different use cases and provides distinct advantages, such as flexibility, speed, scalability, and ease of use. Now, let's discuss the benefits of using NoSQL databases in detail and how they tackle challenges faced by traditional relational databases. One major advantage of NoSQL databases is their ability to handle unstructured and semi-structured data. Traditional relational databases excel at structured data, but often struggle to adapt to changing data requirements. NoSQL databases, on the other hand, allow for dynamic schema definitions, meaning new fields can be added on the fly without disrupting existing data. This makes NoSQL an ideal choice for applications dealing with varied and evolving datasets, such as social media platforms or content management systems. Consider an e-commerce application where product attributes can vary significantly. Using a NoSQL document store, adding a new feature like color options can be done without a complicated migration process, while in a relational database, you'd need to alter the existing schema, which can involve considerable downtime. Scalability is another critical advantage. NoSQL databases are designed to scale out by distributing data across multiple servers, accommodating increases in load effortlessly. This horizontal scaling allows applications to manage high traffic, especially during peak times like sales events or product launches. For example, if your application begins to experience a surge in users, you can simply add more servers to your NoSQL cluster to balance the load. This is much more challenging in a traditional relational database, which typically requires vertical scaling, essentially upgrading the existing server's hardware. This ability to distribute data not only improves performance but also enhances availability. Many NoSQL systems are built with replication as a fundamental feature, ensuring data is copied across multiple nodes. If one node fails, another can pick up the slack, maintaining uptime and reducing the risk of data loss. Another important aspect is schema flexibility. With NoSQL databases, developers can store data types that would typically be cumbersome to fit into a rigid relational schema. This means developers can be more agile, releasing new features without cumbersome database migrations. Any new feature can have its own structure and adapt as required, which aligns well with agile development practices. However, it's crucial to note that the flexibility of NoSQL databases also requires a shift in mindset regarding data consistency. As we discussed earlier, NoSQL emphasizes eventual consistency over immediate consistency. This might be a challenging transition for teams used to the strict ACID guidelines of transactional databases. Considering this, it's essential for developers to implement strategies for data integrity and concurrency. Techniques like sharding, partitioning, and employing eventual consistency models are part of everyday practice in projects using NoSQL databases. Investing in solid monitoring tools to track data integrity and manage inconsistencies is also advised, helping ensure a smooth experience for users. To conclude our exploration of NoSQL databases, it's evident that these systems are tailored for modern data challenges. From scaling effortlessly to providing flexibility in data structure and high availability, NoSQL databases empower developers to create applications that are not only robust but also capable of adapting to rapid changes in data and user requirements. As more organizations shift towards big data solutions and real-time analytics, embracing these technologies will prove to be a game changer. In our next discussion, we will dive deeper into specific NoSQL database implementations, looking at their strengths, weaknesses, and the best scenarios for their use. Thank you for joining me today, and I hope this segment has given you a comprehensive understanding of the key concepts surrounding NoSQL databases. NoSQL databases excel in performance optimization, delivering exceptional read-and-write speeds that are crucial for modern applications. Today, we'll explore strategies to optimize performance in NoSQL systems and understand how to leverage their unique architectures to achieve better efficiency and responsiveness. So far, we learned that NoSQL databases provide flexibility, scalability, and performance to handle unstructured data, making them ideal for applications with dynamic requirements. We delved into the different types of NoSQL databases, including key-value stores, document stores, column family stores, and graph databases, each serving unique purposes. We emphasized the advantages of NoSQL, such as efficient data retrieval, ease of schema changes, and high availability through distributed systems. Now, we will talk about specific techniques for optimizing performance in NoSQL systems. Now let's take a look at how we can interact with a Redis database using Python to set and retrieve values efficiently. We begin by importing the Redis library, which enables us to communicate with our Redis server. Next, we establish a connection to the Redis server by creating a strict Redis client. We specify the host, port, and database number, ensuring we are connecting to the correct environment. Moving forward, we set a key-value pair by calling the set method on our Redis client. In this example, we store the user's name, Alice, associated with the key, user 1000. This operation occurs extremely quickly due to Redis's efficient in-memory storage architecture. Now let's see how we can retrieve the value we just stored. We use the get method to fetch the value associated with the same key. The result is returned as a byte string, so we'll decode it using UTF-8 to convert it to a regular string. Finally, we print the output in a user-friendly format, which clearly displays the user's name. This simple demonstration highlights the core functionalities of a key-value store and its responsiveness, a fundamental aspect that makes Redis a popular choice for applications requiring fast data access. Now let's implement a simple example to interact with a MongoDB database using Python. First, we begin by establishing a connection to the MongoDB server through the Mongo client class. This requires the URI of the MongoDB instance. In this case, we are connecting to a local instance running on the default port. Subsequently, we specify the database we want to work with, here named MyDatabase, and within it, we access the user's collection where our documents will be stored. Next, we will write the code to insert a user document into the user's collection. In this example, we create a dictionary representing a user with fields for name, age, and city, and then we utilize the insert1 method to add this document to the collection. After inserting the document, it's crucial to retrieve it to verify our insertion. For this, we use the findOne method with a query that filters documents based on the user's name. This operation fetches our recently added user document, demonstrating how easily we can store and query data in MongoDB. To optimize read operations in future queries, we will create an index on the name field. This can significantly enhance the retrieval speed, allowing our database to quickly locate the relevant document based on the queried attribute, which speeds up overall performance. Now let's see how we can implement write operations with eventual consistency in Couchbase. First, we establish a connection to the Couchbase server using the bucket class, specifying the desired bucket to store our documents. This connection allows us to interact with the database. Next, we write a document by using the insert method, where we specify a unique document ID and the data we want to store, in this case, user information including their name and age. Importantly, we include parameters for persist2 and replicate2, both set to 0. This signifies that we want to achieve eventual consistency by allowing the system to acknowledge the write operation without requiring immediate replication or persistence, thus boosting write performance. After the insertion, we then attempt to retrieve the document using the get method. However, as we've opted for eventual consistency, we acknowledge the possibility that the document may not be immediately available. We utilize a try-except block to handle the document not found exception, gracefully notifying us that the document might still be in the process of replication before it becomes accessible. This approach offers insights into how leveraging flexibility in consistency models can enhance write performance in NoSQL databases. Now let's implement the following function to demonstrate how data partitioning, or sharding, can be effectively managed in a NoSQL environment. The route to shard function takes a user ID as input and calculates which shard to route the request to, ensuring an even distribution of data. The process begins with a hashing operation on the user ID, which produces a unique hash value. We then apply the modulus operator with number of shards, which gives us the integer value of the shard that the user ID will be routed to. This method not only helps in evenly distributing users across multiple shards, but also minimizes bottlenecks when the application experiences high user traffic. To see this in action, we define the variable number of shards as 4, indicating that our data is distributed across 4 separate shards. Next, we input a sample user ID, user1001, into our function. Finally, when we call print on the route to shard function, it outputs which shard the user ID is directed to, helping us visualize how sharding works in practice and reinforcing the importance of load balancing in NoSQL database systems. The pie chart titled Performance Optimization Techniques in NoSQL Databases displays the relative emphasis of 5 techniques: indexing 30%, sharding 25%, eventual consistency 20%, concurrency control 15%, and monitoring 10%. Key patterns emerge from these proportions. Indexing is the single largest segment, indicating that efficient indexing is the most commonly prioritized technique for improving read performance and reducing query latency. Sharding is a close second, reflecting the critical role of partitioning to scale throughput and distribute load across nodes. Eventual consistency, at 1/5 of the chart, highlights that many NoSQL designs trade immediate consistency for higher write throughput and lower latency, while concurrency control, 15%, signals the necessary balance between performance and correctness when multiple clients update data. Monitoring, though the smallest slice, 10%, represents the foundational practice of measuring and validating the impact of the other techniques. From this distribution, we can conclude that a balanced strategy, focusing first on indexing and sharding while employing appropriate consistency models, concurrency patterns, and monitoring, is the most effective approach to optimize NoSQL systems for both speed and reliability. Now let's see how we can implement reading from a secondary replica in MongoDB to optimize our database performance. In a distributed NoSQL setup, using replica sets allows us to offload read operations from the primary instance. This code begins by establishing a connection to a secondary replica of the MongoDB database using the Mongo client class. By specifying the URI with the replica set name, we ensure that our application identifies and connects to the correct replica. Once connected, we access the desired database and collection, in this case, a database named MyDatabase and a collection named Users. This structure enables us to retrieve information about users stored in the collection effectively. The next step is executing a query to fetch a specific document by searching for a user named Alice. The findOne method is utilized here, which efficiently retrieves the first document that matches the criteria without scanning the entire collection. Finally, we print the result, allowing us to view the details of Alice's record. By shifting these read operations to secondary nodes, we can significantly enhance throughput and reduce latency, resulting in improved overall database performance. Now let's see how we can implement immutable document updates in a MongoDB setup to handle concurrency effectively. First, we establish a connection to the MongoDB server and select our desired database and collection for user data. We retrieve the current user's document based on their name, which allows us to access the existing state of that user. Next, instead of modifying the current document directly, we create a new document that represents the updated state. This new document includes an incremented age for the user while keeping the previous version in a field called Previous Versions. By storing the old state, we effectively avoid write conflicts, as this pattern accommodates multiple updates without compromising data integrity. Finally, we insert this new user version into the collection, ensuring that each change is tracked and the history of the user's modifications is preserved. This strategy is particularly useful in scenarios where multiple clients may attempt to update the document simultaneously, thus enhancing concurrency control and maintaining data consistency within the application. Now let's implement a script that logs slow queries to help us optimize our NoSQL database performance. We start by importing the necessary modules: time for measuring execution time and logging for recording slow queries. The logging is configured to display messages at the info level or higher. Next, we define the execute query function, which takes a query string as an argument. Inside this function, we use time to record the starting time before simulating a database query. In a real-world scenario, this is where you would execute your actual database query. We simulate a delay to mimic query execution time, during which we will check if the query takes longer than our predefined threshold of 0.4 seconds. If the query execution time exceeds this threshold, the script logs a warning, highlighting the slow query detected along with its details. This practical implementation allows us to focus our optimization efforts on specific queries that negatively impact performance. By monitoring and identifying slow queries, we can enhance the responsiveness of our application, ensuring a better user experience overall. To summarize, performance optimization in NoSQL systems requires a multifaceted approach. From understanding the underlying data model and implementing proper indexing to employing sharding and careful infrastructure choices, each consideration plays a crucial role in ensuring optimal performance. Keep monitoring and tweaking your performance strategies, and soon you'll be able to balance speed, reliability, and scalability in your NoSQL applications. Thank you for joining me in this deep dive into performance optimization in NoSQL systems. I hope you found this session informative and engaging as we navigated through essential techniques that will empower your development projects. Make sure to apply these strategies in your applications, and don't hesitate to experiment and measure your outcomes. Happy coding! When it comes to implementing NoSQL databases, there are some best practices that can significantly enhance performance, data integrity, and overall application effectiveness. In this session, we will dive into practical advice that will help you navigate the world of NoSQL effectively. So far, we learned that NoSQL databases offer flexibility and performance, particularly intended for unstructured data in dynamic applications. We examined different types of NoSQL databases, each with unique advantages for data retrieval and schema management, and discussed optimization strategies such as read and write operations, indexing, sharding, and fine-tuning consistency models. Effective performance monitoring tools and metrics are essential for maintaining database health and improving query efficiency. Our exploration covered practical coding examples to illustrate these concepts in real-world scenarios. Now we will talk about best practices for implementing NoSQL databases, focusing particularly on the trade-offs around limited transaction support. One of the first considerations when opting for a NoSQL database is the need to assess the specific requirements of your application. Collecting and analyzing your data access patterns will provide clarity on whether a NoSQL database is suitable for your use case. For instance, if you have an application that requires complex transactions with ACID compliance, a traditional SQL database might be more appropriate. On the other hand, if you're building real-time analytics applications or dealing with large volumes of unstructured data, NoSQL is often the way to go. The figure titled Best Practices for Implementing NoSQL Databases presents a horizontal bar chart that assigns an importance percentage to 5 practices: data integrity 35%, performance optimization 25%, scalability 20%, effective caching 10%, and monitoring 10%. The most prominent pattern is that data integrity is weighted highest, representing over 1/3 of the total importance and signaling that preserving correct, consistent data, even under eventual consistency, should be the primary focus. Performance optimization is the second priority, 25%, reinforcing the need for indexing, query tuning, and other optimizations described earlier. Scalability comes next, 20%, supporting the emphasis on sharding and horizontal scaling strategies. Effective caching and monitoring, while lower at 10% each, still represent necessary supporting practices. Together they account for 1/5 of the overall importance, indicating that once core integrity, performance, and scaling strategies are in place, engineers should invest in caching layers to reduce read load and in monitoring to detect and resolve bottlenecks. The percentage labels on each bar make the relative gaps clear, and the combined top 3 practices totaling 80% suggests a practical roadmap. Allocate primary engineering effort to data integrity, performance, and scalability first, then layer in caching and comprehensive logging monitoring to maintain and tune the system over time. Now let's see how we can implement a user profile update in MongoDB, focusing on version control to maintain data integrity in a NoSQL environment. We begin by establishing a connection to the MongoDB server and accessing the relevant database and collection for user data. Next, we identify the user we want to update by their unique user ID, allowing us to retrieve their current profile information. Rather than updating the document in place, we create a new version of the user's profile. In this updated profile, we preserve the user ID and increment the version number, ensuring we track changes over time. Additionally, we can modify other user attributes, such as the name and email, while also updating the age based on the current user's information. Finally, we utilize the update1 function to apply the changes, specifically replacing the previous version with the new one, which facilitates rollback if necessary and minimizes the risk of data conflicts. This strategy exemplifies how NoSQL databases can accommodate eventual consistency and provide a practical approach to maintaining data integrity in dynamic applications. Now let's implement a repository pattern for managing product data in our e-commerce application. This approach encapsulates database interactions, which simplifies our code and enhances maintainability. We start by defining a product repository class that takes a database connection as a parameter, allowing us to work with the products collection within that database. Within this class, we create the getProduct method, which retrieves a product by its unique product ID. This method uses a query to search through the collection and returns the product details, thereby abstracting the database query logic. Next, we have the addProduct method, which allows us to insert new product entries into the collection using the insert1 function. This method takes a product object as an input. Finally, we demonstrate the usage of this repository by instantiating product repository with our database connection. We call the getProduct method with a specific product ID, effectively fetching the product details in a clean and efficient manner. This structured approach not only promotes code clarity, but also ensures that any future changes to the database technology will require minimal adjustments to the application logic. Now let's see how we can implement a user document in a NoSQL database, specifically MongoDB, to demonstrate data modeling for enhanced performance. In this example, we create a user object that represents both the user details and their associated orders within a single document. The user object includes essential fields such as the user ID and name, along with an array of orders, where each order is represented as a subdocument containing an order ID and an amount. This denormalized structure offers several benefits, as embedding orders directly into the user document allows us to fetch all relevant information in a single read operation, improving performance in read-heavy scenarios common in e-commerce applications. By employing this approach, we minimize the number of read operations required to gather user order information, thus optimizing access patterns. After defining the user object, we can insert it into the user collection in MongoDB with a single operation, facilitating efficient data retrieval and aligning well with the best practices for NoSQL databases. This method showcases how thoughtful data modeling can yield significant performance advantages and simplified data access in dynamic applications. Now let's see how we can enhance query performance in MongoDB through indexing. Indexes are crucial for speeding up data retrieval and play a significant role in optimizing queries, especially when dealing with large data sets. In our example, we create an index on the email field of the user collection. By specifying create index, email 1, we indicate that we want to create an ascending index on the email attribute. This effectively allows MongoDB to organize and locate user documents by their email addresses much faster than scanning the entire collection. However, it is essential to remember that while indexing improves read operations, it can also have an impact on write performance. This is due to the overhead of maintaining the index during insertions or updates. Therefore, it is vital to monitor your application's performance both before and after adding indexes to determine their impact and ensure you strike the right balance between read and write efficiency. By continuously evaluating your indexing strategy, you can optimize both the speed of your queries and the overall responsiveness of your application. Next, we will implement a function to manage sharding user data effectively. The sharding process is essential for enhancing scalability in NoSQL databases by distributing data across multiple servers. In this function, shardUser, we take the user ID as an input and apply a hash function to determine which shard the user belongs to. Specifically, we use the hash function on the user ID, then apply the modulus operator with the total number of shards defined by number of shards. This approach ensures that user data is evenly distributed among the available shards, which can significantly improve load balancing and minimize the risk of overloading any one server. Once we calculate the appropriate sharded, the function returns a string indicating the designated shard for the input user ID. To illustrate this process, we define that we have 4 shards available and then examine a specific user ID, user 456. By executing our shardUser function with this user ID, we can observe which shard this user is routed to. This mechanism is crucial, especially in applications with growing user bases, as it maintains availability while facilitating efficient data retrieval and management. Now let's implement a caching mechanism using Redis to enhance the performance of our product retrieval process. In our code, we first import the Redis library and create a connection to a Redis server running locally. This connection allows us to interact with the caching system. Next, we define a function called getProduct, which takes a producted as its parameter. Within this function, we first attempt to retrieve the product from the cache using the cache.get method. If the product is found in the cache, we can return it immediately, which significantly speeds up access and reduces database load. However, if the product is not found in the cache, we proceed to query our database to retrieve the desired product information. We then store the retrieved product in the cache for future reference, allowing subsequent requests for the same product to be served directly from the cache. By implementing this caching approach, we optimize read operations and improve overall application performance, showcasing the advantages of integrating caching solutions with NoSQL databases. Now let's see how we can implement logging for query execution times in our NoSQL database interactions. The code begins by importing the logging module and setting the logging configuration to capture messages at the info level. This ensures that any logs we create are suitably detailed for monitoring purposes. We then define a function called executeQuery, which takes a query as an argument. Inside this function, we simulate the execution of a database query by recording the start time and then introducing a delay to mimic latency, such as what might occur in a real-world scenario. After the delay, we check the total execution time by calculating the difference between the end time and start time. If the execution time exceeds a threshold of 0.5 seconds, we log a warning indicating a slow query. This proactive approach allows developers to identify performance bottlenecks early. Finally, we invoke the function with a sample SQL-like query that fetches products priced under 100. By logging slow queries, we gain actionable insights to enhance database performance, ensuring our application can respond efficiently under load. To conclude, implementing NoSQL databases comes with unique advantages and challenges. It's vital to adopt best practices focusing on design patterns, data modeling, indexing, sharding, caching, and monitoring. By taking a thoughtful approach to these considerations, you can leverage the power of NoSQL effectively while ensuring your application remains performant and reliable. Keep experimenting and measuring the impact of these strategies on your application, and you'll find great success in your NoSQL endeavors. Happy coding! In today's discussion, we dive into the future trends in database management systems. With the exponential growth of the internet and the rise of big data, the demand for databases that can effectively scale, handle diverse data types, and manage high performance across distributed systems has become more critical than ever. So far, we learned that implementing NoSQL databases involves understanding their unique advantages and challenges, particularly around flexibility, performance, and scalability. We explored essential best practices like data modeling, optimization strategies, and the importance of indexing and sharding for efficient data access. Additionally, we emphasized the need for effective caching and comprehensive monitoring to maintain database health and performance. As we move forward, we will cover emerging trends and technologies that will significantly impact the landscape of database management systems in the coming years. Now let's see how we can implement a PostgreSQL database instance in a cloud environment using Terraform. In this script, we begin by defining the OS provider and specifying the region where we want to deploy our database, the US West region in this case. Following that, we configure the resource block for our PostgreSQL instance. Here, we allocate 20 gigabytes of storage for our database and choose PostgreSQL as the database engine, specifically using the version 12.4. This gives us a solid foundation for our database requirements. The instance class is set to dbt2 micro, which is a suitable choice for small-scale applications, providing a balance of cost and performance. We also give our instance a name, myPostgresDB, along with a username and password for accessing the database. Importantly, we reference a database subnet group and a security group to ensure that our instance is deployed within the correct network infrastructure and is secured against unauthorized access. Finally, we specify to skip the final snapshot, which is often a precautionary step when deleting a database instance. This concise setup encapsulates everything needed to automatically configure and deploy a PostgreSQL database in the cloud, streamlining your development process. The displayed bar chart titled Emerging Trends in Database Management Systems quantifies the relative impact of 5 trends: cloud-native solutions 30%, multi-model databases 25%, AI and ML integration 20%, data security 15%, and serverless architecture 10%. The bars are ordered left to right from highest to lowest impact, making it immediately clear that cloud-native solutions lead the projected influence on DBMS evolution. Multi-model databases follow closely, with a 5 percentage point gap from cloud-native, indicating they are the second most influential trend, but still notably behind cloud adoption. AI and ML integration sits in the middle at 20%, showing a strong but not dominant role in near-term changes. It is 10 points lower than cloud-native and 5 points lower than multi-model, suggesting substantial interest in embedding analytics and automation without eclipsing infrastructure shifts. Data security is marked at 15%, emphasizing that governance and protection remain critical priorities, albeit secondary to architectural and modeling changes. Serverless architecture is at 10%, reflecting a smaller but meaningful influence, particularly for cost-sensitive or highly variable workloads. Reading the exact data labels on top of each bar confirms these values, and the grid lines aligned with the y-axis help compare their magnitudes precisely. Taken together, the chart implies a strategic priority. Organizations should focus first on cloud-native transformations and multi-model capabilities, which together account for 55% of the represented impact, while concurrently investing in AI/ML capabilities and robust security measures, and considering serverless patterns where workload patterns and cost models make them advantageous. Now let's see how we can implement a products table in PostgreSQL to effectively manage multi-model data. In this example, we define a table named products that includes 3 columns: producted, name, and specs. The producted utilizes the serial data type, allowing PostgreSQL to automatically generate unique identifiers for each product, establishing it as the primary key. The name column, defined as a varchar 100, will store the product names with a maximum length of 100 characters. However, the most notable feature here is the specs column, which uses the JSONB data type. This allows for flexible storage of product specifications, accommodating varied structures such as key-value pairs and arrays. Next, we will populate this table with some initial data. By using the insert into statement, we add 2 products: a smartphone with attributes like screen size, battery capacity, and camera resolution, and a smartwatch, which includes its screen size, battery specification, and available features. This approach showcases how PostgreSQL enables seamless integration of structured and semi-structured data within a relational database, enhancing query flexibility and application development. Now let's see how we can analyze customer purchase patterns using a SQL query within our PostgreSQL database. The code provided performs a straightforward task. It identifies the most active customers over the past month by counting their orders. We start by selecting the customer ID and applying the count function to aggregate the order ID values for each customer. By filtering the data with the where clause, we restrict our attention to orders that have been placed in the last 30 days, leveraging PostgreSQL's built-in now function and the interval keyword to define this timeframe effectively. Next, we group the results by customer ID using the group by clause, which enables us to compile a summary of purchase activity on a per-customer basis. Finally, the results are organized in descending order with order by purchase count desk, ensuring that the most active customers appear at the top of our results. This query not only aids in tracking customer engagement, but serves as crucial input for targeting marketing strategies with machine learning algorithms tailored to forecast future buying behaviors. By harnessing this data, businesses can enhance their outreach and improve customer retention. Now let's see how we can implement role-based access control in PostgreSQL to enhance the security of sensitive data. First, we begin by creating a new role named Data Viewer, which will be responsible for viewing data. This role is granted the select permission on the sensitive data table, limiting its access to only reading the data rather than modifying it. This separation of responsibilities is vital for maintaining data security, as it ensures that users can only perform actions necessary for their roles. Next, we create another role called Data Editor, which is given permissions for data manipulation tasks, specifically insert, update, and delete on the same sensitive data table. By assigning different roles with appropriate permissions, we ensure that only authorized personnel can edit or delete the data they are entitled to, thus enhancing the management of sensitive information. This approach not only helps in compliance with data protection regulations, but also promotes accountability within the organization. Implementing such role-based access controls is a critical step in safeguarding data while adhering to security best practices. Now let's implement logical replication in PostgreSQL to ensure data consistency across different instances. To begin, we will create a publication on the primary database. This is done using the command that defines what tables should be sent to subscribers. In our case, we're focusing on the orders table, which means any changes to this table will be replicated to subscribers. By designating a publication, we enable efficient data sharing for distributed systems, which is advantageous for maintaining synchronization across multiple nodes. Next, we will set up the subscriber database. This involves creating a subscription that connects to the primary database using specific connection parameters, such as host, database name, user credentials, and the publication from which it will receive data. In our example, we are specifying a subscription to the MyPublication we just created. This setup is crucial because it allows the subscriber database to asynchronously replicate data changes from the primary database, thereby enhancing data availability and resilience. Overall, this configuration is integral to leveraging PostgreSQL's capabilities for distributed database environments in modern applications. Now let's implement a serverless database configuration using Amazon Aurora with PostgreSQL. The SQL command we will use initializes a serverless database named myserverlessDB, which leverages the PostgreSQL engine. One of the key features here is the declaration of dbunits as 2, which indicates the computational capacity allocated for our database. This capacity can adjust automatically based on incoming workload, thanks to the auto-scaling parameter being set to true. With this setup, as your demands fluctuate, spiking during high-traffic periods or dropping during lulls, the serverless database can scale seamlessly, providing high performance when needed while also optimizing costs when usage is low. This is particularly beneficial for applications where the workload is unpredictable, as it eliminates the need for manual server provisioning and management. By adopting this serverless architecture, developers can focus on building features rather than worrying about infrastructure, making it an efficient and cost-effective solution for modern cloud-native applications. In conclusion, the landscape of database management systems is undergoing substantial transformations driven by cloud computing, multi-model databases, AI, data security, blockchain technology, and serverless architecture. As these trends continue to evolve, it's critical for developers and organizations to stay informed and ready to adapt their database strategies accordingly. Each of these advancements brings with it opportunities for greater efficiency, security, and scalability, challenging conventions and creating better ways to manage and utilize data. By embracing these changes, you can help lead your organization into a data-driven future, ready to tackle the challenges and seize the opportunities that lie ahead. Happy exploring. Key-value stores are the simplest form of NoSQL databases, but don't let their simplicity fool you. They offer incredible flexibility and speed, making them a great choice for many applications. In this lesson, we will explore what key-value stores are, their structure, how to interact with them, and the differences between key-value and relational databases. So far, we learned about important trends shaping database management systems, and now we will cover the fundamentals of key-value stores, how they function, and when to use them effectively. Now let's see how we can implement our user data storage model in a PostgreSQL database. In this example, we begin by creating a users table designed to hold key information about each user. The userid column is defined as a serial type, which automatically generates a unique identifier for each new user entry, ensuring we have a primary key for reliable data retrieval. The username column is set to store usernames, and it is mandatory, as indicated by the not null constraint, ensuring each user must have a unique username. To enrich our user records, we also have a details column that uses the JSONB data type, allowing us to store user-related information in a flexible, structured format such as age and email. This design mimics the key-value store structure we discussed, where the username acts as the key to retrieve user details. Next, we populate the users table with an initial entry for the user with the username, user123. Here, we insert a JSON object as the value, illustrating how easily we can manage structured data in PostgreSQL. This setup offers a clear understanding of how similar key-value store capabilities can be accomplished using a relational database, while also highlighting the benefits of each approach. Now let's take a look at how we can interact with a Redis key-value store using Python. First, we establish a connection to the Redis server running on our local machine by creating an instance of the strict Redis class. We specify the host, port, and database index, enabling our application to communicate with the key-value store. Next, we move on to storing data by using the set method. In this instance, we create a key named user123, and assign it a JSON string containing information such as the user's age and email. This method is efficient, allowing for quick storage of user data without the need for a complex schema. Finally, we retrieve the information using the same key with the get method. Once we have the retrieved value, we decode it from bytes to string format for readability. This straightforward approach showcases how efficiently key-value stores can manage data retrieval and storage. By utilizing Redis in this way, we leverage its speed and simplicity, making it an excellent choice for scenarios where rapid access to data is crucial. Now let's take a look at how we can interact with Amazon DynamoDB, a popular key-value store, to perform basic operations such as adding and retrieving data. In the following example, we first import the Bodo3 library, which provides the necessary tools to connect and interact with AWS services, including DynamoDB. Next, we create a DynamoDB client by establishing a resource connection to the specified service. Here, we reference the user's table where our key-value pairs will be stored. When adding a new user, we utilize the putitem method, which allows us to insert an item represented as a dictionary. In this case, the key is the username, and the value is another dictionary containing user details, such as age and email. After inserting the data, we demonstrate how to retrieve it by using the getItem method with the key we specified earlier. This method fetches the associated item, and we print the result to see the details of the user we just added. It's crucial to bear in mind that due to DynamoDB's eventual consistency model, there might be a brief period where the data is not immediately reflected in subsequent queries. This functionality showcases the flexibility and operational model of key-value stores, particularly in distributed environments. The displayed figure is a grouped bar chart comparing performance ratings across 5 key features: speed, flexibility, complex queries, schemaless, and use cases, between key-value stores and relational databases. Each feature has 2 bars, one for key-value stores, 90 for speed, 85 for flexibility, 30 for complex queries, 100 for schemaless, 80 for use cases, and one for relational databases, 60 for speed, 70 for flexibility, 90 for complex queries, 40 for schemaless, 50 for use cases. From the chart, we can identify clear patterns. Key-value stores score substantially higher on speed, 90 versus 60, and schemaless capability, 100 versus 40, indicating their strong suitability for low-latency reads, writes, and flexible, evolving data models. Relational databases dominate complex queries, 90 versus 30, reflecting their strength in expressive querying, joins, and multi-table relationships. Flexibility is moderately higher for key-value stores, 85 versus 70, while use cases is also higher for key-value stores, 80 versus 50, suggesting broader applicability in scenarios that favor simple access patterns, caching, sessions, or high-throughput storage. The largest gaps appear in schemaless and complex queries, both 60-point differences, emphasizing the core trade-off: schema flexibility and raw speed versus advanced querying capabilities. In terms of practical conclusions drawn from the figure, it reinforces the lesson's guidance. Choose key-value stores for performance-sensitive, schema-flexible workloads, e.g., caching, session stores, real-time inventories, and choose relational databases when complex queries, data integrity, and relational joins are primary requirements. Now let's implement a simple inventory management system using a Python class that embodies the key-value store concept. We start by defining the inventory class, which initializes an empty dictionary to hold our inventory items, with producted as the key and quantity as the value. This allows us to store items without the constraints of a traditional database schema. Next, we create an addItem method, which takes producted and quantity as parameters. This method updates the inventory by either adding a new item or increasing the quantity of an existing product using the dictionary's get function, which simplifies the retrieval of a product's current quantity. This feature emphasizes the flexibility of key-value stores, enabling rapid updates without complex queries. We also include a getItemQuantity method that takes a producted to retrieve the corresponding quantity from the inventory. By encapsulating these functionalities within the inventory class, we maintain cleanliness and organization in our code. Finally, we demonstrate how to use this class by creating an inventory instance, adding an item, and printing its quantity, effectively illustrating the speed and efficacy of key-value stores in managing inventory data. Now let's see how we can implement a common query using SQL in a relational database like PostgreSQL. The code demonstrates how to retrieve usernames and corresponding product IDs from 2 related tables, users and orders. By utilizing a join, we create a relationship between these two tables based on userid, allowing us to efficiently combine and access related information. In the query, we specify the columns we wish to retrieve, user's username and orders producted. The join clause is crucial as it merges rows from the user's table with those in the orders table where the userid fields match. To filter results, we include a where clause, which limits the output to orders associated with a specific user, in this case, user 123. This approach illustrates the power and efficiency of relational databases in handling complex queries and relationships, showcasing how one can easily pull data from multiple tables with a single, straightforward SQL command. In contrast, achieving similar functionality in a key-value store would typically require more effort and potentially less elegant solutions. As we wrap up our exploration of key-value stores, it's vital to recognize their strengths and shared contexts with SQL and NoSQL databases. Key-value stores shine when the primary focus is on speed and flexibility. However, they come with their set of challenges and ideal use cases. In summary, we covered the basics of key-value stores, their structure, how to interact with them via various databases, and the differences and benefits compared to traditional SQL databases. Going forward, we will delve into specific use cases for key-value stores, real-world applications, and how to choose the right type of database depending on your project's requirements. In this video, we'll explore document data models, which are essential components of some NoSQL databases. We will discuss how data is structured and stored as documents, typically in formats like JavaScript Object Notation, JSON, and how this differs from traditional relational databases. So far, we learned about key-value stores as a simple yet powerful form of NoSQL databases that excel in flexibility and speed for high-volume data access. We discussed their structure, interaction methods through various technologies like Redis and DynamoDB, and the importance of understanding consistency and availability within the CAP theorem. Additionally, we explored the strengths of key-value stores compared to relational databases, including performance in low-latency scenarios and schema flexibility, as well as their limitations in complex querying situations. Now, we will talk about document data models and how they provide a more organized way to structure complex data. Now let's see how we can interact with a popular document store, MongoDB, using Python. We begin by establishing a connection to the MongoDB database through the Mongo client. This object allows us to connect to the specified database and create or access collections within it. In our case, we create or access a database named MyDatabase and a collection called Users, where we will store user documents. Next, we define a new user object that contains various fields, including user ID, name, email, and an array of addresses. This demonstrates how we can store complex hierarchical data within a single document. We then insert this user document into the user's collection using the insert_one method. Finally, we retrieve the newly inserted document by using the find_one method, providing the user's ID as the search criterion. By printing the retrieved user document, students can see the straightforward manipulation of documents in MongoDB, showcasing the ease of access to structured information while highlighting how document models can effectively handle nested data. Now let's see how we can implement the connection to our MongoDB database and perform some basic operations. First, we use the Mongo client class from the PyMongo library to establish a connection to our MongoDB server running locally. This connection allows us to access and manipulate various databases hosted on the server. Next, we specify a database named MyDatabase, which we will be using to store our data. Once we have access to the database, we interact with a collection called Users. A collection in MongoDB is similar to a table in relational databases where documents can be stored. We are going to insert a new user document which contains fields such as userid, name, email, and an array of addresses that represent the user's home and work locations. After inserting the user document, we employ the find_one method to retrieve the document based on its userid. This method returns the entire document we just inserted, showcasing the ease of retrieving complex data in a structured format. Finally, we print this document, which demonstrates how effectively we can manipulate and access data within a document store like MongoDB. Now let's see how we can update an existing user document to include a new field for phone numbers. We begin by utilizing the update1 method from the MongoDB collection, specifying the criteria for the document we want to update, in this case, identifying the user by their unique user ID, user123. Next, we employ the set operator, which is essential for adding the new phone numbers field. This field will be an array containing objects that represent different types of phone numbers, specifically mobile and home. Each object in the array consists of a type and a number, showcasing the capability of document stores to handle complex data structures within a single field. Once we perform the update, it's crucial to retrieve the modified document to verify the change. We accomplish this by using the findOne method once more, targeting the same user ID. By printing the updated user document, we can see the newly added phone numbers field integrated seamlessly with the existing user data, highlighting the flexibility provided by document data models. The figure titled Performance Comparison of Document Data Models versus Relational Databases presents a side-by-side bar chart across 5 key features: speed, flexibility, complex queries handling, schema flexibility, and nested structures. 2 series are shown: document data models in orange and relational databases in blue, with numeric performance ratings displayed above each bar. Reading the plotted values, speed is 85 for documents versus 60 for relational, flexibility is 90 versus 70, complex queries handling is 70 versus 40, schema flexibility is 95 versus 50, nested structures is 80 versus 60. Key patterns emerge. Document data models consistently score higher than relational databases on every listed feature. The largest gaps appear in schema flexibility, 95 versus 50, a 45-point difference, and complex queries handling, 70 versus 40, a 30-point difference, indicating that in this representation, document models are substantially stronger at adapting schemas and handling complex, nested query scenarios. Smaller but still notable advantages appear for speed, 25 points, and flexibility, 20 points, and a moderate lead in representing nested structures, 20 points. From these values, we can conclude that the plotted data emphasizes document models' strengths in schema evolution and nested data representation, while also showing broad advantages in throughput and adaptability. Relational databases, as shown here, trail across these specific metrics. This visual summary supports the lesson's discussion about why document stores are often chosen for use cases requiring flexible schemas and rich, nested documents. Next, let's take a look at how we can structure a blog post along with its comments in a document-based format, utilizing JSON to represent our data. In our example, we define a JSON document that describes a blog post with fields like posted, title, and content. This structure allows us to provide a clear overview of the blog post, capturing key aspects of its content and identity. Crucially, we also include a comments array, which houses multiple comment objects. Each comment contains relevant data such as the user ID of the commenter, the actual comment, and a timestamp to indicate when the comment was made. This nested structure exemplifies the flexibility inherent in document data models, as it enables us to keep related information, like comments, directly within the blog post document itself. Storing the entire blog post, along with its associated comments, in a single document facilitates efficient data retrieval. When we query the database for a blog post, we can fetch all related comments with one simple query, thus optimizing performance and reducing the complexity that would arise when working with separate collections and needing multiple joins in a relational database. Now let's see how we can implement a validation function for user data before inserting it into our document store. The validate user data function is designed to ensure that all required fields, specifically user ID, name, and email, are present in the incoming user data. This is crucial because, unlike relational databases that enforce schema constraints in a document model, it is the application's responsibility to manage data integrity. The function iterates over the list of required fields and checks for their existence in the user data dictionary. If any field is missing, it raises a value error, clearly indicating which specific field is absent. This approach helps maintain a uniform structure among the documents being inserted, mitigating potential issues later during data retrieval or processing. Next, we have an example of user data that includes the necessary fields. Prior to inserting this new user document into the user's collection, we call our validation function within a try-except block. This not only ensures that the required data is verified before insertion, but also handles any potential errors gracefully, outputting the error message if a validation issue arises. This method establishes a reliable way to enforce data integrity within your document-oriented application. Now let's look at how we can implement a dynamic user profile using a Python script. The createUserProfile function is defined to accept a dictionary of user data, ensuring any data passed meets the validation criteria with the validateUserData function before insertion. This step ensures that all essential fields like user ID, name, and email are present, which is crucial for maintaining data integrity in document stores. Next, we create an example of a dynamic user profile in the form of a dictionary. This profile includes the user ID, name, preferences like theme and notification settings, and an empty array for posts. This showcase illustrates how easy it is to tailor a user document to individual requirements, reflecting the flexibility of document data models. By calling the createUserProfile function and passing this structured data, we insert the new user profile into the database seamlessly. This approach not only demonstrates managing user profiles, but also exemplifies the adaptive nature of document stores, where changes or additional fields can be readily accommodated without disrupting existing data. As we wrap up our discussion on document data models, it's clear that these systems present a compelling alternative to traditional relational databases for many use cases. With their inherent flexibility and capacity to handle complex structures effortlessly, document stores are beautifully suited to environments that need scalability and rapid evolution. In our current lesson, we discovered the core principles behind document data models, how to manipulate documents using Python and MongoDB, and the advantages and trade-offs these models present. Understanding how to leverage document stores will prepare you for real-world applications demanding efficient data handling. In the next session, we will explore specific use cases and practical applications of document data models, equipping you with the knowledge to choose the right database strategy for your projects. Keep exploring and coding, and I look forward to seeing you in our next lesson. Column family stores are a unique type of NoSQL database that offer a different way of organizing and storing data. Unlike traditional databases that use rows and tables, column family stores group related data into column families, making them particularly well suited for handling large volumes of sparse data. In this video, we will explore the architecture of column family databases, their advantages, and practical applications. So far, we learned about key-value stores as a flexible and efficient NoSQL database option and examined their structure and limitations. We then transitioned to document data models, which store data in organized, self-contained documents that allow for hierarchical relationships and complex queries. The advantages of document models include schema flexibility and ease of managing nested data, making them suitable for applications requiring rapid changes and scalability. Looking forward, we will cover column family architecture and how it can be utilized in various use cases. Now let's see how we can implement a user profile in our column family store. The code describes the structure of user data stored in the profile column family, highlighting the flexibility of this architecture. Here, each user is defined by a unique row key, enabling us to differentiate between users effortlessly. For instance, user 101 has attributes such as a username and email, which are basic yet essential fields, while user 102 showcases the versatility of the column family design by including an additional website attribute. This illustrates a vital feature of column family stores, the ability to have varying sets of columns for each row. This means that not every user needs to share the same attributes, allowing for a more tailored data storage solution that adapts to user requirements. As we proceed, we can see how this flexibility supports rapid application evolution and helps maintain the efficiency of read and write operations essential in a social media applications context. The examples provided here lay the groundwork for understanding how data can be structured and manipulated within a column family architecture, setting the stage for further implementation details as we delve deeper into the system. The displayed figure is a side-by-side bar chart comparing performance ratings across 5 key features: flexibility, scalability, high availability, performance, and ease of use, between column family stores and relational databases. For every feature shown, column family stores score higher. Flexibility is rated 90 versus 60 for relational systems, a 30-point gap. Scalability 85 versus 70, 15-point gap. High availability 80 versus 50, 30-point gap. Performance 95 versus 65, 30-point gap. And ease of use 75 versus 40, 35-point gap. Visually, the taller bars for column family stores indicate a clear and consistent advantage across these dimensions, with the most pronounced relative differences in ease of use, performance, flexibility, and high availability. From these values, we can conclude that column family architectures are particularly strong when applications demand high throughput and distributed availability, while relational databases lag notably in ease of use and resilience at scale. This alignment reinforces earlier points about why column family stores are often chosen for large-scale, high-performance, and fault-tolerant systems. Now let's examine how to establish our data model in Apache Cassandra by creating a keyspace and a table for managing user profiles. First, we start by creating a keyspace named social media. This serves as the fundamental unit for data organization in Cassandra, similar to a database in traditional relational systems. We specify the replication strategy using a simple configuration for fault tolerance, ensuring that our data is adequately replicated across nodes. Next, once we switch to using the social media keyspace, we proceed to create the profiles table, defining its structure. The userid column is set as the primary key, which uniquely identifies each profile. By declaring it as a UUID type, we guarantee that each identifier is unique and efficient for querying. Additionally, we include columns for username, email, and website, which will allow us to store essential user information corresponding to their profiles. Now, let's implement the user profile insertion process using the insert statement. We can easily add new user profiles, utilizing the UUID function to automatically generate unique identifiers for each user, thereby streamlining the process of populating our profiles table. This approach highlights the simplicity and efficiency of managing data in a column family database like Cassandra. Now let's implement the following command to set our consistency level for write operations in Cassandra. The command consistency quorum is used to ensure that a write is only deemed successful when a majority of the nodes in the cluster have acknowledged the write request. This approach balances the need for strong consistency with the system's availability, as it reduces the chance of reading stale data by requiring more nodes to confirm changes before they are considered valid. By specifying a quorum, we are optimizing for reliability and accuracy, which is particularly crucial when dealing with critical data where precision matters. This setup is part of Cassandra's tunable consistency model, which allows developers to choose how strict or lenient they want the data consistency to be based on their specific application requirements. Ultimately, by using this consistency level, we can assure our applications of a higher degree of data integrity across the distributed database setup, which is essential in maintaining trust and functionality within our systems. Now let's see how we can implement our IoT temperature logging system using a column family store. We begin by creating a table named device temperatures, which is designed to efficiently store temperature records from various IoT devices. Here, deviceid is chosen as a UUID to serve as the primary key, uniquely identifying each device. This allows us to pull data related to specific devices seamlessly. Next, we include a timestamp column which will act as a clustering key. This enables our table to support multiple temperature entries per device over time, allowing for a chronological record of temperature readings. The temperature column is designated as a float to accommodate decimal values, ensuring we can capture slight variations in temperature. Lastly, a status column is added as text to log the operational state of each device, which can vary based on its reporting capabilities. Once our table structure is set up, we can swiftly insert sensor data. The insert into statement allows us to log temperature readings along with a timestamp and the device's status. This flexibility means we don't need to fill in all columns for every entry, accommodating situations where devices may not report their status consistently. Now let's see how we can implement a query to analyze temperature data for our devices. This SQL statement calculates the average temperature recorded for a specific device within a defined timeframe. We start by selecting the average temperature from the device temperatures table. By including the where clause, we specify the device we're interested in by its unique identifier, which allows us to filter the results effectively. The query further narrows down the dataset by bounding the timestamps, ensuring that only temperature readings from the first day of September 2023 to the last day of the same month are considered in the calculation. This flexibility in focusing on specific columns and criteria exemplifies the strength of column family stores in executing analytic queries. As you experiment with your own device data, you can change the Your Device ID placeholder to match the actual device ID you want to analyze, enabling you to retrieve meaningful insights about temperature variations over time. This ability to aggregate data dynamically showcases the power of the column family architecture in facilitating in-depth analysis while maintaining efficient query execution. However, it's important to acknowledge the downsides of column family stores as well. One trade-off to keep in mind is that while they scale efficiently and provide high availability, the complexity of managing consistency across distributed databases can escalate. Developers need to establish thorough testing and monitoring systems to ensure data integrity is being upheld, especially when performing write and read operations at varying consistency levels. Another consideration is that column family databases generally require a deep understanding of the data access patterns. In contrast to relational databases that allow ad hoc queries with ease, with column family stores, you often have to plan your data model according to how your application will query the data later. As we wrap up our exploration of column family architecture, it's evident that they are tailored for a wide range of applications that necessitate scalability, flexibly structured data, and rapid speed of access. Whether dealing with user data in apps, logging sensor outputs in IoT, or even managing product catalogs in e-commerce, column family stores like Cassandra provide robust solutions for handling complex, varied data requirements without the overhead of strict schema enforcement typical of traditional relational databases. Keep in mind the trade-offs and strengths we discussed here, as they will help you make informed decisions about when to leverage column family architecture in your projects. In our next session, we will dive into specific use cases and practical applications of column family databases, further equipping you with the skills needed for real-world implementations. Keep exploring, keep coding, and I look forward to seeing you in our next lesson. NoSQL databases have become crucial in modern application development, especially when it comes to handling vast amounts of data efficiently. A vital aspect of these databases is their approach to consistency, which directly affects how data is accessed and modified. Today, we will dive deep into evaluating consistency models in NoSQL databases, exploring the trade-offs between availability and partition tolerance. We'll break down different consistency levels, their implications, and provide code examples to illustrate these concepts in popular NoSQL databases. So far, we learned that column family stores are a type of NoSQL database organized into columns rather than rows, optimizing data handling for sparse datasets. We discussed their advantages, including schema flexibility and fault tolerance, as well as their strong performance in high-throughput applications like IoT and analytics. Additionally, we explored how to manage data using Apache Cassandra, including creating key spaces and tables, inserting data, and utilizing tunable consistency models. Moving forward, we will examine practical applications and use cases of column family databases in real-world scenarios. To kick off our discussion, let's clarify what we mean by consistency in the context of NoSQL databases. Consistency refers to the guarantee that the data is the same across all nodes in a distributed system. This means, regardless of when or where a client accesses the data, it reflects the most recent write operation. However, achieving absolute consistency can come at the cost of availability, especially in distributed environments where network partitions might occur. This creates a fundamental tension among three properties known as the CAP theorem: consistency, availability, and partition tolerance. In practice, NoSQL databases often prioritize either availability or consistency, leading to various consistency models. The important consideration here is that you cannot achieve all three properties simultaneously in a distributed system. The CAP theorem definitively states that you can only reliably guarantee 2 out of these 3. Once you understand this, the next step is to explore the various consistency levels in detail. Now let's see how we can implement a data insertion operation in Cassandra using eventual consistency. In this snippet, we insert a new user profile with the user ID, name, and email address. Here, the command specifies the target table, user profiles, which reflects our application's user data model. The values clause conveys the actual information we want to store, with 1234 as the user ID, Alice as the user's name, and alice@example.com as the email address. What's noteworthy in this example is the use of using consistency 1. By using this consistency level, we instruct Cassandra that only one replica needs to acknowledge the right operation for it to be considered successful. This choice enhances the system's availability, making it more resilient in scenarios where not all nodes are accessible. However, it also introduces the risk that, should another client attempt to read this data immediately after the insert, they may not yet see Alice's profile depending on the replication timing. This behavior exemplifies the trade-offs involved in the eventual consistency model, where immediate accuracy can be sacrificed for improved availability. Now let's take a look at how we can ensure strong consistency in a database transaction using Spanner. The code begins with the statement to initiate a transaction, laying the groundwork for a series of operations that must be executed atomically. Following this, we perform an insert operation into the user profiles table, where we add a new user with a specific user ID, name, and email address. This step is crucial because it defines the data that will be written to the database. The key element here is the use of the commit statement, which signals that all operations within the transaction block should be finalized. Until this point, the insert has only been a pending operation, and the transaction remains incomplete. By requiring a commitment of the transaction before any reads can occur, Spanner guarantees that only the most recent data is accessible across all nodes in the cluster. This behavior exemplifies strong consistency, ensuring that once the right operation is acknowledged, any subsequent reads will reflect this latest state, thereby maintaining data accuracy throughout the system. Now let's see how we can implement a write operation in Cassandra with a specified consistency level. The code provided demonstrates how to insert a new user profile into the user profiles table. This operation includes a user ID, name, and email for the user Charlie. Importantly, we specify the consistency level using the using consistency quorum clause. By choosing quorum, we ensure that the write operation will only be considered successful once a majority of the nodes in the cluster have acknowledged the insertion. This approach strikes a balance between data accuracy and availability, as it gives us strong assurance that the data has been reliably recorded across the nodes. However, it's crucial to understand the implications of setting this consistency level. While quorum helps maintain robust data accuracy, if your data model or application logic doesn't align with this requirement, it could lead to slower transaction rates. Therefore, carefully evaluating the necessity of this consistency level in relation to your application's needs is essential for optimal performance in a distributed database environment. The figure titled Evaluating Consistency Models in NoSQL Databases presents a bar chart with performance ratings on a 0-100 scale for 5 consistency models. Strong consistency 90, read-your-writes 85, tunable consistency 80, eventual consistency 75, and monotonic reads 70. Clear ordering shows strong consistency scoring highest, followed closely by read-your-writes and tunable consistency, which form a mid-high cluster around the 80-85 range. Eventual consistency and monotonic reads occupy the lower end of the scale but remain above 70. From these values, we can conclude that models providing stricter guarantees, strong consistency, are rated highest in this evaluation, while models that relax guarantees, eventual and monotonic reads, score lower. The relatively small spread, 20 points between highest and lowest, suggests trade-offs are nuanced rather than extreme. Tunable and read-your-writes approaches offer a balance between accuracy and responsiveness, whereas eventual and monotonic approaches emphasize availability or read progression at the cost of lower performance rating in this assessment. The numeric labels on each bar make the comparisons explicit, and the y-axis range, 0-100, confirms these are normalized performance ratings, allowing direct interpretation of how each model ranks against the others. Now let's implement a feature using DynamoDB that demonstrates read-your-writes consistency in a social media application. First, we initiate a write operation to store a new post in the posts table. This action is performed using the put method, where we specify the table name and the item containing the user's ID, the post ID, and the content, in this case, Hello World. Once this write operation is complete and acknowledged by the database, we can proceed to ensure that the user sees their newly created post immediately. Next, we initiate a read operation to fetch the same post we just wrote. we use the get method, specifying the same table name and the key that uniquely identifies the post we want to retrieve. To ensure we achieve read-your-writes consistency, we include the parameter consistentRead set to true. This guarantees that we retrieve the most recent version of the post, allowing the user to view their update right after submission. By carefully structuring our write and read operations in this way, we enhance user satisfaction while highlighting the importance of design considerations to balance performance with responsiveness. Now let's see how we can implement a monotonic reads approach to keep track of document revisions in our application. The code begins by fetching the current version of a specified document using the getLatestDocumentVersion function. This establishes a baseline version that we are currently viewing. Next, we await an event that signifies the document has been updated by invoking waitForDocumentUpdate. This function will pause our code execution until the new version is ready, ensuring that we only handle fresh information. Following the update event, we again call getLatestDocumentVersion to retrieve the most recent version of the document. By comparing the latest version with the version we initially fetched, we can determine if changes have been made. If we find that the latest version is indeed greater than the current version, we log a message indicating that there is a new document update available. This logic guarantees that users are informed about any updates while preventing them from seeing outdated information, thereby maintaining a seamless and intuitive experience when interacting with the document. Through this implementation, we can effectively manage and display version data in a way that meets user expectations. Evaluating the various consistency models in NoSQL databases includes weighing the trade-offs of each based on the application needs. Strong consistency offers absolute accuracy at the expense of availability, while eventual consistency provides higher responsiveness but requires patience for synchronization. Tunable consistency allows developers to define data behavior on a case-by-case basis, tailored to specific user interactions. In practice, choosing the right model will vary according to specific use cases and expected workloads. Factors include how critical it is for clients to access the most recent data, the stakes involved in potential stale reads, and how frequently data is being updated. This understanding will empower you to design with intention, harnessing the right balance for your unique applications while leveraging the strengths of the NoSQL paradigm. As we wrap up this discussion on evaluating consistency models in NoSQL databases, consider how these concepts intertwine with practical implementations. In our next session, we'll delve deeper into advanced techniques for data modeling and querying strategies that leverage these consistency models effectively. Keep coding, keep exploring, and I'm excited to see where this journey takes you. NoSQL databases have rapidly become the go-to choice for developers looking to meet the demands of modern applications. Their flexibility and scalability make them an appealing alternative to traditional SQL databases. In this lesson, we'll delve deep into understanding data models in NoSQL, equipping you with the knowledge needed to design and implement effective database solutions tailored for dynamic environments. So far, we learned that consistency in NoSQL databases is crucial for ensuring data accuracy across distributed systems, and achieving it involves trade-offs among consistency, availability, and partition tolerance, as summarized by the CAP theorem. We explored various consistency models, including eventual consistency, strong consistency, tunable consistency, read-your-writes consistency, and monotonic reads, each with its advantages and implications for application performance. Understanding these models allows developers to tailor data behavior based on specific needs, ensuring the right balance between performance, accuracy, and user experience. Moving forward, we will focus on advanced techniques for data modeling and querying strategies that effectively leverage these consistency models. When talking about NoSQL data models, we first need to recognize that they can be grouped into several categories: document-based, column family, key-value stores, and graph databases. Understanding these models will guide our decisions on how to structure our data, keeping in mind that NoSQL's flexibility allows us to adapt as requirements evolve. The figure presents a simple comparative bar chart titled Understanding NoSQL Data Models that quantifies the relative usage or importance of four NoSQL models: document-based 30%, column family 45%, key-value 25%, and graph 40%. Key patterns are immediately evident. column family databases register the highest value at 45%, indicating their strong relevance for large-scale distributed workloads where wide row or time series patterns and efficient write-read throughput are critical. Graph databases follow closely at 40%, highlighting the significant role of relationship-centric use cases, social graphs, recommendations, traversals, where connectedness and traversal performance drive model choice. Document-based stores sit at 30%, reflecting their balanced utility for flexible, nested, schema-evolving data structures that benefit many application domains, but may be less dominant in specialized high-throughput or relationship-heavy scenarios. Key-value stores are shown at 25%, underscoring their niche strength in ultra-low latency access patterns such as caching, session stores, and simple lookup needs rather than complex queries. From these proportions, we can draw practical conclusions for design decisions. Prefer column family models when horizontal scalability and bulk analytical or time series access are priorities. Choose graph models when relationships and path queries are central. Use document stores for evolving, hierarchical entities, and rely on key-value stores when speed and simplicity outweigh complex query requirements. The numeric labels on each bar make these distinctions clear and help map workload characteristics to the most suitable NoSQL model. Now let's see how we can implement a collection of user documents in MongoDB. In this snippet, we use the insert many method of the DB users collection to add multiple records simultaneously. Each document represents a user with various fields that include the user's name, age, hobbies, and address, showcasing the flexibility of document-based databases. For example, notice how we can include an array for hobbies, allowing users to list multiple interests without needing a rigid schema. Additionally, the address field is structured as a nested document, encompassing further details like street, city, and zip code, illustrating how easily we can represent complex data relationships. This schemaless nature allows us to evolve our data structures flexibly as application requirements change. By enabling the incorporation of diverse data types and hierarchies within a single document, MongoDB empowers developers to create rich, intuitive data representations that align with the dynamic nature of modern applications. This approach, free from the constraints of traditional relational databases, enhances both the development process and the ability to adapt as projects grow. Now let's implement the user activity log in Cassandra, a crucial step in capturing user interactions over time. We start by creating a table named User Activity that organizes different attributes of user activities. This table includes a unique identifier for each user, the date of the activity, and the type of activity performed. The combination of userid and activity date serves as the primary key, ensuring that each entry is distinct and allowing for efficient querying based on these attributes. Next, we recognize that as our application evolves, there may be a need to store additional information, such as the device type users are utilizing. To accommodate this without significant schema changes, we can simply alter our existing table by adding a new column for device type. This flexibility encapsulates the essence of column family databases, where schema evolution does not require complex migrations, enabling us to quickly adapt to new logging requirements as they arise. This approach significantly speeds up development while carefully maintaining the integrity of our data, reflecting the advantages that NoSQL databases like Cassandra bring to managing dynamic datasets. Now let's take a look at how we can implement a simple key-value operation using redis, a popular key-value store. In this example, we use the set command to assign a unique user ID, user1000, to the string Alice Johnson. This command effectively creates a key-value pair, where user1000 serves as the key pointing to the value Alice Johnson. Key-value stores like redis excel in scenarios where fast retrieval of data is crucial, such as in caching user sessions or quick lookups. Following this, we utilize the get command to retrieve the value associated with the key, user1000. This operation is designed for speedy access, demonstrating the efficiency of redis in fetching quickly the stored data, an essential feature for real-time applications. This straightforward approach allows developers to manage frequently accessed data without complex queries, thus improving overall user experience by minimizing latency. By directly using these commands, we see how redis can simplify data management and enhance performance in applications where speed is a priority. Now let's see how we can manage user relationships in a social networking application using Neo4j's Cypher query language. We'll begin by creating two user nodes, Alice and Bob, along with defining their attributes such as name and age. This is achieved through a single create statement that not only sets up the user nodes, but also establishes a directional relationship between them labeled friends with. This graph structure allows us to visualize and traverse relationships easily, showcasing the power of graph databases in handling interconnected data. Next, we will implement a query to find all friends of a specific user, in this case Alice. By using a match statement, we can retrieve all nodes connected to Alice through the friends with relationship. This query efficiently demonstrates the simplicity and expressiveness of Cypher, allowing us to focus on the relationships and paths, rather than the complexities of join operations found in traditional relational databases. With this approach, querying relationships becomes straightforward, enhancing both performance and ease of understanding in our data modeling efforts. Now let's see how we can implement sharding in MongoDB to enhance data distribution and application performance. The command shard collection, a database users userid 1 is used to shard the user's collection based on the userid field. Sharding is an essential feature in NoSQL databases, particularly when dealing with large datasets, as it allows data to be spread across multiple servers. By directing MongoDB to partition the user's collection using the userid, each entry is divided into smaller, more manageable chunks. This distribution facilitates better load balancing and increases data availability, especially during high-traffic scenarios. When an application dynamically handles numerous users, the application benefits from improved scalability without running into performance bottlenecks. With sharding, you can add more machines to your database cluster, ensuring that as the number of users grows, the database can efficiently support a seamlessly scalable application. Therefore, implementing sharding becomes a strategic move to ensure your application remains responsive and reliable under heavy loads. In summary, effective data modeling in NoSQL is about knowing the strengths and weaknesses of each type of database. Understanding document, column family, key value, and graph databases helps impel your application to new heights concerning flexibility, scalability, and performance. Having covered the basics of various NoSQL data models, the next step is ensuring you know how to leverage these structures effectively through proper querying techniques and advanced design practices, enabling you to make data-driven decisions and optimizing your applications for success. As we adapt to the needs of modern applications, the NoSQL landscape continuously evolves, challenging us to rethink data management and discover innovative ways to harness the power of diverse data types. The model you choose today can set the stage for how effectively your applications perform tomorrow, so choose wisely, design smartly, and embrace the limitless possibilities of NoSQL data models. The CAP theorem is a fundamental concept in the design and implementation of distributed systems, particularly in NoSQL databases. Understanding the implications of the CAP theorem is essential for developers and architects seeking to build robust, scalable applications. So far, we learned that NoSQL databases offer flexibility and scalability for modern application needs, with various data models like document-based, column family, key value, and graph databases serving different use cases. Each model has its strengths, such as the rich representation in document databases, the schema evolution in column family databases, the simplicity of key value stores, and the relationship focus in graph databases. We also discussed the significance of consistency models in NoSQL, highlighting the balance between performance and accuracy in data management. Moving forward, we'll explore the CAP theorem and its implications in distributed systems, helping us understand the trade-offs between consistency, availability, and partition tolerance. So far, we learned that NoSQL databases offer flexibility and scalability for modern application needs, with various data models like document-based, column family, key value, and graph databases serving different use cases. Each model has its strengths, such as the rich representation in document databases, the schema evolution in column family databases, the simplicity of key value stores, and the relationship focus in graph databases. We also discussed the significance of consistency models in NoSQL, highlighting the balance between performance and accuracy in data management. Moving forward, we'll explore the CAP theorem and its implications in distributed systems, helping us understand the trade-offs between consistency, availability, and partition tolerance. The radar chart titled Trade-offs in the CAP Theorem displays three axes corresponding to consistency, availability, and partition tolerance, with plotted scores of 75%, 85%, and 90% respectively. Visually, the filled polygon extends furthest toward partition tolerance, 90, slightly less toward availability, 85, and least toward consistency, 75, indicating a design emphasis on maintaining operation during network partitions while still keeping the system largely available. Interpreting these values against the CAP trade-offs, the high partition tolerance combined with high availability suggests a leaning toward an AP-style approach where systems remain responsive under partitions, but the lower consistency score signals a willingness to accept eventual or weaker consistency guarantees. From a practical perspective, this pattern aligns with architectures that prioritize continued service, for example, social or user-facing applications, and tolerate temporary divergence across replicas, whereas workloads demanding strict correctness, such as financial transactions, would find the lower consistency score problematic and might instead push the design towards CA under controlled network conditions. The chart's percent scale gives a quick quantitative comparison of priorities and reinforces the earlier discussion about how system designers must choose which two properties to emphasize when all three cannot be fully achieved simultaneously. Let's first define what the CAP theorem is. Proposed by Eric Brewer in the early 2000s, the theorem states that in distributed data stores, you can only guarantee 2 out of 3 of the following properties at any given time: consistency, availability, and partition tolerance. This means that you have to make strategic decisions about what aspects of your application you want to prioritize based on your specific use case. To clarify these concepts, let's break down each component of the CAP theorem. Consistency means that every read receives the most recent write for a given piece of data. Imagine you have a bank application. If you check your account balance, you want to see it updated in real time, reflecting any recent transactions. If your application sacrifices consistency, you might read an outdated balance, which could lead to severe issues, especially in financial transactions. Next is availability. Availability means that every request receives a response about whether it succeeded or failed. In a highly available system, even if some parts of the system fail, you should still be able to access your data. Taking our bank application example again, if the system is unavailable, you wouldn't be able to check your balance or perform transactions. Finally, we have partition tolerance. This refers to the system's ability to function correctly even when network partitions occur, meaning that some nodes cannot communicate with others. In other words, if your application can still operate despite network issues, it demonstrates partition tolerance. Since network failures are inevitable, most distributed systems must prioritize this feature. Now that we have defined each component, let's delve into how these properties interact with one another in distributed systems. Let's suppose you are building an application and decide to prioritize consistency and availability. In scenarios where a network partition occurs, your system would have to sacrifice either consistency or availability, as the theorem asserts that you cannot achieve all three. For example, consider a distributed database like Couchbase. When there's a network partition, Couchbase may deny access to a portion of the system, prioritizing consistency over availability. Users might experience downtime or inability to read writes until the partition is resolved, ensuring that reads are always accurate when accessed again. Now let's see how we can implement a simple table structure for managing user accounts in PostgreSQL. We start by creating a table named Accounts that will store each user's account information. This table has 2 columns: accounted, which is a unique identifier for each account generated automatically using a serial data type, and balance, which stores the amount of money in the account as a numeric value. Next, we will learn how to update a user's balance. To do this, we can issue an SQL command that subtracts a specific amount, let's say 100, from the balance of a user identified by their accounted. This operation is crucial for maintaining accurate records after transactions. It's important to note that if this update occurs simultaneously with another request to read the balance, the result will depend on the consistency model in place. With strong consistency, the system ensures that reads see the most recent writes by locking the table during the transaction, whereas in an eventually consistent model, a user may read an outdated balance if the update has not been propagated yet. Understanding these dynamics is essential for managing data accurately in distributed environments. Now let's see how we can implement tunable consistency in Cassandra by utilizing the quorum setting for our database operations. In the code snippet, we start by setting the consistency level with the command consistency quorum. This configuration ensures that read and write operations require acknowledgement from a majority of the replicas in the cluster before a successful response is returned. Following this, we perform an insert operation into the accounts table, where we create a new account with an ID of 1 and a balance set to 500. The combination of setting the consistency level to quorum and executing this insert command highlights how Cassandra balances consistency and availability. By requiring that most replicas confirm the write, we reduce the likelihood of stale data being read or written, while still ensuring the system remains available to handle requests. This feature is particularly useful in distributed environments where maintaining accurate data across nodes is crucial, especially when network partitions occur. In this way, developers have the flexibility to choose their desired balance between consistency and availability based on the needs of their applications. Now let's see how we can implement a basic item update operation in Amazon DynamoDB using the Oz SDK for Python, known as Boto3. In our example, we start by importing the Boto3 library, which allows us to interact with DynamoDB easily. Next, we create a resource object for DynamoDB, establishing a connection to the service. After that, we specify the table we're working with, in this case, the accounts table. The updateItem method is crucial here. It is used to modify an existing item in the table. We specify the primary key, which identifies the item we want to update, in this case, the accounted of 1. We then define an update expression, which indicates the modification we want to make. In this example, we set the balance attribute to a new value of 500. Finally, the return values argument allows us to specify what information we want the operation to return after the update. Here, using updated new ensures we receive the updated balance after the operation, giving us instant feedback on the change made. This operation exemplifies how to use DynamoDB's capabilities to manage data flexibly while accepting the inherent trade-offs of eventual consistency. Another important aspect to consider is how developers can test and monitor their systems to understand and manage the implications of the CAP theorem. Implementing logging and metrics are fundamental practices. By monitoring metrics such as read-write latencies and error rates, you can assess whether your chosen strategy aligns with user expectations. Implementing alerts can notify you when availability drops or when consistency checks that verify data across replicas fail. Utilizing tools like Prometheus or Grafana for real-time monitoring helps provide insights that inform you whether your application is behaving as intended under different loads and conditions. In summary, choosing between consistency, availability, and partition tolerance in distributed systems necessitates careful consideration based on your application's requirements. The CAP theorem encourages developers to understand the implications of their design decisions, empowering them to create robust, resilient architectures. As we wrap up our exploration of the CAP theorem, it's clear the interactions among consistency, availability, and partition tolerance are pivotal in shaping the behavior of distributed systems. Engaging with various NoSQL databases provides insight into how these properties are managed. By leveraging the right architectural choices and monitoring, developers can navigate the challenges posed by the CAP theorem, ensuring applications deliver the optimal balance of performance and reliability. In our next discussion, we will dive into advanced querying techniques and best practices for leveraging NoSQL data models effectively, enhancing our understanding and application of these technologies. Get ready to build on what we've learned and explore that exciting terrain. In our discussion today, we will analyze the base transaction model in NoSQL databases and how it contrasts with the traditional ACID model. This understanding is vital for anyone working with distributed systems and looking to leverage the strengths of NoSQL technologies. So far, we learned that the CAP theorem highlights the trade-offs between consistency, availability, and partition tolerance in distributed systems. We defined each component, emphasizing the necessity to prioritize certain aspects based on application needs. Additionally, we discussed how various NoSQL databases approach these trade-offs, using examples to illustrate the implications of design choices. Moving forward, we will explore a different side of transactions in distributed systems, specifically the base model. The displayed horizontal bar chart, titled Key Aspects of the Base Transaction Model in Nosql, quantifies the relative importance assigned to each base component, basically available 85%, soft state 65%, and eventually consistent 75%. The pattern is clear: basically available scores highest, indicating that system availability is the primary design objective in the represented context. Eventually consistent sits at an intermediate level, showing that designers treat convergence across replicas as an important goal, but not ahead of immediate responsiveness. Soft state receives the lowest score among the three, implying that while the system acknowledges transient or changing state, it is comparatively less emphasized when allocating design priorities. The numeric labels on the right of each bar make the differences explicit: a 20-point gap between basically available and soft state, and a 10-point gap between basically available and eventually consistent, and likewise between eventually consistent and soft state. From these values, one can conclude that the overall architectural trade-off favors responding to requests and tolerating temporary divergence, while still investing in mechanisms that ensure eventual reconciliation of data across nodes. Let's delve into what the base model actually stands for. BASE is an acronym for basically available, soft state, and eventually consistent. Unlike ACID transactions, which ensure strong consistency and immediate visibility of transactions, BASE takes a more relaxed approach to consistency in favor of improved availability and partition tolerance. This approach is particularly beneficial in distributed systems, where maintaining strict ACID properties can significantly hamper system performance and user experience. The first component, basically available, means that the system guarantees availability of data most of the time. In practice, this means that even during system failures, data requests will be responded to, though the response may not reflect the latest data state. Consider a social media application where user posts are updated frequently. If you were to query for posts, you might retrieve older data during a peak load or network partition. However, users still expect the application to provide responses, meaning that maintaining availability is priority number one. Now let's take a look at how we can create a table in a Cassandra database to store user login information. The code uses the SQL Cassandra query language and begins with the command to create a new table named users. Within this table, we define two key columns, userid and last login. The userid column is of type UUID, which ensures that each user has a unique identifier, crucial for distinguishing between different users in the system. By designating this column as the primary key, we enforce data integrity and enable efficient lookups. The second column, last login, is defined as a timestamp data type, which allows us to store the exact date and time when the user last logged in. This information is vital for tracking user activity and managing session states in applications. Cassandra's flexible schema allows us to build scalable applications that may require updates to this table over time, demonstrating its adaptability in the context of the base model, where responsiveness and availability are prioritized while maintaining the capability to manage data consistency eventually. Now let's see how we can implement user login updates in a Cassandra database as part of our exploration of the base model. In this snippet, we begin by importing the necessary cluster class from the Cassandra library, which allows us to connect to a Cassandra cluster. We establish a connection by creating a cluster instance and specifying the address of the local node. For this example, we assume the node is hosted at 127.0.0.1. Once the connection is established, we connect to a specific keyspace, here referred to as your keyspace, which is essential because it defines the database context in which our operations will occur. After connecting, we prepare to update the last login timestamp for a user. The timestamp is set to the current time using the now function in SQL, ensuring that each time a user logs in, the latest timestamp is stored. The session execute method is crucial here. It executes the update command that modifies the last login field for the specified user based on their unique ID. This approach exemplifies how we allow for eventual consistency, as it may take time for other nodes to reflect this change, but the system remains responsive to user requests in the meantime. Now let's see how we can insert a user document into a MongoDB collection using Python. We start by establishing a connection to the MongoDB server running locally on our machine at port 27017. This is done using the Mongo client, which is part of the PyMongo library. Once connected, we specify the database we want to work with, referred to as your database in this example, and select the user's collection where we will store our user documents. Next, we insert a new user document into this collection. The document includes a unique userid and a last login timestamp. Using datatime now, we capture the current date and time as the last login information. This operation is performed by calling insert1 on our collection, which performs the write operation quickly without blocking read operations. This behavior illustrates the soft state characteristic of the base model, allowing other users to access existing data even while new entries are being added. Thus, the application remains fast and responsive, showcasing the advantages of using MongoDB in a NoSQL context. Now let's see how we can simulate an ACID transaction using PostgreSQL, a relational database that adheres to ACID principles. The code begins with the begin statement, which initiates a transaction, signaling that the subsequent operations should be treated as a single unit of work. This means that all changes made can either fully succeed or fully fail together. Next, we have two update statements. The first updates the balance of an account by subtracting 100 from the account with accounted equals 1. This would represent a withdrawal transaction. The second update statement adds 100 to the account with accounted equals 2, simulating a deposit transaction into another account. These operations are crucial in financial systems, where you want to ensure that money is properly transferred from one account to another without allowing any intermediate states where funds might appear to be in two places at once. Finally, the transaction is concluded with the commit statement, which makes all the changes permanent in the database. If an error were to occur at any point between begin and commit, the entire transaction could be rolled back, ensuring that no partial updates are reflected in the database. This approach guarantees data consistency and integrity, which are key in scenarios like banking transactions. However, when developing applications that need to operate at scale and prioritize user experience, the base model offers flexibility that can be crucial. Designing applications that inherently manage the eventual consistency aspect allows for faster user interactions. This model encourages developers to think about how their data can be designed in such a manner that real-time updates are not always necessary. So, how do developers implement this relaxation of consistency effectively? Monitoring is key. Leveraging tools such as distributed tracing can help ensure that data is synchronizing across nodes and that eventual consistency goals are being met. Such observability ensures that even if transient inconsistencies appear, corrective actions can be taken before they impact user experience significantly. We should also consider using hybrid approaches, where certain parts of the application adopt ACID properties while others utilize base principles. This is feasible when different components of an application have varied requirements. A payment service might adhere to ACID to ensure transaction integrity, while a recommendation engine can thrive on base, where real-time data isn't as crucial. Eventually, understanding the architecture will guide you on how best to integrate these paradigms to meet your application's needs. For instance, suppose you're using a microservices-based architecture, where one service handles transactions while another manages user profiles. By applying ACID to your transaction service and base to your user profile service, you can achieve a scalable solution that meets both integrity and responsiveness. As we conclude our discussion on the base transaction model in NoSQL databases, we've expanded our understanding of how these characteristics differ from traditional ACID transactions. Basically available, soft state, and eventually consistent concepts enhance user experience in distributed systems, especially when prioritizing performance and availability over strict consistency. In our future discussions, we will dive deeper into advanced querying techniques and best practices for efficiently leveraging NoSQL data models. Understanding base is just the tip of the iceberg in this exciting journey into NoSQL databases, and I can't wait to explore more on this topic with you. Stay tuned. Now let's see how we can implement a query to suggest products to a user based on the purchases made by their friends. The code uses the Cipher query language to traverse relationships in the graph database, specifically focusing on a user named Alice. In this query, we start by matching a specific node representing Alice, denoted as user name, Alice. From Alice, the query traverses the friends with relationship to find her friends, represented by the variable friend. This allows us to retrieve all nodes that are connected as friends. Next, we continue the traversal from each friend to the products they have purchased through the purchased relationship. By doing this, we form a path that connects Alice to the products her friends have bought. The return distinct product name part of the query ensures that the results list only unique product names, avoiding duplicates. This approach allows for efficient retrieval of relevant products through direct relationships, showcasing the graph database's strength in handling interconnected data and enhancing the user experience with personalized recommendations. Now let's see how we can query for the friends of a user in a graph database using Neo4j. This particular cipher query showcases the simplicity and elegance of traversing relationships in a graph model. By starting with a specific user, Alice, we first identify her immediate friends through the friends with relationship, represented as friend. Next, we extend our search to include friends of these friends, which we label as FOF. The query is structured to ensure that we retrieve distinct names of these friends of friends, which effectively eliminates any duplicates from the results. This approach allows us to easily understand and visualize the connections within the social network without needing complex joins, as would be necessary in a traditional relational database. This method of querying not only enhances readability and performance as more users are added, but also illustrates the natural way in which graph databases handle interconnected data, making complex relationships more intuitive to explore. Now let's implement the following query to introduce a new relationship type within our graph database. In this example, we will denote a like action between a user and a post. Specifically, we are targeting a user named Alice, who we want to represent as having liked a post identified by an ID of 1. The match clause of our query allows us to locate both Alice and the post by their respective properties. By specifying user name, Alice, and post id, 1, we're clearly defining the nodes we wish to work with. Once both nodes are identified, we utilize the create statement to establish a new relationship, represented by the dotted arrow syntax, liked, connecting Alice to the post. This approach exemplifies the flexibility of graph databases, as we can easily extend the model without the need for altering existing database structures or creating new tables, showcasing real-time adaptability. The simplicity of this operation supports rapid feature development, aligning perfectly with modern agile application methodologies while effectively enhancing the social dynamics represented in our application. The displayed bar chart titled Impact of Graph Databases in Various Applications quantifies perceived importance across 4 application categories: social dynamics 90%, recommendation systems 85%, fraud detection 80%, and flexible schema 75%. The bars are ordered and labeled along the x-axis with their respective percentage values shown directly above each bar, making the ranking and magnitudes explicit. Key patterns: social dynamics has the highest importance score at 90%, followed closely by recommendation systems at 85%, then fraud detection at 80%, and finally flexible schema at 75%. The differences between adjacent categories are modest, generally 5 percentage points, indicating consistently high relevance of graph databases across these domains rather than a single dominant use case. From these values, we can conclude that relationship-centric applications, social dynamics, and recommendations are rated slightly more impactful than fraud detection and flexible schema, but all 4 areas score well above typical mid-range values, supporting the general suitability of graph databases for these problems. The visualization thus reinforces prioritization, emphasize features and optimizations that benefit social graph traversals and recommendation logic first, while recognizing that fraud detection and flexible schema capabilities remain important and valuable. Now let's see how we can implement a query to identify potentially fraudulent transactions involving large amounts using a graph database. In this example, we will utilize the Neo4j query language cipher to model the relationships between users, transactions, and accounts. The query starts by looking for users who have made transactions, which are represented by the made relationship connecting the user node to the transaction node. We specifically want to focus on transactions with an amount greater than $10,000, which is a common threshold for identifying suspicious activities in financial systems. This is achieved through the where clause, filtering our results based on the transaction amount. The next part of our query returns the names of the users alongside the corresponding accounts involved in those high-value transactions. This allows fraud analysts to trace the connections back to potentially fraudulent accounts quickly. By following this path through the database, users can efficiently pinpoint relationships that warrant further investigation, showcasing the powerful capabilities of graph databases in fraud detection. Now let's implement the following indexing command designed to optimize performance in our graph database. The command createIndexOn user name creates an index on the name property of nodes labeled user. Indexing is crucial because it enables faster lookups and queries, particularly in datasets with a large number of nodes. When querying for user information, searching by name can be significantly accelerated by this index, allowing the database to quickly locate relevant records rather than scanning through all user nodes sequentially. This is especially important in scenarios with a growing user base, where efficient querying becomes essential for maintaining performance and responsiveness. By preparing our database with this index, we are not only enhancing the speed of queries that filter by user names, but we are also laying a foundation for a scalable application that can handle the demands of intensive data operations with greater efficiency. Thus, employing indexing best practices is a vital step in optimizing the performance of graph databases as they evolve and expand. Lastly, let's touch on the various graph database management systems available today. Some well-known systems include Neo4j, ArangoDB, and Amazon Neptune, each offering unique capabilities and features. Neo4j, for instance, is often favored for its robust API and user-friendly query language, while ArangoDB supports multi-model operations, allowing for flexibility in handling different data types. Choosing the right graph database ultimately depends on your application requirements, community support, ease of use, and performance characteristics. It's crucial to evaluate these factors using empirical data from your use cases to ensure you're adopting the best solution for your needs. In conclusion, graph databases offer an exciting and powerful alternative for managing data, especially where relationships are key. They excel in scenarios requiring quick relationship traversal, adaptive schemas, and intuitive querying. As we've explored, using graph databases not only enhances application performance but also simplifies complex data interactions, making it a go-to choice for many modern applications. As we progress, we'll delve into more advanced querying techniques and best practices for harnessing the full potential of graph databases and their capabilities. From optimizing performance to implementing robust security measures, the journey through the world of graph databases will continue to unravel exciting possibilities. Stay tuned for our next lesson, where we will take a closer look at advanced querying techniques in graph databases, equipping you with skills to leverage their full potential in your applications. Scalability is undeniably one of the most significant advantages offered by NoSQL databases. Unlike traditional relational databases that can struggle under heavy load, NoSQL systems are designed to grow and exploit parallel processing. In this video, we will dive deeper into how NoSQL databases achieve this remarkable scalability and why it makes them the go-to choice for modern applications. So far, we learned that graph databases enable scalability and maintain high performance in complex scenarios, such as social dynamics and recommendation systems. Now, we will cover how NoSQL databases architecture supports horizontal scaling and why this is crucial for handling large volumes of data in real time. Now let's take a look at how we can implement sharding in our NoSQL database, specifically in MongoDB. The command shard collection, datacorp comments, userid1 is instrumental in partitioning the comments collection based on the user ID. This effectively initiates the sharding process, allowing the database to distribute user comments across different servers based on the userid field. By doing this, we enable a more balanced workload for the database, as each server will handle only a subset of the data related to specific user IDs. For example, if users are assigned to servers with ranges of IDs, it prevents any single server from becoming overwhelmed with requests. This seamless distribution of data is crucial for maintaining high performance and availability, particularly as user traffic increases. In essence, this command sets the groundwork for horizontal scaling, ensuring that as Datacorp grows and collects more user-generated content, their database remains efficient and responsive, ultimately fostering a better user experience. The bar chart titled Key Concepts of NoSQL Scalability quantifies the relative impact of 5 core concepts: sharding 30, replication 25, flexibility 20, high throughput 15, and caching 10. The data show a clear descending order of impact, with sharding and replication together representing the majority share, 55 of the total 100 when summed, emphasizing that partitioning data and maintaining redundant copies are primary drivers of scalable behavior. Flexibility holds a substantial, mid-level role, indicating that schema adaptability remains important for evolving workloads. High throughput and caching, while lower in numeric impact on this chart, still contribute meaningfully. Throughput supports large volumes of writes and reads, and caching reduces load on persistent stores. The numeric labels on each bar make the relative differences explicit, allowing us to conclude that design priorities for scalability should typically focus first on robust sharding schemes and replication topologies, then on flexible data models and throughput optimization, and finally on targeted caching strategies to alleviate hotspots. Now let's see how we can implement replication in MongoDB to ensure data redundancy and maintain high availability. The first command, rs initiate, initializes a new replica set, which is a group of MongoDB servers that maintain the same data set. When you run this command, it sets up a primary node that receives all write operations and allows secondary nodes to replicate the data from this primary node. Next, we will write the following commands to add additional nodes to the replica set. Using rs add datacorp replica 127,017 and rs add datacorp replica 227,017, we can incorporate 2 secondary nodes into our set, which will keep copies of the data from the primary node. This configuration ensures that if the primary node fails, due to hardware issues or other failures, one of these secondary nodes can automatically take over, allowing users of Datacorp to continue posting comments without any noticeable downtime. This process enhances the system's fault tolerance and operational continuity, crucial for maintaining an uninterrupted user experience. Now let's take a look at how Datacorp can leverage the flexibility of a NoSQL document database to store richly structured user comments alongside media files. This example illustrates the adaptive nature of NoSQL databases, which enable organizations to evolve their data models seamlessly. In this JSON structure, we define a comment object that includes 3 key attributes: userid, comment, and media. The userid uniquely identifies the user submitting the comment, allowing for easy association with individual profiles. Following this, we see the comment attribute, which contains the text of the user's feedback, showcasing the significant role that user-generated content plays in the application. The most noteworthy part of this structure is the media attribute, which is an object itself. This attribute accommodates additional media types, evidenced here by the inclusion of an image with its type and URL. It demonstrates how NoSQL databases can effortlessly incorporate various data formats without needing a rigid schema. As new features are developed, such as the ability to include video comments or other media types, Datacorp can expand its database model to accommodate these changes, ensuring it remains agile and scalable in response to user needs. In a NoSQL database like Apache Cassandra, efficiently managing user comments is essential for sustaining performance during peak traffic periods. We can achieve this by utilizing an insert statement, which illustrates an SQL-like command crafted for adding a new comment to the comments table. The command employs a clear syntax that includes the table name, comments, along with the fields to be filled, userid, and comment. This format explicitly directs the database on what data is being inserted into which columns. For instance, by designating the user ID as 12,345 and the comment as "this is awesome," we distinctly indicate both the comment's origin and its content. This procedure demonstrates Cassandra's high throughput capabilities, enabling numerous transactions to occur simultaneously across its distributed system. It also emphasizes the advantage of its peer-to-peer architecture, where each node is equipped to handle requests independently, ensuring that the user experience remains smooth and responsive, even during significant load times. Now let's implement a caching mechanism using Redis to enhance our NoSQL database's performance by storing frequently accessed data. First, we need to establish a connection to the Redis server. In the code, we initiate a connection to the local Redis instance by specifying the host, port, and database index. This step is crucial as it allows our application to communicate with the caching system. Next, we will cache a specific comment by using the set method of the Redis client. Here, we are saving a comment identified by the unique key, comment12345. The value we are storing is the text, "This is awesome." This approach is efficient. When a user requests this comment in the future, our application can retrieve it directly from the cache rather than querying the backend database. This not only speeds up response times significantly, but also reduces the load on the Nosql data store, allowing it to manage other data that might not be accessed as frequently. Through caching, we optimize performance and improve user experience, showcasing a fundamental aspect of Nosql scalability. Considering all these elements together, sharding, replication, flexibility of the data model, high-throughput transactions, and caching, it's clear why NoSQL databases have become a preferred choice for companies looking to scale quickly and manage large volumes of data efficiently. They allow businesses to grow without a corresponding increase in complexity or infrastructure costs. As organizations depend more on their data, the ability to scale both horizontally and vertically becomes essential. While NoSQL databases shine in horizontal scaling by letting businesses add more machines easily, they also ensure that, as data needs grow, they can maintain performance levels, becoming a fundamental asset in data-driven decision-making. In summary, we delved into the various facets of NoSQL scalability, from architecture and data modeling to system performance under heavy loads. So far, we've learned how these aspects contribute to making NoSQL an advantageous option for modern applications. In our next lesson, we will discuss data consistency in NoSQL databases, which is equally important as scalability in building robust and reliable systems. Let's dive into the fascinating world of transactions in NoSQL databases, particularly focusing on the base model. Unlike the traditional ACID transactions we're used to in relational databases, NoSQL databases employ a more flexible approach that helps them achieve high availability and scalability. Today, we'll explore how this fundamental shift affects how data operations are handled, making transactions efficient even when dealing with large and diverse datasets. So far, we learned that NoSQL databases offer significant scalability advantages over traditional relational databases through a distributed architecture that utilizes sharding and replication. This enables efficient management of large datasets and provides high availability, as seen in the example of DataCorp using MongoDB and Apache Cassandra. The flexibility to handle various data models and high-throughput transactions further supports NoSQL scalability. Now we will cover how transactions work in NoSQL databases, highlighting the base model's characteristics and its implications for data consistency and application design. The heart of our discussion today is the concept of base, an acronym for basically available, soft state, and eventually consistent. This contrasts sharply with ACID, which stands for atomicity, consistency, isolation, and durability, the gold standard for transactional systems. While ACID places a premium on strict data integrity and consistency, the base model adopts a more relaxed approach that accommodates the desired high availability and scalability of NoSQL technologies. Let's break down what these terms mean specifically. Basically available signifies that the system guarantees availability, meaning requests can be fulfilled most of the time, even if the system cannot return a valid response concerning all data. This is particularly useful in distributed systems where some nodes might become unreachable. The goal here is to prioritize the ability to retrieve some data over the need for complete accuracy at any given moment. Soft state refers to the notion that the state of the system may change over time, even without new input, indicating that data may exist in multiple states across different nodes. This aligns perfectly with the dynamic nature of distributed databases, where updates and changes may proliferate at different rates across the network. Eventually consistent is perhaps the most critical concept in base. It suggests that while immediate consistency may not be guaranteed after a transaction, the system will converge to a consistent state given enough time. This is a significant shift from ACID, where strict consistency must be assured before concluding a transaction. The displayed chart is titled Key Characteristics of Base Transactions in NoSQL and breaks down the three base attributes into proportional emphasis, basically available at 40%, soft state at 35%, and eventually consistent at 25%. The pie segments sum to 100%, explicitly showing the relative weight assigned to each characteristic. Key patterns visible are that basically available is the largest single slice, 40%, indicating the greatest emphasis on availability in base-minded designs. Soft state is close behind, 35%, highlighting that transient or variable state across nodes is nearly as important as availability. And eventually consistent, while essential, is the smallest slice, 25%, suggesting that immediate convergence is less prioritized relative to availability and tolerance for soft state. From this distribution, we can conclude that designers of base systems typically trade stronger immediate consistency guarantees for higher availability and acceptance of temporary variable state, an explicit visualization of the design priorities discussed in the text. Now let's discuss how we can implement a user profile update in a NoSQL database like Cassandra. We begin by establishing a connection to the Cassandra cluster, allowing us to interact with our data stored within a specific key space. This is crucial for any database operation, as it sets up the context in which we'll be working. Next, we define a function called updateUserProfile, which takes a userid and a new email as parameters. This function constructs an update query that modifies the email address of a user, identified by the given user ID. It's important to note the use of parameterized queries here, which not only helps in preventing SQL injection attacks, but also streamlines the execution process. Once we execute the update command through the session, we provide feedback by printing a message that confirms the update's success. However, remember that while this operation appears seamless, the eventual consistency model means that some replicas may still have the old data momentarily until all nodes are updated. This reflects the fundamental principle of base, highlighting how the system prioritizes availability while acknowledging potential temporary inconsistencies across the distributed database. Now let's take a look at how we can insert a recommendation into our NoSQL database, which plays an essential role in dynamically updating a user's recommendations based on their activity. The function insertRecommendation accepts two parameters, userid and productid. These parameters will be used in our query to add a new entry into the recommendations table. Within the function, we construct an SQL insert statement formatted to include the user ID and product ID. By executing this query through the session, we are not only inserting the new recommendation, but also ensuring a swift update in our database without waiting for any previous operations to complete. This showcases the base model's flexibility, as it allows us to handle multiple transactions simultaneously, embracing the possibility of presenting initially inconsistent data. After executing the query, a confirmation message is printed, indicating that the recommendation has been successfully inserted for the user. This practical approach aligns perfectly with our e-commerce scenario, where immediate updates can enhance user experience, even if the recommendations are momentarily based on stale data. Thus, as users continue to interact with the system, the data will gradually converge towards accuracy. Now let's implement a function to retrieve the latest recommendations for a user, which aligns perfectly with the base model's philosophy of prioritizing speed and responsiveness. This function, named getLatestRecommendations, takes in a user ID as a parameter and constructs a query to fetch product IDs from the recommendations table specifically for that user. Using the session object that connects to our Cassandra database, the function executes the SQL-like query, substituting the userid to ensure accuracy in fetching data. The result, which consists of the rows returned from the query, is then transformed into a simple list of product IDs. This list represents the recommendations that the system has access to, reflecting the current state of the recommendations data, even if it may not be perfectly current at the moment of retrieval. To demonstrate its functionality, we call this function with a sample user ID of 1 and print out the latest recommendations. This approach allows users to receive timely suggestions based on available information, exemplifying the base trait of flexibility in delivering data while sacrificing the strict consistency guaranteed by traditional systems. Now let's implement a versioning model for a comment system. In this implementation, each comment includes a timestamp that records the precise moment it was added, which is critical for managing data freshness in NoSQL applications under the base model. We begin by defining a function, insert comment, which takes two parameters, the userid and the comment text that the user wishes to submit. Inside the function, we capture the current date and time using datatime now, ensuring that each comment is tagged with an accurate timestamp. This timestamp serves as an essential tool for differentiating between stale and fresh data, allowing the system to track and display comments based on their recency. The SQL query used here inserts the user ID, comment text, and timestamp into the comments table of the database. After executing the query, we print a confirmation message that indicates a successful insertion, displaying both the user ID and the timestamp. This informative feedback not only allows developers to trace actions, but also reassures users that their contributions are being captured in the system. This method of incorporating timestamps enhances overall user experience by enabling the application to present timely and relevant feedback. Moving forward, it is essential to remember that embracing the base model necessitates a flexible mindset. Developers adopting NoSQL paradigms need to adjust their application architectures to accommodate the inherently different approach to transactions. Design patterns for NoSQL often revolve around understanding and accepting that immediate consistency is not achievable, and focusing efforts on achieving durability and availability instead. In conclusion, we've explored the nuances of base transactions and how they contrast with conventional ACID approaches. We've seen how adopting base allows for agility, scalability, and high availability, qualities that are invaluable in today's data-rich environments. As developers, our responsibility lies not only in executing transactions efficiently, but also in designing applications that thrive in this eventual consistency landscape. So now you're ready to implement your very own base strategies in NoSQL applications. Embrace the challenges, design with user experience in mind, and keep iterating to build systems that are both robust and responsive. Next, we will delve into the topic of data consistency in NoSQL databases, emphasizing its critical role alongside scalability. In this session, we will explore the implications of design choices in NoSQL databases, focusing specifically on the CAP theorem. This theorem, proposed by Eric Brewer in the early 2000s, has become a cornerstone in understanding the balance between three key properties: consistency, availability, and partition tolerance. So far, we learned that the base model in NoSQL databases prioritizes availability and scalability over immediate consistency, contrasting sharply with the traditional ACID model. Key characteristics of base include being basically available, allowing for soft state, and eventually achieving data consistency. This flexibility enables developers to create responsive applications that can manage large datasets without facing performance bottlenecks associated with strict data integrity. Next, we will focus on the crucial topic of data consistency in NoSQL databases and its interplay with scalability. The CAP theorem posits that in a distributed data store, you can only simultaneously guarantee two out of the following three properties: consistency, availability, and partition tolerance. This concept encourages developers to think critically about the trade-offs they must make when designing systems. To elaborate, let's consider each property in detail. Consistency means that every read receives the most recent write or an error. In other words, all nodes in the distributed system reflect the same data at the same time. Availability, on the other hand, guarantees that requests will receive a response, whether it's successful or failed. Finally, partition tolerance indicates that the system continues to operate despite an arbitrary number of message losses or failures that partition the system. The displayed radar chart titled Implications of the CAP Theorem in NoSQL Design maps the three properties, consistency, availability, and partition tolerance, onto a single polygon and shows distinct numeric emphasis for each axis. Consistency at 70, availability at 85, and partition tolerance at 75. Visually, the filled polygon is pulled furthest toward the availability axis, indicating a clear prioritization of availability over the other two properties. Partition tolerance is the next strongest axis, and consistency is the least emphasized. From this pattern, we can conclude that the design choice represented favors systems that remain responsive under load or partial failure, high availability, while still maintaining a substantial tolerance for network partitions, moderate partition tolerance, but accepting weaker immediacy of consistency, lower consistency. This configuration implies trade-offs such as a higher likelihood of eventual consistency and the use of replication or asynchronous updates to keep nodes available. It also suggests designers may accept stale reads in favor of uninterrupted service. The geometric shape, a lopsided polygon skewed toward availability, succinctly communicates these priorities and underscores the practical engineering decision to opt for responsiveness and partition resilience over strict, immediate data uniformity. Now let's see how we can implement the red committed isolation level in our PostgreSQL database. This isolation level allows transactions to read data that has been committed but does not block other updates, which is crucial for maintaining availability in systems where data is frequently updated. To start, we set the transaction isolation level by using the command set transaction isolation level red committed. This ensures that all subsequent queries within the current transaction will adhere to this isolation level. It effectively strikes a balance between being responsive to user requests and safeguarding data integrity, albeit with a slightly reduced consistency guarantee. Following the setup of the isolation level, we then execute a SQL query to retrieve the available quantity of a specific product identified by its producted. This query allows us to fetch the most current available data without waiting for other potential transactions to complete, embodying the principles of availability and responsiveness in our e-commerce platform. However, we must remain cautious, as this approach may expose us to the risk of reading stale data if updates are still in process. Now let's implement a transaction that ensures a money transfer between two accounts is handled with strict consistency. We begin by marking the start of the transaction with begin, setting the stage for the operations we are about to perform. This way, all subsequent changes will occur in isolation, ensuring that no other transactions can interfere until our operation is completed. Next, we set the transaction isolation level to scralizable, which is the strictest form of isolation in PostgreSQL. This guarantees that our transactions will behave as though they are executed one after another, thereby maintaining consistent data across all nodes in the database. We then proceed to deduct money from the first account by executing an update statement that subtracts a specified amount from the account balance. After updating the first account, we immediately follow with another update statement to add the same amount to the second account's balance. Finally, we conclude the transaction with commit, which permanently applies our updates to the database. This whole process exemplifies how to ensure data integrity in critical financial transactions where any inconsistency could lead to disastrous outcomes. Next, we will write the following SQL commands to demonstrate the implementation of a locking mechanism in a content management system. We start by initiating a transaction with begin, which marks the beginning of our series of database operations. The subsequent select statement retrieves the text of the article with a specific articleid, and the addition of forUpdate ensures that this row is locked. This is critical because it prevents any other transactions from modifying or accessing this article until our current transaction is complete. This way, we guarantee that all changes made during this transaction will be visible to any readers accessing the article, thus maintaining data consistency. Following this, we strategically place an update statement to modify the content of the article to updated article text. After making our changes, we conclude the transaction with commit, which finalizes the updates and releases the lock on the article. This simple yet powerful series of commands exemplifies how we can prioritize consistency in our application, ensuring that users always access the most current version of the content at the potential cost of temporarily reduced availability during the locking period. Now let's implement a function that dynamically sets the consistency level in a Cassandra database based on our operational needs. We begin by establishing a connection to the Cassandra cluster, specifying the address of the node we want to connect to and the keyspace that contains our data. Next, we define a function called getProduct, which takes two arguments, producted and consistency level. Inside this function, we set the session's default consistency level using the provided consistency level parameter. This dynamic assignment enables us to optimize our read operations for speed when appropriate, such as by retrieving data from a single replica, or to enhance write operations by requiring confirmations from multiple replicas, depending on our consistency requirements. In the function body, we construct a query to select the available quantity of a specific product using its ID. When the query is executed, it returns the result, allowing us to fetch the product's availability seamlessly. Finally, we demonstrate how to retrieve product information with a lower consistency level by calling the function and printing the result. This approach illustrates a pragmatic application of the CAP theorem principles by adjusting our design strategy to fit varying consistency needs. Ultimately, as developers, we must embrace a mindset that anticipates the trade-offs involved in our design choices. Understanding the CAP theorem not only helps us make informed decisions, but empowers us to communicate such decisions effectively with our teams and stakeholders. After all, designing a scalable, flexible, and robust system is as much about architectural clarity as it is about implementing the right technologies. As we lead our systems into the future, we can leverage insights from the CAP theorem to build resilient applications that continue to serve users effectively, regardless of the challenges presented by distributed environments. Embracing this complexity is part of what makes database design both challenging and remarkably rewarding. In conclusion, today's lesson has equipped us with a better understanding of the implications of NoSQL design choices rooted in the CAP theorem. We've explored how each property interacts within the confines of our applications, navigating the necessary trade-offs between consistency, availability, and partition tolerance. As you forge ahead in your development journey, always remember the careful balance you must strike in designing systems that can handle the complexities of modern data demands. Happy coding. Transaction management and concurrency control are crucial elements in database systems, particularly in NoSQL environments, where ensuring data integrity and consistency can be quite challenging due to their distributed nature. Today, we will explore how advanced transaction management can be achieved in NoSQL systems, emphasizing strategies for maintaining reliability and consistency even in the face of concurrent operations. So far, we learned that the design choices in NoSQL databases are significantly influenced by the CAP theorem, which emphasizes the trade-offs between consistency, availability, and partition tolerance. We explored the base model, which prioritizes availability over immediate consistency, leading to flexible and scalable applications. Additionally, we highlighted scenarios demonstrating how developers must choose which 2 out of the 3 properties to prioritize based on their specific application needs. Understanding these implications is vital for architects to create resilient systems capable of effectively handling distributed data challenges. Now let's see how we can implement a multi-document transaction in MongoDB to achieve atomic updates across different collections. First, we initiate a connection to the MongoDB server and specify the database we want to work with. We then start a new session, which is crucial for executing transactions. Next, we define our transaction operations as an array of commands, where each command specifies the updates we want to perform. Here, we aim to set the quantity fields for 2 different products. The key part of our implementation is the try block, where we initiate the transaction with session start transaction. Inside this block, we perform the updates, ensuring to include the session parameter, which makes these operations part of the current transaction context. If both operations successfully execute, we commit the transaction with session commit transaction, confirming that the changes should be saved. However, if any exception occurs during the process, we catch it, abort the transaction using session abort transaction, and provide feedback on the failure. Finally, whether successful or not, we end the session to clean up resources and conclude the transaction workflow. This methodology guarantees atomicity even in the distributed NoSQL environment, reinforcing data integrity. Now let's see how we can implement a conflict resolution strategy using the last right wins (LWW) approach in our updates. In this example, we define a function called updateDocument, which takes a documented and a new value containing the updated data. The first step is to retrieve the existing document from the database by its ID to access its current state, including its timestamp. Next, we compare the timestamp of the incoming update with the timestamp of the existing document. This comparison is crucial for determining whether the incoming update should take precedence over the existing data. If the new value has a timestamp greater than the current document's timestamp, it indicates that it is more recent, and we proceed to update the document in the database. This is done with an update operation that sets the new value. However, if the incoming update's timestamp is not greater, we print a message indicating that the update is ignored because it's based on an older version of the document. Through this mechanism, we ensure that only the latest update is applied, allowing us to maintain consistency in scenarios where multiple updates might occur concurrently. Now let's take a look at a simplistic implementation of optimistic concurrency control, OCC, with the update price function. This function was designed to manage the price updates of a product in a way that minimizes conflicts arising from simultaneous transactions. Initially, the function enters an infinite loop that continues until the price update is successfully applied. Inside the loop, we first retrieve the current price of a product using its producted from the database. This is vital because we need to know the original price to ensure that our update only occurs if the price hasn't changed since we fetched the data. Next, we attempt to update the product's price in the database while checking for conflicts. The update operation uses a condition that matches the original price. If the product's price has been altered by another transaction, this condition will fail. If the modification is successful, a message is printed indicating the price has been updated, and the loop breaks. However, if a conflict is detected, a message is printed saying that a conflict was detected, and the loop continues, allowing the function to retry the operation. This approach ensures that only the most recent price change is saved, exemplifying the essence of OCC in maintaining data integrity. Now let's implement the following command in Apache Cassandra to create a new keyspace that enhances data durability. This command sets up a keyspace named myKeyspace with a specific replication strategy. By using the simple strategy class, we ensure a straightforward replication mechanism suitable for a single data center environment. The most critical aspect is the replication factor, which is set to 3 in this case. By selecting a replication factor of 3, we ensure that each piece of data is stored on 3 different nodes within the cluster. This redundancy is vital for durability because, in the event of a node failure, the system can still retrieve data from the remaining nodes. Therefore, even if 1 or 2 nodes fail, the data remains safe and accessible across the other nodes, significantly enhancing the reliability of the database. This configuration not only aids in recovering from potential data loss due to node failures, but also improves read availability, making it a crucial step in designing resilient Nosql applications. Through this demonstration, we see how keyspace configuration in Cassandra plays a central role in achieving durable transaction management in distributed environments. In summary, advanced transaction management in Nosql requires an understanding of atomicity, consistency, isolation, and durability. Implementing these principles effectively often requires choosing the right strategies suited for the unique challenges presented by distributed systems. Nosql databases offer various methodologies, from multi-document transactions in MongoDB to conflict resolution mechanisms in Cassandra, enabling developers to tailor their approach based on application needs. So far, we discussed each of the ACID properties and how they can be approached within Nosql environments. Now, we will explore some practical scenarios where these strategies can be especially useful and how to implement them effectively in real-world applications. Now let's see how we can implement the order placement functionality in our e-commerce application. The placeOrder function initiates a session to handle transactions within the database. This is crucial because it helps maintain the integrity of operations, ensuring that related actions, like reducing inventory and creating an order, are executed atomically. We start the transaction by invoking session_start_transaction. Next, we check the inventory for the item requested in the order. By querying the inventory, we can verify whether there's enough stock available. If the stock is sufficient, we proceed to deduct the quantity from the inventory using the updateOne function, and we associate this operation with the active transaction session to ensure it is included in the transaction. Once the inventory is updated, we create the order by inserting it into the orders collection, again tying this action to the same session. Upon successful completion of both operations, we commit the transaction, confirming all changes in the database for the session. If there's not enough stock or any error occurs, the process is aborted, rolling back all changes to maintain data consistency, and the session is closed finally. This approach enhances the reliability and performance of our application by ensuring that transactions remain atomic even under high concurrency. As we wrap up this exploration of advanced transaction management in NoSQL databases, bear in mind that while the flexibility of NoSQL systems allows for ingenious applications, it requires careful consideration of how transactions are structured. Understanding the nuances of each NoSQL database and their respective transaction processing capabilities will empower you to make informed decisions that align with your application requirements. The world of NoSQL is always evolving, and by mastering these advanced transaction concepts, you set yourself up for success in creating robust and scalable applications that can handle the demands of modern software environments. Happy coding! Today, we're diving into a crucial concept in distributed systems and NoSQL databases, the CAP theorem. Understanding this theorem will greatly enhance your ability to design reliable and efficient databases. So, let's get started. So far, we learned about transaction management and concurrency control as essential in NoSQL databases to ensure data integrity amidst their distributed nature. We covered key ACID properties, atomicity, consistency, isolation, and durability, and discussed various strategies such as multi-document transactions and optimistic concurrency control to address challenges within these frameworks. The importance of understanding consistency models like strong and eventual consistency, along with conflict resolution techniques like last right wins, was highlighted. As we continue, we'll focus on practical scenarios that demonstrate the application of these principles. The CAP theorem proposed by Eric Brewer in the early 2000s asserts that in any distributed data store, one can only achieve two of the following three guarantees: consistency, availability, and partition tolerance, often referred to as the CAP attributes. To clarify, let's break down each of these terms. Consistency means that every read receives the most recent write or an error. If one node in a distributed system has been updated, all the nodes must reflect that update before any reads can occur. Availability implies that every request receives a response, either success or failure, without guaranteed consistency. Lastly, partition tolerance is the ability of the system to continue operating despite network partitions. This means that even if nodes cannot communicate with each other, the system will still function. The displayed bar chart, titled Effectiveness of CAP Attributes in Distributed Systems, quantifies the relative effectiveness of the three CAP attributes on the vertical axis labeled effectiveness %. Three color-coded bars represent the attributes: consistency at 80% green, availability at 90% blue, and partition tolerance at 85% amber. Each bar is annotated with its numeric value atop the bar, making direct comparison straightforward. Availability is the highest at 90%, partition tolerance follows at 85%, and consistency is lowest at 80%. From these values, we can conclude that in this depiction, system designs prioritize availability most strongly, with partition tolerance nearly as emphasized and consistency slightly de-emphasized. The modest gaps between the bars indicate a trade-off that favors keeping systems responsive and resilient to network partitions, while accepting a limited, quantifiable reduction in strict consistency guarantees. Now let's see how we can implement MongoDB operations for handling user posts in our social media application. First, we start by importing the Mongo client from the PyMongo library, which allows us to connect to our MongoDB database. We then establish a connection to the database located at localhost on port 27017 and specify the database name as social media. Once connected, we create a dictionary called post that holds the user post data. This dictionary includes the unique user ID, the actual content of the post, and a timestamp indicating when the post was created, which we retrieve using datatime now. This structured format allows us to store essential attributes about each user post systematically. Next, we perform the insertion of the post into the posts collection of our database using the insert1 method. This action will save the post data, ensuring it is available immediately for users, thus demonstrating high availability. The operation returns a result object that allows us to access the unique ID of the newly created post. Finally, we print a success message that includes the post ID, confirming that the post was successfully created in the database. This setup illustrates how to handle user interactions while prioritizing availability in our application, following the concepts outlined in the CAP theorem. Now let's implement the following code to handle the updates of a post in our social media application. This example illustrates how we can update a post while addressing the potential for concurrent writes due to network partitions. In this code snippet, we begin by creating an update query that specifies the user ID and the new content for the post. We then utilize the update1 method provided by MongoDB's driver to find the specific post matching the user's ID. Inside this method, we utilize a query to select the document we want to update and employ the set operator to modify the content and timestamp of that post. After performing the update operation, we check the modified count attribute from the result. This attribute indicates whether any updates were made to the post. If modified count is greater than 0, it means that the update was successful and we print a confirmation message. Conversely, if no modifications were made, we output a different message indicating that no updates occurred. This process effectively illustrates how we can maintain availability and manage conflict resolution in a distributed system, while ensuring users can continue to create content even during network issues. Now let's see how we can implement a simple transaction in PostgreSQL, which emphasizes consistency through ACID properties. We start the transaction with the command begin, indicating that a series of operations is about to take place that should be treated as a single unit of work. This is crucial in scenarios such as transferring funds between user accounts, where it is essential that either both operations complete successfully or none do to maintain balance integrity. Next, we execute two update statements. The first one deducts an amount from one user's account, and the second adds that same amount to another user's account. These operations directly manipulate the account balances, reflecting the transactional nature of this process. If any issues arise during these updates, such as database errors or constraint violations, the entire transaction can be rolled back. This is a fundamental feature of PostgreSQL, ensuring that the database remains consistent even in the face of unexpected interruptions. Finally, we conclude the transaction with the commit command. This finalizes all changes made during the transaction, making them permanent. If everything proceeds without error, both updates are saved, ensuring critical accuracy and reliability in our application's financial operations. This approach illustrates how well-structured transactions in PostgreSQL offer strong consistency guarantees, essential for applications handling sensitive data like financial transactions. Now let's see how we can implement a table in Cassandra to track user activity effectively. The given SQL statement creates a table named user activity, which will store details about each user's interactions. The primary key consists of user ID, uniquely identifying each user's activity while allowing for efficient retrieval of records. The activity time field captures the timestamp when the activity occurs, and activity description stores a textual description of that activity. This flexible schema supports the storage of varied and evolving data, which is common in real-time analytics applications. Moreover, the use of with compact storage instructs Cassandra to optimize storage for this table, which is particularly beneficial when handling large datasets with many sparse columns. The read repair chance setting is key to enhancing data consistency. By specifying it as 0.1, we're allowing the system to perform read repairs 10% of the time when data inconsistencies are detected, thus striking a balance between performance and eventual consistency, a vital feature under the CAP theorem's trade-offs. This setup exemplifies how Cassandra is tuned for high availability and partition tolerance, making it an ideal choice for real-time analytics where data integrity is important but doesn't need to be immediate. Now that we have looked at some of the Nosql solutions and database models, let's review some illustrative case studies highlighting real-world applications of the CAP theorem. Picture a streaming service like Netflix, which requires high availability. During peak usage hours, it is essential that users can access movies without delays. To maintain this availability, Netflix employs a microservices architecture that spreads requests across its global infrastructure. In this environment, slight inconsistencies may arise. For instance, if a user begins watching a show on one device, the service may not immediately reflect this on another. However, Netflix manages to offer a seamless experience thanks to effective caching strategies that prioritize availability, even as they refine consistency over time. Another notable example is Airbnb, which relies on strong consistency to prevent conflicts when booking properties. Through a combination of PostgreSQL with eventual replication to Nosql databases for analytics, Airbnb ensures users see available properties in real time, balancing availability for user experience and strong consistency for transactional integrity. So as we wrap up our discussion on the CAP theorem and design choices in NoSQL, remember that understanding the implications and trade-offs is crucial for effective database design. Whenever you're faced with a choice between availability, consistency, and partition tolerance, reflect on your application's specific requirements. In building systems capable of handling vast amounts of data and users, you'll often gravitate towards strategies that prioritize not just one of the CAP attributes but a balanced approach tailored to your use case. Thank you for joining this exploration today, and as you continue your database journey, remember these principles as guiding lights in your architectural decisions. With great knowledge comes the power to create even greater systems. Happy coding. Now let's implement the tables that will structure our graph for the social media application. First, we create a users table, which serves as a repository for user information, with each user assigned a unique identifier through the id column defined as a serial primary key. This ensures that every user added to the table has a distinct, automatically generated numerical ID. The name column will store the name of the user, and it is defined as a varchar with a limit of 50 characters, ensuring that the input will not exceed this length. Next, we need to establish the relationships between users by creating a friendships table. This table contains two columns, userid A and userid B, both referencing the id field in the users table. This reference not only establishes a link between users but also enforces data integrity, ensuring that any friendships recorded in this table align with actual users. The combination of both user IDs as a primary key prevents duplicate friendships, ensuring that each relationship is unique. By setting up these tables this way, we create a flexible structure for user data and relationships, allowing us to easily traverse connections, which is central to the functionality of graph databases. Now let's look at how we can insert new users and establish friendships in our database. First, we begin by populating the users table with three distinct entries, Alice, Bob, and Charlie. This is achieved using a straightforward insert statement that allows us to add multiple values in one go, making it efficient to populate the table quickly. Following this, we need to define the relationships between these users, which we accomplish through the friendships table. Here, we specify pairs of user IDs to indicate who is friends with whom. For example, Alice is friends with Bob and Charlie, while Bob is also friends with Charlie. Next, if we want to find out Alice's friends, we'll perform a query on the friendships table. This query uses join operations to connect the friendships with the users, allowing us to fetch the names of the users associated with Alice's user ID. By filtering through the relationships established previously, we can retrieve a list of her friends efficiently. This demonstrates how relational queries can reflect interconnected data, although graph databases would handle such queries even more effortlessly. The figure titled Effectiveness of Graph Databases in Various Applications displays a horizontal bar chart that quantifies perceived effectiveness % across 5 application areas: social network, recommendation systems, fraud detection, network management, and smart cities. The chart shows exact values as data labels at the end of each bar: social network at 95%, recommendation systems at 90%, smart cities at 88%, fraud detection at 85%, and network management at 80%. From these values, we can conclude that all 5 domains score highly, all above 80%, indicating broad applicability of graph databases. The pattern shows social network as the clear leader, 95%, with recommendation systems and smart cities closely following, 90% and 88% respectively, which suggests these domains benefit most from relationship-centric queries and rapid traversals. Fraud detection sits in the middle, 85%, underlining strong usefulness for modeling transaction paths and anomaly detection, while network management, 80%, though the lowest, still reflects meaningful utility for mapping device interconnections and reachability. The horizontal orientation and labeled axes make it easy to compare categories directly and read precise effectiveness percentages, revealing a modest spread, 15 percentage points, between the highest and lowest scores, and underscoring that graph databases are considered highly effective across diverse real-world use cases. Now let's implement the database structure to support our recommendation system, focusing on how users interact with products. First, we create a products table, which will store details about each item, including a unique identifier for the product and its name, ensuring that each product's name is not null. This setup allows for a straightforward way to add and retrieve product information. Next, we establish a user product views table to record interactions between users and products. This table contains two foreign keys: userid, which references the user's table to associate each view with a specific user, and producted, linking to the products table to indicate which product has been viewed. The combination of these keys as a composite primary key ensures that each user can only have one record for each product they view, preventing duplicate entries. Now let's see how we can implement a query that recommends products to a user, in this case Alice, based on what her friends have viewed. This involves joining the user product views, users, and products tables to retrieve distinct product names that Alice hasn't yet interacted with. By using subqueries to identify Alice's friends and filter out products Alice has already seen, we efficiently generate personalized recommendations for her, showcasing the power of graph databases in leveraging relationships for insightful data retrieval. Now let's dive into how to set up the database structure for handling accounts and transactions in our fraud detection system. We begin by creating a table for the accounts, where each account is given a unique identifier through a serial primary key, and we also store the account number, making sure it is not null. This structure is essential as it allows us to clearly identify each account in our analyses. Next, we proceed to create the transactions table. This table establishes the relationship between accounts by using foreign keys that reference the account IDs from the accounts table. Each transaction record includes the sender and receiver's account IDs, the transaction amount, and a timestamp that captures when the transaction occurred. This design is crucial for tracking the flow of funds and enabling us to analyze interactions between different accounts. Now let's see how we can identify suspicious activity. We write a query that counts transactions between pairs of accounts, grouping the results by the account IDs involved in each transaction. By applying a filter to gather only those pairs with more than 10 transactions, we effectively highlight unusual patterns of activity that may suggest fraudulent behavior. This query is invaluable for fraud analysts as it pinpoints accounts that require further investigation. Now let's see how we can implement the structure for our network management system using graph databases. First, we create a devices table, which will store information about each device in our network. This includes a unique identifier for each device, a name, and a type, ensuring that we can categorize devices effectively. Next, we establish the relationships between devices with a connections table. This table will utilize a composite primary key consisting of two device IDs, allowing us to map connections directly between devices, whether that be servers, routers, or switches. Next, we must consider how to efficiently query our graph structure for operational insights. To achieve this, we write a recursive query to gather information about all devices that are reachable from a specific device, router 1 in this case. The recursive component of the query allows us to traverse the connections dynamically, first retrieving the devices directly connected to router 1, and then exploring further connections through successive iterations. By joining the results with our devices table, we can obtain the names of all reachable devices, demonstrating the efficiency of graph databases in network management and their ability to maintain uptime and performance through robust querying capabilities. Now let's see how we can implement a query that effectively analyzes data from traffic and weather sensors within a smart city framework. The code utilizes a SQL select statement to retrieve the average data readings from both traffic sensors and weather sensors. Here, we select the device IDs from the respective sensor tables, traffic sensors, and weather sensors, which allows us to identify the sources of our data. Next, we join these two tables on their geographical location to ensure that we are correlating the appropriate data points for the same area. This is crucial, as traffic patterns will likely vary based on local weather conditions. By using the AVG function, we calculate the average traffic and weather readings for each device, which provides valuable insights into how these factors influence one another. Finally, the group BY clause is employed to categorize the results based on device IDs, ensuring that our averages are grouped correctly for accurate analysis. This query will empower city planners to make informed, data-driven decisions that enhance urban living and efficiently manage city resources. Now, as we wrap up our exploration into the future applications of graph databases, it's important to understand that their unique capabilities are just getting started. From recommendation engines to fraud detection, network analysis, and smart city applications, the potential is vast. As the world becomes increasingly interconnected, leveraging the relationships between data points will be vital for innovation and efficiencies. Graph databases are well equipped to address the complexities of interconnected data, enabling businesses to uncover insights, enhance decision-making, and maintain the responsiveness required in today's fast-paced environment. Moving forward, as you consider database solutions for your applications, think about the power of graph databases, their ability to model real-world relationships, and their impact on your data-driven decisions. Thank you for joining us in this exploration, and I'm looking forward to seeing how you will leverage these exciting technologies in your projects. In this final section, we will do a project challenge to apply what we have learned so far. Your task is to design and implement a fully functional database system for a fictional e-commerce platform using PostgreSQL or MySQL. Begin by defining the necessary entities like users, products, orders, categories, and reviews, and create a detailed entity relationship diagram (ERD) that illustrates the relationships among these entities. Once your design is complete, you'll build the database schema using SQL commands, ensuring that your tables are properly normalized. After that, populate your database with sample data to simulate realistic interactions within your e-commerce platform. You'll need to develop queries to extract valuable insights, such as retrieving products by category or listing user orders. Lastly, document your entire process, including the design decisions you made, the SQL scripts used, and the queries performed. This is your chance to showcase your skills and creativity, so dive in and bring your vision to life. You can find the final project details in the GitHub repository linked in the description.